my first conversation onto the stream was probably not the right one, because you're right, I was muted onto the stream. This is the kind of thing I might need some help with from, smart people like you, Dwight, if I start screwing that up. One of the things I'm going to do, or going to have to do across the course of the day, is switch off mics and video and other things while I'm running presentations so that I don't overtalk them and other stuff. And if I get any of that wrong, it's going to be a little rough. That's the mistake I hope not to make. But anyway, for those folks that are actually on the stream at this point, apologies for having it scheduled to start early. I gave myself a buffer to screw up and make my earliest mistakes, and I'll make new ones, better ones later. And as of right now, we've got about 5 minutes before I'll start the formal program. And we're just doing mic tests and other stuff, and when I publish the stream, I'll probably cut this all out. Probably be.
So Eric, just doing a mic check that you can hear me?
Yep.
It's Dave. Great.
Sounds good.
Thank you.
Yeah, Corey's a little bit, well, he's always been, things always go sideways with Corey. And then, Jeff's a lot like the Vanisher from Deadpool.
What
Can
happened?
anybody hear me?
I heard my name in vain.
Your camera sideways.
Probably. Does it have to go this way?
Yeah, better.
It doesn't. It's not smart enough to realize it's sideways.
No.
No, it should be fine.
Now it is.
Isn't it now fine?
Now it is.
Yeah, that's weird.
Works
It doesn't
now.
Like when I'm turning it. I blame Google. Okay, Google, fix yourself.
Yeah, I always blame Google. Or Googlers.
It's better to be a Googler than to be a musketeer. Those are those SpaceX and Tesla crazies.
Well, those guys are going to be stuck up in orbit for a few more days, I'm going to guess.
Yeah.
Where's my... Oh, 16. Okay, that's good. That was just me showing off again. For those not in the know, I use an IBM Model M keyboard everywhere I go. I even carry them with me on vacation. And no, I'm not kidding.
I'm sure your neighbors appreciate the sound of that mechanical keyboard.
I get complaints at work. I think people are actually happy about COVID. My coworkers are actually happy about COVID just so they don't have to hear me type. And they can also tell my mood, which is the funny part, right? You can tell when I'm pissed because my typing gets harder, faster, or whatever. All right. So I think the good news for anyone that's monitoring the stream right now is the stream is working properly. They can see our Google Meet window up. They can hear me. They can hear the people replying to me. That's a pretty good start to the day, to be honest with you. I mean, except for the me part. We'll have to remember to put these away.
What is that?
They're poker chips. I just sit here and I do little...
Oh.
I spend a little bit too much time playing with these things, which again annoys my neighbors at work.
Fidget spinners, huh?
Yeah, they're my version of the fidget spinner. And if I sit here and do this all day long, I'm going to be on audio doing that all day long, and I'm sure I'm going to get in trouble for it. All right. See if I can find my notes. Get our stuff in gear here. Keep doors closed. Doesn't sound like any fun at all. All right. should work fine. If anyone's on the stream, I'm going to go and mute my Meet mic, and hopefully I'm still audible. So if you can still hear me, give me a wave or something. But other than that, I'm hoping everything's good. All right. It is 9 o'clock on the Pacific Coast. We are officially live, and we're officially starting our virtual VCF West.
I don't hear him, do you?
Oh, hold on a second. And yes, I'm putting the chips away. So for those that are on the Meets meeting, well, actually, you know what? I'll leave it live, but I'll ask you guys to mute your mics just so that you're not talking over me if we're getting into that mode. And I'm going to give it a minute or two and see if we get any more viewers on the actual stream over the course of the next couple minutes. And then I'll introduce our show and get us rolling. This is going to be a fun day. It's going to be a long day, but it's going to be a fun day.
So it looks like we should be watching the stream and this meets at the same time.
I would say that you're best off watching the stream unless you are being called on for Q&A, in which case I would definitely be on the Meets because that's the only place it's going to work.
Okay, got it.
And if you have questions for other presenters, you can jump on the Meets and ask the questions that way, etc.
Hey, Eric, it's 9:01.
Yep, I know. I'm just making sure that we get our audience in full. Everyone shows up a little bit late to these things, right? All right. Might as well get ourselves started once again, and I'll probably cut some of the previous stuff. Once again, welcome to VCF West 2020. This VCF is a virtual event this year, unfortunately. I really did want to do the in-person event. The things that we do at the Computer History Museum are obviously interactive, hands-on, and you get a whole lot more of an experience than you're going to be getting from the videos. However, the videos actually are an excellent source of information as well because they're organized and pre-planned and pre-edited, and the people that are presenting these videos, that have put these videos together, get to put their passion into them and put them into a compact package for you in the online format, which is equally awesome, just different. We will be doing the in-person show again next year, come hell or high water. At least I hope. And as with this year, I've reserved the full top floor of the Computer History Museum, which means that we're going to have much more space than we've ever had before. And that means we're going to need more exhibits, more talks, more of everything, more guests. So I'm looking forward to next year, but let's get through this year first. I did want to do a little bit of housekeeping about this event in general before we start. Well, first of all, fire exits. No, that's the wrong speech. The first thing to say is that this is a first. We haven't done a virtual event before. We're new at this. I've practiced as much as I can offline, but we're online now. And I'm sure that I've made a bunch of good mistakes before we got live. I'm going to make all new ones throughout the course of the day. Call me on them if you catch me. But please be patient with the fact that we're doing this for the first time and things may not go perfectly. The layout of the screens that we've got going forward are going to include this video chat, and it's not going to be my face because once I'm done with this introduction, my face goes away. You're welcome. And for the people that are on our Google Meets, I do want to ask to be cognizant of the fact that you are on the screen at all times. So we're going to be running the videos as the bigger part of the screen. I've got the schedule up, hopefully readably on the upper left. And then on the lower left, we're going to actually have the little thumbnails of everybody that's on this video chat. And I'd really rather that be a picture of the fact that this is a live event and not a distraction to the videos that are being run. So if you are on video and need to do something locally that might be a distraction, please turn off your video. The audio won't be running except during the Q&A sessions. If you are involved in the Q&A, mute your mic unless you need to talk. And definitely mute your mic if you're snacking on a noisy bag of chips or whatever else. Let's see. The Q&A is going to be firewalled. So what we've decided, rather than using the Q&A sessions on actual live stream, which you're welcome to do, you're welcome to post comments on the live stream, you're welcome to ask questions. We will get to those at some point, but it won't be during the live stream itself. But what we've got is we have set up an email address, microphone@vcfed.org, and that email address is for asking questions of the presenters. My request to anyone that is asking questions is to please put the name of the person that you are asking, or the name of the presentation that you are asking of, in the subject of the message. So if you're going to ask me a question, you'd put Eric Klein in the subject, and then you would put the question that you have in the message itself and send it there. We have a couple of volunteers that have agreed to curate those questions as they come in, and when we get to a Q&A after each video, we will be running through those questions in a curated fashion, meaning we're going to ask the ones that we think will fit in the time and that are most apropos to the presentation itself. Any additional questions, anything we didn't get to based on either time or content, we will be able to forward to the presenter, the folks that made the video, and different folks are going to have different ways of being able to answer those, but we'll try and get those answers up on the individual video streams afterwards. And speaking of which, the videos themselves are currently embargoed, but at midnight tonight will be available on our YouTube feed. So each of the individual presentations that you'll be viewing today as we go through will be available there. And again, you can ask questions under those videos, or we'll be posting email addresses or forum handles or whatever else for the folks that are going to be dealing with videos. Again, Dag Spicer, one of our volunteers, and Jeff Brace, one of our others, are going to be helping along with maybe some other folks at our museum back east in New Jersey with question curation. And finally, one of the things that I have had to do because of this being a virtual event, and because of the overwhelming support we've got for this, is I've had to schedule this thing really tightly. So for those that have seen the schedule online, we've got, I remember correctly, 19 presentations and roughly 8.5 hours of content. That's going to take a lot of effort and a lot of energy to stay on target with, and some people aren't going to want to come in for the entire day. Some people are going to poke in for a specific exhibit at a specific time, and I don't want them to miss that time because we've fallen off schedule because of Q&A or whatever else. So I'm going to unfortunately be kind of mean. If we're running really close to the next scheduled speaker and we're in the middle of a question or the middle of an answer, I'm going to cut you off. And my apologies in advance for this. I'm not trying to be rude, but I'm going to have to be in order to keep us on schedule, and I hope you can appreciate that. The other stuff, the only other thing that I want to really say about this event before we kick off our first video is a huge thank you to everyone that's been involved in this entire thing. We've got all of these presentations that have come in. We've got all the volunteers from the VCF Board of Directors, through our video editors, through a bunch of other folks who have done amazing things to help this thing along. The idea of a virtual event came up fairly late, obviously, in our planning. I wouldn't say it was rushed, but I will say that it was still quite impressive that we were able to get to this point and only got here because of all the people who threw in to help out. So thank you to everyone who submitted videos. Thank you to everyone who edited videos. Thank you to everyone who's answering questions, asking questions, and especially thank you to everyone who's online enjoying the show now or in the recorded sessions later. With that said, I'm going to take a little bit of time, and I'm going to get Corey's video. Corey is our first presenter today, and get him rolling so we can enjoy hearing about Corey Cohen's Sol20, the first of a pair of Sol20s we're going to see this morning. His with a Helios disk system, which is an impressive thing, as I'll let you hear from Corey.
Hello, my name is Corey Cohen, and some of you may know me from the Apple world, but I actually collect other types of computers. Today I'm going to talk to you and show you the Sol20 personal computer from Processor Technology and a very rare and functional Helios 2 disk subsystem made by Processor Technology that worked with the Sol20. This is an 8-inch floppy system, and as we go through it, I'll explain why it's so rare to have one that's actually functional in today's day and age. The first step for us is to turn on the Helios system using a key. This was built to be a professional system for businesses. The Helios unit actually weighs 70 pounds and is made of very hefty metal. We then need to turn on our Sol20 system. The first thing we're going to do here is we're going to put a disk in this case PT-DOS 1.5, our operating system. We'll put it in drive 0. We will go over to our Sol20 system, and at the prompt, type boot to load the operating system. I can list the files very simply. I can even simply run a program like Targ or Target. Target was one of the first programs shown on television back in 1976 on the Tomorrow Show, mesmerizing host Tom Schneider. Now while we're here, let's talk a little bit about PT-DOS. PT-DOS is very similar in design to a modern Unix. All file I/O, all system I/O are done through file handles. So if I wanted to write to the serial port, I can simply copy a file to a specific file object, and the information will be sent to the serial port. One of the other very nice features of PT-DOS is the fact that it has built-in help. This was pretty rare for operating systems back in 1976, 1977, so if you would get the name of a command, you can simply look it up. For example, I'm always forgetting the fact that free has a question mark after it. The Helios system also supports running other operating systems than just PT-DOS. CP/M 1.4 was available from Lifeboat. I actually have one of the only working copies of CP/M 1.4 for the Helios system, and have archived and shared this with other Helios system owners. There aren't very many of us with working systems. One of the things that you'll notice is there is only 46K for this CP/M version. That is because internally, the Helios system and the Sol20 reserve some of the upper memory, and this is what limits us for our CP/M system. So I can run a little utility that lets me install some CP/M 2.2 extensions, and I can even run Zork on this system. So while we're here loading Zork, let's talk a little bit about what plugs into the Sol20 from the Helios system. Well, the Helios system has two cards that are in the Sol20 system, two S100 cards. There is a formatter card as well as a controller card. This, combined with a special personality module for the Sol20, will provide the ability to boot the Helios system. So while we load up another program for the Helios system, the actual sales demo used in 1977 by Processor Technology to show off the Helios system, let's talk a little bit about why there are so few working systems. The Helios 2 disk subsystem used a PERSY 277 drive, very much like some of the Kremenko systems. However, understand some things about this drive. The drive used a lot of hard drive technologies for a floppy drive. It had a voice coil system. It used a mirror with graduating lines on it to position the head. If the head was not tied down or secured during shipping, basically your drive was destroyed. If the mirror cracked, game over. And even today, just through age, the mirrors fall off these drives, and they must be positioned perfectly and re-glued on, or the drive is basically unusable. Also, many of the capacitors, the tantalum capacitors in the system, were actually spec'd just a little bit too close to where they needed to be, so that they tend to fail. And they fail spectacularly, and they're not easy to replace based upon how the drive has to be essentially disassembled to change them out. And then you've got to go through some very complex procedures in order to recalibrate the drive. The Helios system also has an electrical eject system. The gears for this system are nylon, and almost every single one by now have cracked, and you can no longer eject the disks out of the drive. Yes, someone has actually gone out and produced a couple of gears, and those gears can be used to fix this. But there are a handful of those gears left. So we know there are a handful of working drives. Now the new gears were produced in a much better material and should never have this problem again, but only a handful remain. So any Helios system that has not had the gears replaced is living on borrowed time. One final thing that should be mentioned about the Helios systems. They're extremely heavy, and many of them are dented because someone has dropped them because of just how large and heavy they are. So that also affects the problem with the mirrors. Now, one other thing that should be mentioned about the PERSY 277 drive is while it is a dual disk drive, it actually is not technically a dual drive. It shares a lot of components between the two drives. And this is why you'll hear when you use the drive, for example, when you're copying disks, a lot of clattering as things are repositioned between drive 0 and drive 1. It's a very interesting system. Now, some of you may say you've got a Helios system, but it doesn't have the electric eject, and it really is two separate drives. Many of the discarded or broken Helios system PERSY drives were just simply removed, and the large case was used to house Seagate and other drives, though they are not compatible with running Helios software. One of the things that I get asked often about this particular Sol20 system is, wow, it's so clean. Is it new? Is it real? Well, this is a restored system. While I do have some unrestored Sol20s that look pretty good, this particular system has actually been fully restored. That restoration included not only bringing everything down to bare metal to remove all the crazy little things, dings, dents, and rust that were actually on the system, and then it was completely refinished, repainted with the complete factory-style splatter coat. But the system was also rebuilt, specifically the Helios 2 drive system, from the ground up. The bearings have been repacked, all the gears were changed out, the sensors were recalibrated, all the capacitors were changed out. It is essentially a new drive, and hopefully we will be able to enjoy seeing the Helios 2 system operate for years to come.
All right. Hopefully Corey's online right now, because he's supposed to be in order to answer questions for us.
Yes, I am.
Oh, there he is. So,
There I am.
you were invisible for a moment. So, again, for those that are asking questions, our email address for questions is microphone@vcfed.org. And the ask is that you put Corey's name in the subject of the message and shoot us an email with any questions that you have about his Sol20 and Helios system. And Dag, if you're on, are there any pending questions at this point? Dag's on mute.
I'm here, Eric. I don't see any questions yet.
All right, that's fair.
Yeah.
Because
I think people are just getting used to the fact that we're we have an email address for the questions, and hopefully I answered most of the questions in the video. So
well, that is the goal. But the good news is, and this is something I wanted you to do anyway, we can get you, and I don't know how to let's see if
how to make me big.
Yeah, I can make you big, and what we want to do is Corey is wandering around the Vintage Computer Federation Museum in Wall, New Jersey. And I'm going to let you talk about it since you're there.
Okay, so yeah, I'm actually sort of in the middle of the museum now. We were going to try and do this later, I think, using a tripod, so I apologize if it's a little shaky. But yeah, so I'm in the Vintage Computer Federation Museum in Wall, New Jersey at the Bil.H Science Center. I'm actually standing right next to a 1980s bedroom exhibit. So I don't know if you are making me big. I don't know.
Yep,
I guess
no,
I am. I'm looking at the monitor down there. So basically, here's, for example, of one of our exhibits. Let me turn a little bit because I got to keep it on the camera here. So this is a 1980s bedroom exhibit. So kind of the idea of being a typical bedroom for a teenager in the 1980s. It's very popular, and we just really put this up. We were hoping to show this off live at VCF East, but with all the restrictions due to COVID, I think this might be our introduction to it. So let me get a little closer, just so you guys can kind of see some of the. I'm gonna try and do this as best as I can. Some of the features here. So we've got kind of what our bookshelves look like. The kind of messy Commodore 64 computer that would have been set up and playing video games back then. We're doing other things. We actually have this set up as a, let's move this down a little bit. We have this set up with Print Shop. So anyone who comes in with their family, we can, they can create a sign and print it out in Print Shop. And next to it, we've got had a lot of fun building this, our cubicle. And those of you who worked in the 80s and early 90s in an office building would remember these kind of cubicles with this, this wood trim and the gray. And here we've got, a digital rainbow computer. Hopefully you can see this. So I'm going to back up a little bit, trying to kind of show you this. So this would have been a computer in sort of on a technical person's desk in many cases, though it did run IBM Microsoft MS-DOS, and it also ran some VAC software. But we'll rotate these exhibits out. I'm sure at some point we'll have an IBM PC. And as we go in, I'm going to take you guys through some of the more larger machines in a minute. Now, we do have a giant warehouse full of stuff, so we do rotate things in and out. But, this is kind of, I guess, one of my favorites. This is a PC Junior running King's Quest. And we've kind of got two levels here of things. We've got some foreign computers. This is a Soviet computer.
Eric, I
see
don't
that?
want to interrupt Corey, but we do have some questions.
Oh, okay. I guess we'll go into some questions then. Maybe I'll do the tour later and I'll do it on the tripod. That'll be a lot easier and a lot nicer because I won't be trying to look and level and see things. So sure, questions ahead. Go ahead.
Can you connect the Sol20 to a BBS?
Yes, you can. So the Sol20 has built-in serial and parallel ports. As a matter of fact, one of the first modems that you'll see around was developed by the same person. The penny whistle modem was developed by Lee Feldstein, who developed the Sol20. So kind of cool. And yeah, definitely you can connect to a BBS. Sol20 is kind of also neat in that you can hit one button and it kind of becomes a regular terminal as well. So you don't even really need terminal software to use it as a terminal connecting into a BBS.
Okay, thank you. Can you connect the Sol20 to the internet?
Actually, yes, you can. So this is a common question we get a lot with vintage computers. Can you connect your vintage computer to the internet? There's a really easy answer besides just yes. It's called buy a serial to IP conversion box. They do have them. There are some surplus ones for companies that were using them for terminals and things, as well as you can buy some guys out there have made them specifically for the vintage computer community. For a while, I actually had my Altair on the internet, and people could dial in and play games on my Altair. I used to have Star Trek running, but it sounds like a jet drive, so I kind of shut it off and stopped doing that just for the noise in my office.
Okay, thank you. The next question is, are there any pictures of the internal of the drive?
I realized that after I looked at the video that I did not have internal pictures. So yeah, I do have tons of internal pictures from the restoration process. I will provide those to Eric so he can put them on something, or maybe we can attach it to you know, something on the stream or whatever. But yeah, there's a lot of pictures during the restoration. You know, this as I said was a ground up restoration. So there's pictures of it being brought down to bare metal. There's pictures of the actual internals of the drive being completely assembled, disassembled, as well as you know, pictures of the glass mirror and things. So I'll try and get some of those pictures to Eric, and we'll try and get them on our website or on the stream or something, you know, within the next few days. It is a really interesting. And by the way, most of that case is empty. I think Processor Tech thought at one point they would come out with a 4-disk drive, which is really just 2 drives, but they never really did that. They just only had the one single double drive.
Okay, thank you, Corey. Eric, do we have time for more questions?
Eric, you're not live on the your voice is not live on the YouTube.
Okay, so Eric's voice isn't live on the YouTube right now?
No,
Okay,
I should have been on the
fix
YouTube.
that.
I'm just, I would have been on delay because I had turned off my my Meets mic. Apologies. So we have time for one more quick question, and we can then go forward.
Okay, the next question is, have you had any communication with Lee Felsenstein about this Sol20 and Helios system? If so, what did he say about our restoration?
Not specifically about this Sol20. I think when Lee was out here a few years back, he was here at InfoAge at VCFed for a repair shop. He came out and was helping people repair their Sol20s. He helped me on one of my Sol20s. I have a few of them, but not on this specific one. This one was a multi-year project for restoration just because of how long it took to do and put everything together. I mean, even the wood on this particular one was sanded down and refinished using the exact same stain that was specified in the documentation. I was able to find that. So this one took a really long time. So I guess I really should probably send it to him. I think I've sent him a copy of the Helios sales demo or video of it because that's pretty rare. And I think I just kind of found it in a bunch of discs, and it had been provided a copy of that to CHM so that they have it in their archives. I didn't want it to be gone because you know I had the only copy. I think I did the same thing with some other software as well, like Focal and things.
Yeah, if Al's got a copy of it, it's good for life.
Yep.
And speaking of Lee, I've he was at my Maker Faire booth because he was doing an exhibit elsewhere in Maker Faire. He loves talking about the Sol20s, and he also loves taking pens to them. He'll scribble all over them if you ask him to. Those and Osborne's and whatever else.
I'm going to walk over real fast. You mean doing that?
Exactly.
Hopefully the light comes out.
Yeah, it's a little glary, but yeah, he actually writes notes on them to people. I know. Yep. I did one with him for one of our Italia friends before I sent it out to them. Anyway, it is 9:30 on the spot, so believe it or not, we've got another Sol20 to talk about. So I am going to start Francis Bauer's video to talk about his also fully functional amazing machine.
Hello, my name is Francis Bauer. I live here in Northern California. I've been having fun with computers since the mid-1970s. While attending junior college working towards my AS degree in electronics technology, I was introduced to the Sol20 terminal computer processor technology from a fellow classmate. The following slides and video clips show my processor technology Sol20 in operation, as well as giving some information about processor technology as a company. Enjoy the video. This presentation contains a number of slides and video clips showing my Sol20 hardware and software in operation. The first part of this slideshow moves quickly to fit more in later on. In 1977, this was the processor technology product family. The Sol20 is based upon the Intel 8080A 8-bit microprocessor. This thick binder contains all the assembly instructions and schematics. This custom denim cover keeps the Sol20 clean. The back panel of the Sol20 shows the various I/O ports available: cassette, serial, and parallel. Here is the Sol20 with its two covers removed. After 40 plus years, the Keytronics keyboard needed some attention. The foam pads on each key disintegrated, which kept the keys from being seen when pressed. Fortunately, replacement keypads are available and easily changed. There are some videos and instructions online describing the process. Most Sol20s shipped with this version of the 8080A microprocessor. The Sols have a 5-slot S100 bus card cage. Currently I have these 3 boards installed. Here is the rear view of the Sol20 motherboard, and it shows the EEPROM personality board installed. The Sols have a number of available personalities, each with different capabilities. The most popular of these was the Solos version. I initially had a 9-inch Sanyo black and white composite monitor for use with the Sol20. Here's a side-by-side comparison showing the effect of different display, set S equals N, output speeds when executing the same RAM dump command. The set display speed command can be set from 0, the fastest, to FF, the slowest. You are seeing the difference between a setting of 0 and a setting of 5. As you can imagine, a setting of FF would be very slow. Back in 1983, I purchased a larger monitor for the Sol20. This 12-inch Zenith green phosphor CRT was a nice change from the 9-inch black and white Sanyo CRT. DPMon is a third-party personality module from Microcomplex that adds a number of useful commands not found in Solos. The caveat is that all the cassette commands and support has been removed. Here's one of the newer DPMon commands that display RAM contents as ASCII characters. I previously used the new Enter ASCII Character command to load the ASCII characters into RAM. I used the Set S Display Speed Control command to have the characters displayed slower. Here's an example of using the DPMon RAM Fill Memory command and the Dump RAM Memory as Hex Values command. The DPMon DH Dump RAM Memory as Hex command is equivalent to the Solos DU Dump command. As with all the dump commands, pressing the spacebar will pause the display. Here's an example of using the dpmon RAM test memory command to test all the RAM between 0000 to BFFF 5 times. Any found memory errors will be displayed with the appropriate error code. The first test memory pass is in real time. The following ones have been sped up to shorten this video. Here's an example of using the find character command to find a specific ASCII character in the specified RAM address range. There is also a find hex value command as well. For this example, I start out by filling all the RAM with zeros. I then enter two ASCII characters at address 1000 and 1001 using the EA command. I then use the FC find character command to find the ASCII character F. Command finds F at address 1000. I then use the FC find character command to find the ASCII character B. The command finds B at address 1001. This is a useful S100 board that is helpful in debugging programs and hardware and was created around 2007 by a Sol20 enthusiast. This board essentially gives you the front panel abilities similar to the Altair and IMSI microcomputers and gives you single-step and breakpoint address and program control. In this demonstration, the System Bus Probe board is configured with a breakpoint address of 0. A simple RAM fill program is installed and executed at address 0. Program execution stops immediately at address 0, so then you can use the single-step button to execute each instruction while monitoring the LEDs. Eventually, the Run button is pressed to allow the program to complete and return control back to Solos. Following slides and video clips show my collection of Sol20 software. I purchased the 16K BASIC language for the Sol20 and found it to be a very nice and powerful version of BASIC. After loading the extended cassette 16K BASIC software into the Sol20, you do EX0 to start it. Initially, the user is asked a few configuration questions that specify the upper RAM limit and whether or not the matrix math functions are removed to free up more memory. The free 0 basic function determines that there is 32,704 bytes of memory available for basic programs and data. To load a basic program, I used the set IP equals 1 command and then started a serial data transfer to load the program. After the program is loaded, type run to start it. Processor Technology created a great 8080 program development environment called ALS8. Processor Technology 8080 Assembler. Processor Technology created a small 5K version of BASIC. Focal was popular on PDP-8 mini-computers. Processor Technology's version of chess. Processor Technology's first game pack. One of the most popular games for the Sol20 is in Game Pack 1. This video clip shows the starting and playing of the target game and having it run in demo mode. The target game's objective is to shoot down runaway spaceships. You can, of course, play the game yourself by pressing a number from 1 to 9. The game claims to have sound effects. You need to tune an external AM radio and place it next to the Sol20. The game sounds are there, but they are certainly not that impressive. One of the tricks in playing target is that you can move the just-fired projectile while it is still in flight by moving the cannon. This allows you to zero in on a spaceship. Even in demo mode, you can press keys and play along. This usually helps in getting a better score, since the demo mode is just randomly firing and positioning the cannon. Processor Technology's second game pack. Processor Technology's version of a Star Trek game. A third-party version of BASIC. This is an example of a generic data cassette. With the appropriate floppy drive hardware, you can run CPM 2.2. If you want to experience working with a Sol and you don't have any Sol hardware, get the Solus emulator. Thank you for viewing my presentation. Stay healthy, stay safe.
Oops. All right. I think that's what I wanted. There we go. All right. I know that we've got at least one question lined up for Mr. Bauer here. Again, microphone at vcfed.org if you have questions.
All right.
Got about 5
Ready,
minutes.
Eric?
Go ahead.
All right. So the first question is, they're asking about emulators. Are there emulators available for the Sol20?
It turns out, yes, there is. There's a very good emulator. I have it listed on one of the slides in my presentation that works very well and running on your PC. And it pretty much lets you run all kinds of things, including CPM and various other applications.
And by the way, speaking of slides, I apologize for interrupting, but the additional materials for a lot of these presentations will be attached to either the individual videos that we've posted of all of these, or we'll come up with something on the VCFed site that we'll have for augmenting either links or slide presentations or whatever else we've got. Jeff, are there other questions, or Dag?
Yes, there is another question. One person is asking about this VDM. He's not sure about the name, VDM1 direct memory card for the Sol. First of all, is he remembering it correctly? And how many Sols had direct memory cards?
Pretty much all the Sols have VDM built in on the motherboard, but you could get the VDM as a separate product, as a separate S100 board to put into your other S100 based systems. The VDM board came out earlier than the Sol, so that was one of their earlier products, but then they designed it onto the motherboard of the Sol itself.
I had a question about the software just because I've got a couple of Sols here and don't have all of the stuff. I've got a couple, I think, of the game packs and some others, but Corey had talked about in the previous video of archiving off some of the software that he had. Have you done, basically recordings of those tapes, created WAV files of those tapes so that others could use them, or have you, in other ways, archived off any of that software to share?
Well, I have done some of that for myself for sure, but some of that's already been done and it is all online. If you go to the sol20.org site and various other sites, a lot of that's already out there on the internet.
All right. And one of my favorite stories about the Sol20, are you familiar with the reason for the wooden sides?
I think I remember the story, but go ahead.
No, I want you to tell it. This is your presentation.
Well, I don't know if I remember it well enough to tell it.
Go ahead. No? All right. Well, my understanding of the story, and I think I heard this from Lee himself, was that when he was first working on the machine, he was in a storage area or warehouse or whatever that had some old wood from another project, and he just felt the need to repurpose it, either for environmental or for aesthetic reasons or both. But I just think it's funny that you don't see a lot of wooden computers anymore, and between the North Star and the Sol20, it was maybe not common, but at least not unheard of back in the 70s to have something like that, which I find kind of unusual.
Well, it makes them a little more classy. It's like furniture back when radios were coming into being. They were pieces of furniture in your house. Yep. So why not early computers being a piece of furniture in your house?
Yeah, the big TV consoles, the 400-pound with the record player and everything in them were all wood and all handcrafted. Dagger, Jeff, were there any more questions?
Yes, Eric. The next question is, how much data can fit on a cassette versus how much can fit on an 8-inch floppy disk?
That's a good question. You can pack quite a bit on the cassettes. They were doing, you can either do 1200 baud or 300 baud storage for a Sol. So you can pack quite a bit on there. I don't have the exact numbers in front of me, but I'm sure we can look that up and then add that information later. I would suspect, it's probably possible to put more on the cassette than there was on the earlier floppies at this point, I think.
Yeah, if you had a 60-minute cassette, I could see that happening course, access times would be horrible.
Do we have time for another question?
Yeah, we got time for a quick one.
All right. Someone asked, does the Sol20 work with the MAME emulator?
With MAME?
Oh, MAME. You're talking about
MAME. So it's an emulator that a lot of people use for emulating different computers, mostly video games, and that they're asking, is there a Sol20 emulator for the MAME?
I'm not sure if there's one specifically for MAME, but there is a standalone emulator for the Sol20 that you don't even need to use MAME for at all. And that's on one of the slides that I have in my presentation on how you can download that. It's a very small emulator. It works very well. So you don't really need to even use MAME in order to get a Sol emulation.
All right. Very cool. All right. It's 9:45. Time to start Carl Clonch's video. And I got to say, Carl's got an Apollo Disky that he's got working. And the working part is impressive enough, but just having a Disky is, in my mind, insane. I'm going to let Carl talk about this.
Hi, I'm Carl Clonch, and this is my project to light up an Apollo Disky panel. This project is intended to take the display unit from an actual Apollo Disky and animate it so that we can see the digits displaying on it. I have in my hand a late model version. In fact, it's a spare that would have been put into spacecraft. It's got a 160 pin set of connectors here. The segments are activated by 275 volt, 800 hertz AC. And to generate that, there is a power supply module, which I have wired up here. And then that high voltage AC goes through relay modules. The relay modules are switching the high voltage to the individual segments that form all of the digits. There's 21 numeric digits with 7 segments, plus 3 signs and some other features on the display. Now, the power supply I have and the relays are from the earlier design called Block 1 of Apollo. But they had significantly redesigned the Apollo equipment, and before any people flew in it, they were on to Block 2. So the modules here, the displays are from Block 2, but unfortunately the relays and the power supply are Block 1. Fortunately, they're compatible enough, same voltages and all. This older version is got the same elements on it as the later Block 2. It's still Block 2, but it's the very first specification or version of it. It has a slightly different wavelength of the light, and so it's a more bluer green. So I'll turn it on now and you can see the coloring of this. See, it's a more blue-green than we're accustomed to see on Apollo spacecraft. Now, the way I'm activating it is by driving voltages into the power supply module. It takes both 14 and 28 volts and an 800 hertz input signal. That's a square wave coming from the computer. So basically the square wave goes through this driver circuit. I'm generating it from a square wave generator, and that makes this power supply module produce the 275 volt AC that is needed for the rest of it. To activate the relay module, you need to drive 14 volts into it. One set of lines selects a row of 5 digits that go across the relay module, and then the other lines either latch or unlatch the relay for each column. There are 5 columns. Those hold a 5-bit code. The 5-bit code is switched through those relays to produce the 7 segments that light up the system, 5 bits being enough to generate 1 of 10 unique digits. So the relay module has 137 connections that go into it. Some of them are the segments, the high voltage that goes in and is switched out, and others are the low voltage, the 14 volts that drives latching or unlatching the relays. To drive the 14 volts from an Arduino I have this board with transistor driver circuits that are converting the voltages so it can either feed 14 volts or pull the other side to ground to activate the different relay coils. So I wrote a little simple command-based script in Arduino where I can set codes and it'll latch and unlatch the appropriate relays so that we display the digits we want. So I'm going to put a value into the program area of 88. Listen, that were the little digits going. As we can see, the values 88, 55, and minus are in there just as I had set it up. You can see the bag of individual connectors here. They're a small piece of nylon. They have a long gold tail that you can do wire wrap on. And the other end are a pair of pins that grip. This is the female side of the connector that grips around a little prong that exists, which is the male side. Okay, now we can see I've swapped in the newer version, the version that would have been just like the ones flying on the spacecraft. We have a nice brighter display, and even more importantly, we have the correct Apollo coloring for it. The more shifted green toward yellowish green rather than the blue-green of the original one. Let's put some numbers in it now. Beautiful looking. Turn off the sign. That's what we hope to see from an Apollo DSKY display. I have since wired up 2 relay modules, and I can now animate the first row of 5 digits after the plus sign, as well as the ones I had previously shown.
All right. Let me give Carl the screen here. Nice T-shirt.
Hi.
Dagger Jeff, do we have questions inbound?
Right now, we don't have any questions. Hold on, maybe we got one. Hold on a second. Oh, so someone wants to know, can you connect it to a BBS?
Well, unfortunately, these modules are just on loan to me from a collector who owns them. So now that I've animated the display, they're going to go back to their rightful owner, and they won't be available any longer.
That actually segues into a question that I had. How in the heck do you get your hands on stuff like this? I know that at last year's VCF there was a full Apollo setup, the full computer and DSKY that was going on auction. I don't know what that ended up closing at, but I can't imagine it was under 7 figures. But where do these things even come from?
So it turns out that because of my sort of demonstrated lunacy focusing on Apollo era hardware, I've met similarly obsessed people, a number of whom are collectors who have the means to pay these huge prices and own these precious artifacts. And they've all been quite eager to see these restored and see them in operation the way they had worked 5 decades ago, and it's already up to 3 different collectors who are sharing things with myself, Ken Sheriff, and Mark Verdeal, and Mike Stewart.
Yeah, that's. I would guess that there'd be a pretty good specialty community for that kind of stuff, but it's very cool equipment. Somebody actually in this chat had a question. I'm going to let you ask.
Is somebody going to read it to me? I don't see it.
So Niles had a question about did he hear 270 volts, and why such a high voltage?
Well, the display technology, remember this was developed back in the early 1960s, so no LEDs. So the only way you could keep power consumption to a minimum, which was really essential to get a spacecraft, to spend 14 to 20 something days traveling with limited resources, was to use electroluminescent technology. So that has a pair of plates like a capacitor, and it needs a really high voltage AC excitation to cause the phosphors to.
Right now, we don't have any questions. Hold on, maybe we got one. Hold on a second.
Sorry, Carl.
Oh, so someone wants to know, can you connect it to a BBS?
Didn't you already ask that?
Yeah. Well, unfortunately, these modules are just on loan to me from a collector who owns them. So now that I've animated the display, they're going to go back to their rightful owner, and then they won't be available any longer.
Uh-oh.
That sounded like a repeat of what we had before.
Somebody probably in our Meets chat is streaming the stream, so it's running a little bit behind. So that was you re-asking a question.
When you're ready for another question.
Yeah, and actually, are there any of the folks that are physically in the museum asking questions as well? I'd love to hear some of them.
Yeah, church that because of my
whoever's got audio on the stream, please turn that off.
I've met similarly obsessed people.
It is a real machine, or is it a replica?
Okay, so these are all genuine Apollo parts, not a replica. So they're units that had been sold off at the end of the Apollo program, and various people had owned them, and they've been, sold again, and the collector loaned them to me. So this was exactly as it was manufactured in the 1960s, and it sat there and amazingly works perfectly, 50 plus years later.
All right. The next question is, how much does the display, transformer, and relay weigh? It looks really heavy.
Yeah, it is relatively heavy. They did develop switching power supplies back then for aerospace, and so that was used in Apollo. So some weight was saved, but the technology is fairly heavy. I don't know the total for that, but with the Apollo guidance computer, you're talking somewhere in the order of a little under 100 pounds just for the computer and the DSKY, and then imagine all of the fuel cells and instrumentation and everything else needed. Pretty heavy spacecraft, which is why it needed a Saturn V to launch it.
True that.
All right.
There more.
Can we have a question?
Do you have more questions there?
Yes.
Go.
How long can the displays be run?
So the specification on the display is a 2,000 hour lifetime. That was the NASA spec. And it's supposed to dim, fairly linearly over life. The one that I animated was really bright, but it was a new old stock spare. I mean, it was packaged up in the kit with its testing sheets and everything else, which implied to me it had very, very few hours on the meter.
All right. Were there any more questions, Jeff?
No, the others are just more or less comments saying fantastic work, and it's great that you're running it on Arduino. It would be great to see it in person someday.
Yeah, unfortunately, if it hadn't been for current affairs, it would have been in the VCF West physical showroom. So
yeah, hopefully next year we can get that beastie in there. Just as a reminder, we're going to move on to our next presentation in a moment. Questions can be addressed to microphone@vcfed.org. And for those of us that are on the Meets meeting, video chat etiquette is in play. Please mute yourself unless you're speaking. If you're simulcasting the web feed, and that comes across our audio, it's going to get really confusing as it did a moment ago. So just please be aware. Please be cognizant of the fact that we're on a live video chat along with our live stream. And with that said, the next two presentations, in fact, kind of go together. Len Shustak of the Computer History Museum and Guy Fedorko have done amazing work with regards to magnetic tape recovery and specifically tape recovery for the Whirlwind computer. Are either of you guys online at the moment?
I am. This is Len.
What I was hoping to do...
Yes.
Oh, excellent. So what I was hoping to do is basically run both videos back to back, and then let you guys jointly answer questions about both of them for about 15 or 20 minutes afterwards. But I can do it the other way and just run the one video and then the other after questions for the first, if you'd like. Anyone have a preference?
No, back to back is fine with me.
All right.
Fine with me.
That
Thank
sounds good. I personally, I believe that doing it that way is going to generate a whole lot more questions. This is some amazing work. I can't. I've seen this video several times, and I'm still just amazed. So let's start with the tape recovery section. This is Len.
Hello. Welcome to Virtual VCF West. I'm Len Shustak, co-founder of the Computer History Museum, and for 25 years was chairman of the board, but I've recently retired and I am now chairman emeritus, which gives me time to work on other fun projects like the one I'm going to be talking about today. This is about magnetic tape data recovery in software. The museum has thousands of mag tapes, which we'd like to read, and we don't often have the equipment to read them. But my motivation for starting this project was actually much more personal than that. When I was an undergraduate at the Polytechnic Institute of Brooklyn in the late 1960s, I worked on a project to write a PL1 subset compiler called Plago. And it was the project that made me want to transition from being a physics major to being a computer science major. When I left Poly, I took a mag tape with all of the source code on it and kept it with me all of those years. And for 50 years, it's been in the attic. And never having been read and not stored under environmentally friendly conditions, I was suspicious that it was going to be difficult to recover the data. And in fact, it was. I dropped $1,000 on a professional data recovery company who promised to do their best job to recover the bits, and they basically failed. The red question marks on this printout below shows all of the places where there were errors. There were hundreds or thousands of errors in every file, which led me to wonder, is there a better way to try to recover the data than using standard tape drives? The standard tape drive uses a lot of hardware. It starts with the read head, and then there's a preamp and maybe a differential amp and a differentiator and a comparator and a threshold detector and a zero crossing detector and a data bit decoder. And that's just to extract the bits. And then you have to do the block handling and the word assembly and the error handling and all of that. And if anything goes wrong, there's not a lot of knobs you can tweak to make the decoding better. There is a better way, or a different way, and that is software-based. Now, I was inspired by a project I knew that Paul Pierce up in Oregon had done in 2004 with some Java software to do software-based data recovery. You start with the read head, you do the minimal amount of hardware necessary to boost the signal, do an analog to digital conversion, and then do all of the subsequent processing in software. Detect flux transitions, use that to determine the bits, assemble those bits into words and blocks, determine your success, and then try it again if it's not good. And you can tweak all of the parameters for those algorithms so that you can do it over and over again based on the recorded data without ever having to read the tape more than once. That's important because for some of these old tapes, sometimes one read is all you get, and the process of reading it strips the oxide off the tape, and you've lost the opportunity to do it again. So I thought this was a good idea. My first attempt was to build some hardware to do the analog to digital conversion. I found this great chip from a UK company called Wolfson that was subsequently bought by Cirrus Logic. And I put together a prototype board using this chip that does 9 parallel analog to digital conversions at one time. They designed it for CCD recorders. I was very frustrated. That chip has about 400 configurable parameters. I was never able to configure them correctly so that it would work. The engineers at Cirrus Logic were unresponsive, and I basically put the project aside. And then there was a brilliant insight from, I think it was Al Casso, who said, don't build your own hardware. Take a standard tape drive with a standard read head and the standard preamp, and then use a A to D logic analyzer to record the analog signal and digitize it before all of the rest of the electronics in the tape drive. And that's what we did. We took a Qualstar 1052 tape deck, wired in a Scelbi 16-channel logic analyzer. I'm a big fan of Scelbi, by the way. They make fantastic products. And the result is a series of waveforms that look like this. And we can collect anywhere from 6 to 16 tracks, 100 to 10,000 bits per inch. The height of the peaks here, by the way, are irrelevant. This is a particular kind of tape encoding where the only thing that matters is the distance between the peaks, not the height of the peaks. So what data do we want? Well, we'd like to get about 20 to 30 samples per bit to give our software algorithms the maximum amount of flexibility. If you're running the tape past the head at 50 inches per second, and it's an 800 BPI tape, and you want 20 samples per bit, that works out to about 800,000 samples per second. That's loafing along for the Scelbi analyzer, so no problem at all reading that data. You've got to move the tape past the head at a reasonable rate. Remember Faraday's law, where the voltage is proportional to the flux change per second. So you need to move it pretty quickly. It produces lots of data, but the Scelbi analyzer actually uses the computer's virtual memory as its storage. So it's essentially unlimited. What it produces for us is basically a spreadsheet, a CSV, comma-separated value text file that contains a timestamp and the voltage level on each of the heads at the time you take the sample. These files can be huge. For several minutes of data, they could be over 50 gigabytes. What we did, and I worked with Al Casso on this as well, is to define a compressed format for the data so that we could more easily process them and store them. It uses 16-bit scaled integers with self-describing headers, and I wrote a utility program that converts to and from the spreadsheet format to this compressed format. The result is about a 10-to-1 space compression, and it's processed about 2 times faster. Well, then you've got to process all the data. So I did what I love to do, which is write lots of C. It's at this point about 7,000 lines of C code. It's all up on my GitHub repository with the address at the bottom of the screen. So if you're interested in looking at it or using it, feel free to take a look at that. It's the kind of code I love to write. There's no graphical user interface. It's a command line interface with lots and lots of parameters to control the decoding. One of the things it does is allow you to specify a set of parameters to decode each block. And if the decoding is not correct, it can choose an alternate set of parameters. And it can try parameter blocks over and over again until it gets the best possible decoding. This is an example of a set of parameter blocks for phase encoded waveforms, where you get to control the clocking windows and decay times, and the peak detection parameters, and pulse adjustment, because pulses tend to move depending on the sequence of bits, and so forth. Lots of parameters that are dependent on the kind of bits that we're decoding. So the overall data flow is the Soleil logic analyzer produces a CSV file. We convert that to our compressed binary format called tbin, and then decode. And the result of the decoding is, for one thing, a binary file that contains the raw data we've decoded. We also create a .tap format, which is Bob Subnick's SimH simulator format for tapes that can drive simulators for a variety of machines. A log file that tells us how the decoding went and what problems were discovered. A text file where we can decode the binary data into interpretable text based on a number of different decoding formats, ASCII and BCD and all of the rest. And then we create our own CSV file, spreadsheet file for debugging information. And here's an example of the debugging information. It's a reconstruction of the analog signals we saw. Here with the little bips showing where we detected peaks and valleys in the data, and some information about how we reconstructed the data flow. This can be very handy when you come up with a tape that has a difficult to decode set of bits. So there are several things we have to do. First is obviously detect the transitions, the flux transitions on the tape. There are two options for doing that. One is a moving window peak detector that looks for the peaks of the signal. You can specify the width and the required peak rise. And depending on where you're tapping into the electronics of the tape drive, you may prefer to look at the differentiated version of that and look at zero crossing rather than peaks. And there you can specify things like the height of the peak before it becomes considered to be a valid data bit. So once you've detected the peaks, you need to create the bits, and there are lots of different ways to do that. One of the earliest ones is NRZI, non-return to zero inverted, where a 1 bit is a transition in the middle of a hypothetical bit period, and a 0 bit is no transition in that bit period. This was used for almost all 7-track tapes, for 800 BPI 9-track tapes, for Whirlwind tapes. One of its problems is that it's not self-clocking. Notice that if there's a continuous series of 0 bits, there are no transitions. So either you have to be perfectly aligned with the bit clock as it was originally written, which of course is impossible, or you have to somehow otherwise reconstruct the clock. And the traditional way of doing that is requiring that the bits have odd, the characters on the tape have odd parity, so that you're guaranteed that at least 1 bit has a single bit transition in the middle of the bit period, and you can use that to realign your bit clock. A way to solve that problem is to use phase encoding. This is what was used for 9-track 1600 BPI drives, which is self-clocking. There's a bit transition for every bit, in one direction for a 0 bit or another direction for a 1 bit. And then there's a transition at the bit boundary as needed to prepare for the appropriate bit transition at the middle of the bit. All of these formats are different. They all have different kinds of error correction. They have different conventions for file marks. For example, in phase encoding, file mark, which is a non-data block that represents the division between sections of the tape, is a whole bunch of flux reversals on tape 2, 5, and 8 only, and silence on all the rest of the tapes. These are completely arbitrary definitions, and decoding for these are all built into the program. The most complicated format we've done is group-coded recording, GCR, which was kind of the last gasp of 9-track half-inch tape drives that generated 6250 BPI data bits per inch based on actually 9,042 bits per inch of data stored on the tape. They used NRZI, but they encoded every 4 bits into 5 bits on the tape to guarantee that there are periodic 1-bit transitions so you could do clock recovery. Incredibly complicated, lots of fun to write the code to decode that. There are several other problems we have to deal with. One is head skew. When the tape was either read or written, the tape might not have been perfectly perpendicular to the movement of the tape, which means that bits come in at different times depending on which track they're in. This is an example of a tape with a 200 microsecond nominal transition between bits, but the bits can be as early as 183 microseconds and as late as 250 microseconds. That creates havoc with the decoding, especially for the non-self-clocking formats. So one of the things I do is to pre-read 1,000 transitions on the tape. I determine what the head skew is, and then insert delays in the early arriving tracks so that all of the track data arrives at the decoder at the same time. So this is before the deskewing and this is after the deskewing. Another problem to deal with is amplitude changes. As the tape is read, or maybe as it was written, the amplitude varies, and if you're doing especially peak detection, that can cause a problem. So we implement automatic gain control that's either based on average of the last few peaks or an exponential weighted average of the previous peaks. And again, these are things that you can control in the parameter sets that you provide to the program. Speed changes are another thing that needs to be done because either when read or when written, the bit rate can vary from nominal. So as we see the bits coming in, we update the speed based on the recent history. Again, based on average spacing of the last few bits or an exponential weighted spacing. Once you've got a good fix on the bits, you can try to produce, correct errors. There are several ways of doing that. One is you can deduce the bits that might be bad from parity. You can correct the bits if the format has error correcting codes or longitudinal check words. A surprisingly good technique that seems to work often is to fake during a dropout on the tape that the bits you are missing were the same bits as before. There are a surprising number of 0 bits on lots of these tapes. So this is an example of a tape that we were successfully able to recover the data from, even though there are some serious dropouts in various tracks. So how does it do? Well, I'm happy to report that on my Play-Go tape, 100% of all the files were recovered. And I was able to read the 360 assembly language code that I wrote 50 years ago, and of course don't recognize a bit of. As you know, the half-life for remembering what code you've written is about 6 months, and after 50 years, you remember none of it. But it was successful, and we have since applied that to many other tapes in the Computer Museum's collection. We have lots of tapes from Doug Engelbart's NLS project over at SRI, other tapes from the SRI PDP-10, Microdata Reality Operating System, Lawrence Berkeley Lab tapes, Project Genie at UC Berkeley, tapes from BB&N, and so forth. We've made a good start at decoding the tapes in the archive of the museum, but there are lots more to be done. At a higher level, why are we doing this? For me, it was mostly nostalgia to look at the code I'd written 50 years ago. But there are more important reasons as well. We can really use this to recover lost knowledge about early computers and early software and operating systems and application programs. These are techniques that you can use for all sorts of digital archaeology of trying to understand from our digital past what was done in the early days. It also provides authentic programs written in the day for restorations and simulations so that we can have a better idea of the simulated machines and what they were used for. Here's an example. Whirlwind. Whirlwind was in some ways the machine that inspired the creation of the Computer History Museum, or actually its predecessor organization, the Computer Museum in Boston. Gordon Bell had written a book with Alan Newell called Computer Structures, where he talked about many of the pioneer computers, and one of them was Whirlwind. And when he got wind of the fact that MIT was basically throwing out Whirlwind, he went to the Smithsonian and said, "You've got to preserve this. This is an international treasure." And the Smithsonian said, "Thanks, but no thanks. We don't collect computers." Well, that was Gordon's inspiration for starting the Computer Museum in Boston, which in the late 1990s became the Computer History Museum here in Mountain View. Well, along with Whirlwind, which we now have in Mountain View, or at least large parts of it, there were about 150 tapes, mag tapes, that had been created on that machine, 6-track tapes, none of which had been read since the machine was in use. So we decided to try to apply this software-based decoding technique to the Whirlwind tapes. Now, these were 6-track tapes, and we don't have 6-track heads. Al Caso, I think again it was, who had the brilliant suggestion of not bothering to try to create or find a 6-track tape, but just read it on a standard 9-track tape. If you look at the geometry, the 6-track tape tracks are 50 mils wide. If you map those to the closest 9-track head and a standard drive, it's only about 14 mils apart. And guess what? You get perfectly adequate signals. Yes, the 3 heads that are in between tracks produce junk, but that doesn't matter. The 6 tracks that are important produce perfectly readable data. And then we need to read the data. Whirlwind is basically a NERSI format. It has no parity or other checks, but each track is duplicated 2 times, and there's a clock track, which is also duplicated. So for each character on the tape, only 2 bits of data is encoded, which allows us to recover from a lot of the dropouts and errors that we knew we would be finding on the tape. It, of course, has its own bizarre format for a tape mark. In this case, it is transitions on both copies of the least significant bit and no transitions on any of the other tracks. So, armed with this decoding that we put into the software, we started a data flow, which had Al Caso reading the tapes using the Qualstar tape drive and the Soleil logic analyzer to produce the waves, basically the analog information in digital format. I converted those waves into bits and then data blocks. And then Guy Fedorko took that data and is converting it into programs and data information to drive his simulator of the Whirlwind. The results so far are that we have decoded about half the inventory, about 81 tapes, 162,000 data blocks, only 0.13% of them had errors that we were not able to recover. So we've recovered about 10 megabytes of original Whirlwind data. There is both data and source code in there. I was hoping to see text, early email, some kinds of, the beginnings of the great American novel. But unfortunately, there is a little bit of text, but very little. As Guy points out, the data was so limited that people would not waste it on storing text. But it's been a successful project. It's been lots of fun. This is actually a lead up to Guy talking about what he did with those recovered data in driving his simulator of the Whirlwind. And I hope you stay tuned for his talk as well. It's a little bit unsatisfying doing this without any mechanism for feedback. So if you have questions, feel free to email me. And I hope perhaps next year we'll have an opportunity to do this in person. Thank you.
And of course, we will do live chat questions in a little bit, but let's go straight into Guy's presentation.
Greetings, VCF West. My name is Guy Fedorko. I'm sorry I can't be there in person today, as I'm sure we all are. But I'd like to talk a little bit today about what we've been doing to recover software work from a machine called Whirlwind, developed in the 50s, about 60 years ago, at MIT. This work has been done with help from both Computer History Museum and the MIT Museum. At CHM, of course, I'm indebted to Len Shustic and Dag Spicer and David Brock, as well as Al Cosso. And at MIT, I've been working with Debbie Douglas, and oh, Debbie, a debt of gratitude. As I said, this is about a machine called Whirlwind. We set about this project to try and recover some of the software from the machine that was designed, first run in 1949, early 1950. So what is this machine, Whirlwind? It's a one-of-a-kind vacuum tube computer. First came into operation in 1949 and was available for research use at MIT starting in about 1951, running through the end of the decade. The project began under a contract from the Navy. Their initial problem was to design a real-time flight simulator, and they decided that a computer was just the thing they needed to do that, as opposed to using a digital computer, as opposed to using analog computers as would normally have been done. The machine evolved to take on roles in air traffic control as well as air defense work, as we'll see. It was designed as a 16-bit parallel architecture with 2,000 words of address space. It was capable of about 50,000 ads per second, which in the context was pretty darn quick. The program is remembered, even though it was not commercialized directly as Whirlwind. The program is remembered for developing magnetic core memory. Many were working on it, but it was the Whirlwind team who's usually credited with getting core memory, as they say, reduced to practice and reliable and practical. The project was a research project and was continually evolving. By 1952, many of the staff members had moved from the original Whirlwind development on to an Air Force funded contract, which ultimately became SAGE, Semi-Automated Ground Environment Air Defense Network. But while the machine was at MIT, there were many other applications that ran on the machine, many in the broad field of applied mathematics. The machine ran for about a decade and was decommissioned in the spring of 1959. There's a photograph of the well-known photograph of the control room for Whirlwind. I always like to think of this as a computer out of the central casting for a science fiction movie. It was wires and racks and cables and all kinds of stuff bolted together to try and get a machine that would work. You can see in the lower right hand of the slide an artist's sketch, including some of the machine room, including 5 rows of racks full of equipment to implement this one 16-bit computer. The block diagram for the machine in modern days looks surprisingly conventional. It was a von Neumann architecture, even though Mr. von Neumann had only published his first draft in June of 1945. The machine used what you might think of as a simple load store architecture. It was centered around an accumulator and core memory with a few other registers for the usual things, program counters, IO register, The ALU was a 16-bit ALU, but a second 16-bit register attached to it for overflow and underflow from operations like multiply and shift. The machine was large in terms of square feet and power. It was about 100 kilowatts of stuff. The computer room itself was 2,500 square feet, with more stuff on the floor below this for drum storage and more stuff in the basement for power supplies. The machine actually maps to its block diagram pretty clearly on the floor plan. You can see there are 16 racks there labeled A0 through A15. Those are the accumulator, the ALU basically accumulator, A and B registers, program counter. Racks E0 through E15 are memory, and they started with electrostatic storage tube memory. And then there's another row of 16 racks which contain other flip-flop storage and comparison registers and a few other odds and ends. I always like to think of the comparison of Whirlwind to other machines. Of course, comparison with a modern machine, it is roughly equivalent to a rather slow Arduino. Approximately 2 kilowords of storage. The mass storage was about 24K words for Whirlwind, and of course you don't get that much space inside an Arduino. Arduino is a lot faster though, 2 million or so operations per second. The cost was a little different. If you compare the cost per ed per second, of course it's about 1 million times less expensive to run an Arduino. But an interesting comparison is also made against the computing environment at the time. In the late 1940s, the biggest computing enterprise in the world was a thing called the Math Tables Project run by the US government, which at its peak had about 450 human calculators who would use pencil and paper or adding machines to carry out computations for mathematical tables, logarithmic tables, and so on. The Math Tables Project cost about $500,000 a year in 1940, which made Whirlwind definitely better, but not by the number of orders of magnitude that you might expect. So the Whirlwind designers were doing it partly because they wanted real time, partly because they were visionary and saw what could be done with the technology. So what's this Whirlwind recovery pilot project? The MIT Museum has many Whirlwind documents. There are hundreds of reports, training manuals, engineering drawings, notebooks. At the same time, CHM has in its archive hundreds of paper tapes and about 100 magnetic tapes. Both of the museums have some physical artifacts, although the bulk of the machine was destroyed around 1970 at the end of its useful life, somewhat past the end of its useful life. So the question, of course, we asked was, could we combine all of these resources and learn something about the early evolution of software development? And in the process, can we somehow make the material accessible to non-specialists who don't want to wade through 2,000 documents of scanned Whirlwind reports? So how did programmers program in 1950? At the beginning of the Whirlwind program, it was a completely manual process. Programmers would write out the code on sheets of paper, transcribe it onto coding sheets. They manually assigned instructions and data locations. Typists would type the program into paper tape, and using a checker machine to type it a second time and catch the errors. If you were a Navy or Air Force programmer, you got to work in the daytime, but anyone else, you get the night shift. So you get some unpleasant time to come in the morning, early or middle of the night, to run your program on the machine. Of course, you run it, it crashes, you panic, you make a patch tape, try to make a patch tape to fix the error, and then repeat until you get kicked out of the machine room for the next job. They rapidly discovered that this programming stuff was actually kind of difficult, and that it was actually worth wasting computer minutes on catching errors and compiling and assembling code. So there was quite a bit of work done on a set of tools that come to be known as the comprehensive system to provide a little bit more friendly environment for creating code to run on this machine. Paper tape was the medium for Whirlwind. They used 7-track tape and a machine called a flexowriter to punch the tape, read the tapes, and print, and later in the program to type commands into the computer. For the most part, it was the machine was operated as one might expect from an analog computer background, was operated by buttons and switches and knobs and lights, but eventually developed something that was kind of like an operating system. So what about recovering this media? We've started on recovering most of the material that's in the archive. Al Cosso has read almost 800 paper tapes using a modern paper tape reader, and Al and Len together have been working on recovering magnetic tapes. Of those, we've read about 60 of the 100 magnetic tapes. That has resulted in hundreds of potential executable programs for Whirlwind. Many are diagnostics and utilities. A number of them are demo programs. We have not yet found much by way of air defense, but may not be too surprising since it was probably classified at the time. Documentation for software was not kind of the thing that was done. So matching up project reports and memos with binary object is still hit or miss. We found a few cases where there's a program which is accurately described in a memo, and we have not yet found the one index that ruled the tape department. I know there was one. They were very careful about numbering tapes, but we have not yet found that index. So a lot of it is still guesswork to figure out what these things are. So I mentioned the project produced quite a few documents. We have found the librarian's document catalog, that is the listing of all of the documents produced by the Whirlwind project, and it runs to some 8,000 titles over the 10-year period of the program. Some years ago, MITRE scanned about 1,800 of these documents, which are available at MIT, and BitSavers carries about 280 of the documents, some of which overlap the MIT collection and some of which are different. There's also some documents at the Smithsonian, and MITRE still has thousands of photos from the Whirlwind project. So how do you recover this stuff? I think the tool chain is not too surprising. You start on the left-hand side with an image of the tape, either magnetic tape or paper tape. There is a decoder which has been quite problematic and challenging because the tape formats changed a lot. But there's a decoder which reads the tape and reassembles it in what would have been the memory format that it would land in Whirlwind memory to run. I can then disassemble that to see what the code looks like, add comments and labels, reassemble it, and run it in the simulator. So one can then form a loop of run a simulator, see what it does, figure it out a little bit, add a few labels, reassemble it, figure out the next step. So what have we recovered so far? There's quite a few bits and pieces. One of the famous demos for Whirlwind is a simple program that ran on the machine and displayed on an oscilloscope on the large radar display oscilloscope that they used, simply to calculate the dynamic path of a bouncing ball. This program actually was unique in its own way at the time, because it was actually solving these equations in real time right there in front of you. You could see the output of the program as it was drawn on the oscilloscope. And it solved the thing at about the same speed that you'd expect an ordinary ball to bounce. We have recovered a parlor trick. There was a tape labeled Jingle Bells, which in fact is the source, or was the program which produced the scrap of music that was played in at the end of the Edward R. Murrow interview of Jay Forrester in the Whirlwind lab. You can find that still online on a video. The program was called See It Now, and was aired December 1951. There's a game of blackjack. We'll see the screen for that on the next slide, I think. This one, as far as I can tell, was a completely unofficial piece of work. We've found no documentation at all, but it runs well enough to play a credible game of blackjack. A couple other programs which are puzzling. There are a number of test programs, and sometimes it's not obvious what they're testing. There's a thing called Pad Game, which runs perfectly well, and I have no idea what they wrote it for. There are a variety of test programs. There are quite a few more diagnostics that we hope to get running to, if nothing else, to shake out the bugs in the simulation. I'm working on a polynomial solver. Again, that was one that ran in some of the videos of Whirlwind in its early days. And another program used to impress dignitaries by calculating dates on calendars. This is the screen from the blackjack program. You can see the display is lean and a little spare. The hardware would draw 7-segment characters on the screen, but with a little creativity, you could turn those into some of those into letters, which, if you know what you're going to read, you can kind of read. So this was actually an interactive game. The Whirlwind developed a thing they called the light gun. We would now call a light pen, and of course is easily emulated with a mouse and a screen. So there are a number of hotspots on the screen. You could hit the hotspot to create, to cause the game to move to its next step. Obviously, normally you would hit you would click the hits button or the stands button to advance the game and try to win against the machine. This, I should say thank you to Ken Sharif, who many of you would know, who translated some of the simulator into JavaScript. So if you go to his website with the URL here, you can actually run this game in your web browser and play a game against Whirlwind. And if you find a bug, we'll dig up the phone number for the Whirlwind help desk. You can give that a try. So this work is ongoing. We have recovered a few things. As you've seen, most of the things we've recovered have been relatively straightforward standalone programs. Of course, because we have not yet tried to recover comprehensive system directors tapes or anything that resembles operating system material. And we have not yet tried to recover the language tools. But I think they're there on the tapes and ready to be sought. Of course, we keep fixing simulation bugs. A tool to visualize program flow would be really helpful. We started on that. It needs a lot more work to help us see what's going on inside these mysterious programs. There is material published on air defense, and I'd like to find more work on that, because this really was the trial of the proof of concept for the SAGE program. And SAGE, of course, turned into a very large program of the US Air Force, which really advanced the state of the art in computing. Finally, there are all kinds of interesting people stories in here. The Whirlwind project seeded lots of different startups as Whirlwind team members moved on to other activities. One, of course, well-known case is Ken Olson and Harlan Anderson. Both worked on Whirlwind as young engineers and went on to form Digital Equipment Corporation. And we owe DEC a debt of gratitude for helping, in fact, to save the remnants of Whirlwind that we have now. Finally, here are a few websites and resources if you're interested in looking into any of this further. BitSavers and the MIT Dome system have many of the documents. Al has posted many of the tape images on BitSavers, and my simulator work is published on GitHub. So if anyone is interested, drop us a note. And with that, I would like to say thank you very much and switch back to the rest of the VCF program. Thanks everyone for listening.
Excellent. That's got to be about as geeky as we're going to get today. Actually, I think we probably outdo that later. But still pretty amazing. I know we've got a bunch of questions queued up. We've got about 13 minutes for them. Jeff, it's you, right?
Yeah, I'm ready. All right. First question is, how can you know that the read tape decoding is correct?
Well, in the case of certain formats, there are check words like CRCs and LRCs and parity bits, and you can see if those are correct. In formats like GCR, the 6250 BPI tape, there's a very complicated series of not only check words and check bits, but also error correcting codes that you can use to correct errors that you find. Sometimes it's hard. In the case of Whirlwind, there are duplicated tracks. So if you get the same answer on both tracks, then you feel confident that the answers are right. If one of the tracks has a dropout, then you're not sure if what you're decoding on the other track is right. And, you know, I feed it to Guy in his simulator, and he tells me whether it looks like it's decent or not.
The Whirlwind guys were a little short on error checking on these tapes. The loader format does include a simple checksum. It took us months to figure out even how to get the checksum to work, but that does now work. So if it is covered by a checksum and the checksum is good, then it's pretty confident that the tape is okay. There are, I have seen tapes where it's actually ambiguous as to whether it's a tape full of, let's say, ASCII characters, I mean characters, text, not ASCII, or whether it's a binary tape. So often it's just take a look and see. Fortunately, the ones that do seem to have been recovered both from paper tape and from mag tape, either you can read it or you can't. Most of them, when you, if you can decode it at all, then it generally has been pretty reliable.
All right, thank you. All right, the next question is, are you confident enough to discard your original sample data, or do you keep it around just in case?
If you mean the original tapes, we are, of course, keeping the tapes. They're not being discarded. We don't know whether the process of reading them once has degraded them, because sometimes the oxide comes off as you read it. But we're preserving the physical tapes. We're also preserving the files that represent the analog information on the tape that we recorded with the logic analyzer. So yes, we're saving everything along the path. So if we come up in the future with a better way of decoding, we'll be able to apply that to the information we saved.
Excellent. I'm sure, you know, and if people are recovering, for example, hard drives, they always want to save it just in case they miss something. All right, the next question is, why design a custom binary format for what is essentially PCM data instead of reusing existing container formats, for example, WAV files, which does support passing any required metadata as well?
I probably should have looked at using something like WAV files, but I didn't. Al and I just decided to define our own format, and you know, it's well documented. So if it's equivalent to something like a WAV file, we could easily make a converter. But doing something special purpose always gives you the opportunity to be more efficient and get greater compression, because you're not trying to be very general purpose. And that's what we did.
All right, yeah, it's understandable. Next question, have you considered using machine learning for decoding parameter tweaking?
I haven't. In some sense, there is a little bit of machine learning built into it, in the sense that you can give it multiple sets of parameters and it will automatically go through those sets and find the one that is generating the best decode. But there's probably a lot more to be gained by doing even more intelligence, if you will, by you know, machine learning, and I haven't done that.
All right. Next question. I think this was answered already in your video, but I'll ask it. How does a 9-track head read a 7-track tape?
Well, it turns out that 7 of those 9 heads are awfully close to the 6-track tapes. If you're talking about Whirlwind, there were 6 tracks, not 7 tracks. One of the questions is, could you use that same technique for other formats like 7-track tape? And I've actually looked into that. In the case of Whirlwind, the misalignment between the heads and the tracks is a constant 14 mils, 14 thousandths of an inch. In the case of mapping a 7-track tape onto a 9-track head, it's not quite as nice. The misalignment varies between 0 mils and 24 mils, but the tracks themselves are separated by 71 mils. So I haven't tried it yet, but I'm actually anxious to do it. I think we'd be able to recover the data from a 7-track tape, just reading it on a 9-track head. One of the things Alcaso tried to do, we couldn't get it to work, but it might still work, is to use an 18-track head. And in that case, you have a much better chance of finding a head that's closely aligned to one of the tracks. So that's another opportunity to read some of these bizarre tapes by using a more modern 18-track head.
The next question is sort of related to that. What is the minimum and the maximum number of tracks that you can read?
Well, the only thing we've demonstrated so far is 6 tracks on the minimum, which is the Whirlwind, and 9 tracks on the maximum, which is all of the standard mainframe tape drives. But as I said, if we move to an 18-track head, we can probably go to a higher number of tracks. I don't know of any standard tapes that were recorded higher than 9 tracks except for 18 tracks. Are there other tapes of intermediate number of tracks that anybody knows about?
Next question. Are there any tapes that you can't read? For example, metal tapes.
I don't know. I believe that the Univac tapes were metal tapes, and I don't know enough about how the recording was done or what kind of heads are required to read those. So I can't answer, but I'd be interested in trying them.
Does the museum have any Univac 1 tapes in the collection?
I believe we do.
Next question. When you recover tapes at CHM, do you upload them to places like archive.org, BitSavers, etc.?
Yeah, in the case of the Whirlwind, all of the data has been uploaded to BitSavers. So we're trying to make everything as public as possible. And both my code and Guy's code are open source up on GitHub. So anybody can try their hand at decoding and simulating.
Next question. Azimuth correction with wavy tape. Was your tape sufficiently straight, not wavy, that the fixed delays for azimuth error were okay everywhere?
Yeah, the deskewing works because the fundamental problem is the tilt of the head, either when reading or writing. So it seemed to be constant throughout a recording session for the tape. Now, one of the things we discovered on the Whirlwind tapes is that those tapes got reused from time to time. So we might find a tape where the first, minute of the tape was recorded in one session, and then it begins leftover data from a previously recorded session. And in that case, you may have to restart and recalibrate and recompute the skew. And what I did in that case was to divide it into 2 separate pseudo tapes, basically. So once I discovered that some discontinuity had occurred in the middle of the tape, I created a new tape out of the second part of it and restarted the computation of the tape skew.
Yeah, I had seen something similar to that. I had some magnetic tapes that someone was recording some audio recordings, and there was some previously recorded stuff on there. So I know what you mean. It's hard to separate that sometimes. All right, next question. I remember a product that let you physically see bits on a tape. Did you use this at all in your project, or is it even available?
It is available. There are 2 forms of it. One of it is basically just an alcohol with metal filings on it. You can paint it on the tape, and when the alcohol evaporates, you can see the metal powder taking the form of the bits that are encoded on the tape. It works okay for maybe 200 bit per inch tapes, but at higher densities, the powder particles are just too big relative to the size of the bits on the tape, and it doesn't work. I recently discovered that there's a more modern version of this, which is kind of a little microscope type thing that has reusable magnetic particles built into it, and you can image tapes. But again, it only works in the case of very low densities, and it won't work for 556 or 800 or 1600 bits per inch.
Thank you. About the tape restoration, has any of this technology been used on floppy disk recovery?
I have not done that, but I see no reason why it wouldn't work. I have not done that.
Are there any pieces of Whirlwind computer, original computer, left?
Yes, it's Guy speaking. There are quite a few pieces. The Computer History Museum has quite a few in the back room. The Smithsonian has a number of items which we know were selected by Ken Olsen and some of the Whirlwind survivors for their uniqueness. The MIT Museum has a few pieces, and then there are a number of other pieces hidden and on display in various private offices and hallways in computer science departments and all kinds of things. There is an exhibit of Whirlwind stuff at the Computer History Museum as well. You can go and see three of the out of 100 or so racks that made up the machine. And I think there's still a blog article posted at CHM which identifies what those components are.
Cool. All right. It is 11. I want to thank you guys again. That was totally amazing. And our next talk is actually a class, a 6502 assembly language programming class. We're doing a fair amount of 6502 today, and this is a good start for it. I just wish this was around, 40 odd years ago when I needed it. Stephen Edwards, 6502 programming.
I'm Steve Edwards, and I'm going to talk about advanced 6502 assembly language programming for the Apple II series of computers. I've been coding in 6502 assembly language since about 1982, so about 80% of my life. Here I am in a magazine article from around then, bragging about how I was going to be programming the Apple II in assembly. I clearly remember the day I figured it out. We were cowering in our basement during yet another tornado warning, and I was reading the Apple II reference manual, Steve Wozniak's gift to hobbyists and cloners alike. This book is a marvel, and it actually came with a computer. Yes, I'm old enough to remember when computers came with useful documentation, but mind you, this was the last millennium. This book tells you absolutely everything about the guts of an Apple II, including character set information, lists of I/O locations, diagrams on the perverse memory layout of the text and graphics displays in the Apple II, schematics, monitor ROM listings, and, most relevant to my story, an appendix on the 6502 instruction set, about the driest introduction to 6502 assembly language you can imagine. I remember when I cracked the code that night, when I first understood that everything had to go through the accumulator on its way to and from memory. But I'm getting ahead of myself. It's good to understand the context of the processor if you're going to program it. At the start of 1975, there were a handful of viable single-chip 8-bit processors. The Intel 8008, which had been around since 1972, only cost $25, but ran at 500 kilohertz, only had a single external 8-bit bus demanding specialized or numerous support chips, had a meager 3,500 transistors, and could only address 16K of memory. The Intel 8080 came along in 1974 and was a substantial improvement. It could access 64K of memory with its separate 16-bit address bus, consisted of 6,000 transistors, and ran at 2 MHz, but sold for a premium, $150 at the end of 1975. Nevertheless, the 8080 ended up in the heart of the Altair 8800, which launched the first personal computer revolution, and its successors, the 8086 and 8088, gave us the behemoth known as the IBM PC, which we've been stuck with ever since. Motorola's 6800 had also come out in 1974 and was comparable to the 8080, but simpler. It had only 4100 transistors, ran at 1 MHz instead of 2, and had a smaller register set. Motorola was selling it for $175. A group of folks who worked on the 6800, including Chuck Peddle and Bill Mensch, left Motorola in August of 1974 to build a simpler, cheaper processor to compete with the 6800. Thus was born the MOS Technologies 6502. It reached the market in late 1975 at a price of around $25, thanks in part to its low transistor count of only 3,510, about that of the 8008. But it was far easier to use than that Intel chip. As you might imagine, there was quite a lot of drama and litigation surrounding the genesis of the 6502, but that's a different story. To understand the 6502, let's work from the outside in. Its pinout is straightforward but worth understanding. Packaged as a 40-pin DIP, most of its pins are devoted to its 16-bit address bus and 8-bit data bus, which allows it to access 64K. The remaining pins include a single 1 MHz clock, a read-write signal, interrupt and reset inputs, sync and ready pins that can be used to single-step the processor, and a single 5-volt power supply. The programmer's model of the 6502, which is a list of registers and other programmable visible state, is extremely simple, even by the standards of 70s-era single-chip processors. It is an accumulator-based architecture centered around a single 8-bit accumulator A, on which virtually all operations are performed. Two 8-bit index registers are mostly intended to hold address offsets, although they can be used for loop indices and other temporary storage. Rounding out the registers is the lone 16-bit register, the program counter, an 8-bit stack pointer that limits the stack to a minuscule 256 bytes, insufficient for high-level languages like C, and an 8-bit status register with the usual 0, carry, and negative bits used to control conditional branches. Thanks in part to the amazing Visual 6502 project, which I strongly suggest you Google, the layout of the 6502 die is now well understood and can actually shed light on the design of the instruction set. When we look inside, we see three regions. The top region is a regular-looking ROM that decodes instructions and feeds signals to the control logic, the second band in the chip, which in turn sends control signals to the data path that covers a little more than the lower third of the chip. The structure of the programmer's model is visible in the data path. It's arranged as 8 1-bit rows. The columns are, from left to right, the Y, X, and stack registers, the arithmetic logic unit, or ALU, the accumulator, and finally the program counter, which is larger both because it is 16 bits and because it includes logic for incrementing. This is a nifty visualization of all the 6502's opcodes, which I adapted from Gary Little's Inside the Apple IIe. At the center, fittingly, is the accumulator, and virtually all the interesting arithmetic instructions, including add, compare, exclusive OR, and others, operate on the accumulator in memory. The two index registers can be loaded, stored, incremented, decremented, and transferred to and from the accumulator. A number of instructions modify the stack pointer, including push, pop, and jump to and return from subroutine. Conditional branch and unconditional jump instructions modify the program counter. Finally, an additional group of instructions transfer and modify the status register. Now, let's dive into the details of the 6502 instruction set. If we're going to program it, we need to know what tools we have at our disposal. Instructions start with an 8-bit opcode and may be followed by 1 or 2 bytes of literal data, depending on the instruction's addressing mode. The encoding of the 6502 instruction set perplexed me for years, in part because of opcode matrix drawings, like this one from a Rockwell datasheet, which didn't provide too much insight. Here's a better way to look at it. The least 2 significant bits in each instruction divides the instructions into 4 groups. The top 3 bits determine the operation, such as add or subtract, and the middle 3 bits determine the addressing mode, mostly. There are many exceptions. Group 1 instructions include the familiar add, subtract, compare, and logical operations with a fairly orthogonal set of addressing modes. Group 2 instructions include shift and rotate, as well as instructions that load and store the X register. These provide fewer addressing modes than those in Group 1. The opcodes ending in 00 are more of a mess. There are at least 5 subgroups, including more index register instructions, flag control instructions, conditional branches, and stack instructions. Finally, the original 6502 didn't have any valid instructions that ended in 11. Let's go through the Group 1 instructions in some detail, since they are nearly orthogonal and present us with most of the important addressing modes. LDA loads the accumulator with an 8-bit value. This example uses immediate addressing, denoted by the pound sign, where the value to be loaded comes immediately after the opcode. STA stores the accumulator in memory. This example uses zero-page addressing, in which the address comes from the single byte following the opcode, implying that this addressing mode can only refer to the first 256 bytes of memory. It took me years to realize it, but the 6502's zero-page is meant to be treated like a large register file. Accessing zero-page memory is often 25% faster than accessing the rest of memory, not because the physical memory is any faster, but simply because the processor does not have to load a third instruction byte. Looking back, I didn't realize this when I started programming because the Apple Monitor consumes about 25% of zero-page locations. DOS 3.3 or ProDOS consumes some more, and AppleSoft consumes all the rest. Well, almost. The result is that if you're interested in doing assembly from AppleSoft, which I, at a tender age, was unfortunately attempting to do, zero-page locations are in very short supply. ADC adds a number taken from memory plus the carry flag to the accumulator. Including the carry flag enables multi-byte arithmetic, but there's no add without carry on the 6502. You just clear the carry flag beforehand. This is using zero-paged index addressing, where the address of the byte to be added comes from adding the single byte after the instruction to the X register. SBC is subtract with carry, meaning the complement of the carry flag indicates a borrow, again for multi-byte arithmetic. Byte in memory is subtracted from the accumulator. This is using absolute addressing, where the address for the byte to be subtracted comes from the 2 bytes following the instruction in little endian order. CMP is compare. Like SBC, it subtracts a byte in memory from the accumulator, but it discards the result and only updates the flags in the status register, typically for a conditional branch. This is using absolute indexed by X addressing, which takes the address from the 2 bytes following the instruction and adds the contents of the X index register to compute the address of the byte to subtract. AND is the bitwise logical operator. It reads a byte from memory, here using the absolute indexed by Y addressing mode, computes the bitwise AND of it with the accumulator, and stores the result in the accumulator. ORA is bitwise logical OR, which operates much like AND. This example is using the indirect indexed addressing mode, which is the commonly used complex addressing mode. The 6502 doesn't have a 16-bit index register. None of the addressing modes I've shown so far can let you access an arbitrary address in memory. Indirect indexed addressing fixes this shortcoming by letting you specify a location in zero page that is treated as a 16-bit address, very much in keeping with the zero page as a register file view I mentioned earlier. After loading the 2 bytes in zero page, addressed by the byte following the instruction, the 6502 adds the contents of the Y register to compute the final address of the operand, such as the byte being ORed into the accumulator. EOR is exclusive OR, another bitwise logical operator like AND and ORA. This example is using the uncommonly used indexed indirect addressing mode. Like indirect indexed, the address of the operand is given by a pair of bytes in zero page, but here, the address of those bytes is the sum of the byte after the instruction plus the X register. That is, the X register is added to compute the zero page location holding the address, that is, before the 16-bit address is computed. It's something like having the X register index an array of addresses held in zero page. Group 2 instructions don't support the indirect addressing modes, but are otherwise very similar to Group 1 instructions and are largely orthogonal. LDX loads a value into the X register, such as a literal. Of the Group 2 instructions, LDX is the only one that can use a literal like this. STX stores the value in the X register into memory, here at a zero-page address. INC is a read-modify-write instruction that adds 1 to the value of a byte in memory, here using zero-page indexed addressing. DEC does the opposite of INC, decreasing the value in memory by 1. ASL is arithmetic shift left. It shifts bits left by 1, shifting a 0 into the least significant bit and shifting the MSB into the carry flag. This example is using the accumulator addressing mode, where the source and destination is the accumulator by itself. ASL and other bit shifting instructions can also perform a read-modify-write operation on memory. LSR is logical shift right. It shifts the bits right by 1. The most significant bit becomes 0, and the least significant bit goes into the carry flag. This example illustrates a bit shift instruction used with a read-modify-write addressing mode. ROL is like ASL, but it takes the new LSB from the carry flag, enabling multi-byte shifting. ROR is like LSR, but it takes the new MSB from the carry flag. Now we're into miscellaneous instructions that generally follow few patterns. For example, LDY, STY, CPY, and CPX are analogous to their accumulator-centric variants, but can be used with only a few addressing modes. JMP is an unconditional jump, which comes in 2 flavors. This is the more common version, where the 16-bit target address is held in the 2 bytes following the instruction. The other addressing mode of jump is unique. Again, the 2 bytes after the instruction specify a 16-bit address, but unlike before, they are treated as the address of the target address to be read from memory. That is, this is a little like indirect indexed addressing, where a 16-bit address is read from memory, but rather than insisting the address reside in zero page, the address can reside anywhere in memory. This addressing mode is rarely used, but finds use in the Apple II monitor's CSW field, 2 bytes that contain the address of the routine currently responsible for printing a character, typically to the screen. But this can be changed to, say, send the output to a printer. The bit instruction has my vote for strangest instruction in the 6502. It loads a byte from memory, loads its 2 most significant bits into the negative and overflow flags, then performs a logical AND with the accumulator, and sets the 0 flag based on the outcome of the AND, without changing the accumulator. It's probably most useful for checking the MSB of an I/O location, like the keyboard strobe, but the AND with accumulator functionality can also be used to check if 1 or more other bits in the byte are all clear. Here's a collection of single byte instructions. These increment and decrement the index registers, which is useful when doing counted loops, shuttle the contents of index registers to and from the accumulator, and provide the rarely used ability to save and update the stack pointer. Here are more single byte instructions that can set and clear various status register flags. The carry variants are used often in conjunction with ADC and SBC instructions. The 6502's decimal flag is quite unusual for a processor. When set, it makes the ADC and SBC instructions calculate with binary-coded decimal instead of binary. This is one of the few aspects of the 6502 that was ever patented. However, I know of little use of this feature. The 6502 variant used in the Nintendo Entertainment System went so far as to remove the decimal mode circuitry, since it consumes a fair amount of area in the ALU. The 6502's conditional branch instructions are straightforward. Each is followed by a single byte containing a 2's complement program counter relative offset, limiting conditional branches to a range of roughly 127 bytes. Each branch tests one of 4 flags in the status register, namely negative, overflow, carry, or 0, and each can be checked for being set or clear. The 6502's stack-related instructions round out our discussion. The stack is used primarily for storing subroutine return addresses. The JSR, jump to subroutine instruction, pushes the 16-bit program counter on the stack and sends control to the address in the 2 bytes following the instruction. The RTS, return from subroutine instruction, undoes the effect of a JSR, popping the return address from the stack. The rarely used RTI, return from interrupt instruction, works like RTS, but also pops a saved status register value from the stack, where the 6502's interrupt handling mechanism pushed it. The processor status can also be saved and restored from the stack with the complementary PHP and PLP instructions. The PHA and PLA instructions push and pop the accumulator value on the stack. These are commonly used for temporarily saving a value, since you don't have to worry about managing the memory for the value. BRK is break, which is a software interrupt that can be used for stopping programs when you are debugging them. Its instruction code is 0, so sending control to uninitialized memory often leads to a break instruction being executed. Finally, NOP is no operation, a surprisingly useful instruction that can be used to increase the delay of a timing loop or patch a buggy program without reassembling. Now let's talk about programming this beast. To illustrate a number of coding techniques, I wrote this little demo program, which performs this eye-catching but physically inaccurate simulation of 30 bouncing balls. I started with a vision of what I wanted this bouncing ball example to look like, which I knew would consist of some initialization followed by the simulation of the physics of the balls. Here's the pseudocode. My code begins by clearing the first high-res screen and then switching to it. Doing it in this order hides the surprisingly slow screen clearing process. Next, I draw the frame, 2 horizontal lines and 2 vertical lines. This is fast enough so you don't see it. Next, I set up the positions and velocities of all the balls, and then draw the balls on the screen in their initial locations. Then I enter the main loop, which loops over each ball. I begin by erasing the ball since we're going to update its position. Then I update its horizontal position based on its velocity and check whether it needs to bounce off a wall. I apply gravity, which just increases the ball's vertical velocity, and then update the vertical position, which may involve bouncing off the bottom. Finally, I redraw the ball in its new position. Once all the balls have been updated, I check to see whether a key has been pressed. If it hasn't, I repeat the main loop. Finally, if the user has pressed the R key, I restart the program, which I found useful for debugging. I'm going to bring you through the code I wrote to perform these tasks, but for it to make any sense, I need to teach you about graphics on the Apple II. To understand graphics on the Apple II, you need to understand its text mode and how WAS implemented it. The text mode on the Apple II series displays 24 lines of 40 characters each. Each character is represented with a single byte and displayed as a matrix of 7 by 8 pixels. The first Apple IIs could only display uppercase. The IIe and later models included lowercase. My 11-year-old daughter was taught to look for friendly numbers when doing arithmetic. For normal humans, things like 10 and 100 are considered friendly, but computer people know better. We love powers of 2, which is why we don't think 40 by 24 is very friendly at all. I can only imagine how disagreeable Woz must have found these numbers, because to get around them, he came up with an ingenious solution that has cursed Apple II programmers ever since. His reasoning must have gone like this. 24 isn't a power of 2, but it's 8 times 3, and I like 8. And 40 isn't a power of 2, but 3 times 40 is 120, which is almost 128. And 8 times 128 is 1024, which is 1K, which I really like. So Woz split the screen into 3 bands of 8 lines each, and put the first line of each band into the first 128 bytes, the second line into the second, and so forth, wasting only 64 bytes out of 1024 total. Now, if you look at one of those inscrutable maps of addresses of the text screen, it begins to make sense. The lines on the top third of the screen start at 400, and then every 128 bytes after that. Then the lines in the second third start 40 bytes after each of the first batch of lines, followed by the lines in the remaining third. The Apple II's low resolution or low res mode treats each character as a pair of pixels, each having one of 16 colors, giving a 40 by 48 display, or 40 by 40 with 4 lines of text at the bottom. Woz actually worked on a version of Breakout for Atari, so it's not surprising that a little Brickout was supplied with early versions of the Apple II. But I doubt the Apple II would have been quite as successful were it not for the high resolution or high res mode that Woz basically hacked into the Apple II. High res mode is a 140 by 192 pixel mode that provides 6 colors, green, purple, blue, and orange, in addition to black and white. Each high res page, and the Apple II supports 2, consumes a whopping 8K of memory each, which is an exorbitant amount of memory for hobbyists in the late 1970s. Nevertheless, most games use high-res mode, and it's what I used for my bouncing ball demo, although I only used black and white. One of the challenges with high-res mode is its memory layout, which is like 8 text pages one after the other. Instead of representing a 7-byte pixel character, each byte in high-res represents 3.5 colored pixels in a row, and like in text and low-res mode, each row consists of 40 sequential bytes in memory. But then it gets weird. The top row starts at the beginning of high-res memory, and the next 7 rows each start 1024 bytes after the last. The next 8 rows start 128 bytes after the previous 8 rows, just like in the text mode display, and the next 8 start 128 bytes after those. Like text mode, this goes on for the top third of the screen. Then Woz uses the same trick he used for text. Starting at row 64, the addresses start again, this time 40 bytes from the start of high-res memory. This odd memory layout gives rise to the characteristic Venetian blinds effect you see when a high-res image is loaded into memory sequentially, such as from disk. The addresses make a little more sense if you look at them in binary. The lower 5 bits of the address indicate the column, mostly. The lower 3 bits of the row number appear in bits 10 through 12, and the next 3 appear earlier in bits 7 through 9, which gives the address for the first 64 rows. As in text mode, the next third of the screen, or 64 rows, are just 40 bytes beyond the first third, and the remaining 64 rows are another 40 bytes beyond that. The punchline is that Woz was able to use a single 4-bit adder to compute these addresses, which saved hardware, but left programmers with a headache. Here's the code from the AppleSoft BASIC ROMs that compute the base address of a high-res pixel. About the top 2/3 is responsible for the row computation, in part because the 6502 can only shift 1 bit at a time. This code is long and slow, which is exactly what we don't want in assembly. The solution used by most high-performance Apple II games was to throw lookup tables at the problem. These are 2 192-byte long lookup tables. The first table contains the most significant bytes of the address of each row of the high-res screen. The second table contains the least significant bytes. The tables are about 300 bytes longer than the code, but are tens of times faster. This is the typical trade-off. The fastest code invariably consumes more memory than the shortest code. The best choice depends on the application. You can find these sorts of tricks described in books like Mark Pelzarski's Graphically Speaking and Jeffrey Stanton's Apple Graphics and Arcade Game Design. The encoding of high-res color pixels is as idiosyncratic as their addresses, and the story I'm going to tell is far simpler than what's really going on, but it's enough for now. Every 2 bytes represents 7 color pixels. The least significant 7 bits of each byte represent the pixels from left to right, which is backwards from how we write numbers. The most significant bit of each byte selects its palette, choosing between green-purple and blue-orange. Black and white is easier to understand. Each 0 is a black pixel, and each 1 is a white. In fact, on a black and white monitor, this horizontal high-res resolution is doubled to 280 by 192. All zeros is black. Setting the 2 least significant bits makes the leftmost pixel appear white. Adding 2 more 1s lights up the next pixel, and adding 3 more 1s and a 1 in the LSB of the second byte lights up the next 2 pixels. Bytes with 7 1s produce all white pixels. To get color, we set every other bit. For example, setting the odd number pixels in the first byte and the even numbered ones, except for the MSB, gives purple. Similarly, setting the even numbered bits gives green. 2 or more consecutive 1s produce white pixels, and you can mix purple and green nearby. Setting the MSB switches to the blue-orange palette. Here, the odd-numbered pixels gives blue, even numbers gives orange. Consecutive 1s give white, and consecutive 0s give black. Now 7 is another very unfriendly number indeed, especially coupled with the 6502's limited ability to do bit shifting. And so, while it's possible to draw signal pixels nearby to create a shape, it's too slow for most games. Once more, the usual suspects threw lookup tables at the problem. The usual solution is so-called pre-shifted shapes, in which 7 versions of each sprite are pre-computed and stored in memory, ready to be quickly copied onto the screen. Here are the tables I used for the bouncing balls. Each ball is 8 pixels high and 8 pixels wide, represented as 2 groups of 8 bytes, the first for the first byte of memory, the second for the byte immediately after that. Every 8 bytes in these tables represents a version of the ball shifted 1 black and white pixel to the right on the screen, even though it looks like they're going the other way. Now I can explain to you my code for clearing and displaying the high-res screen. It's straightforward, yet representative of the sort of thinking you routinely do when coding in 6502 assembly. First, I set up the G.Bas.Al and G.Bas.H bytes in 0 page to 2000, the start of the first high-res page. But even here I'm doing something subtle. At the end of this code, X has 20 and both A and Y have 0. This was for this 3-statement inner loop, which writes the 0 in the accumulator to 256 bytes in memory, addressed by increasing Y. Note that an offset of 0 is written first, so that the B and E exits the loop when it reaches 0 again. Next, I increase G.Bash to move to the next memory page and decrement X. Remember that X started holding 20, which is exactly the number of pages in the high-res screen. Since it's much easier to compare a register with 0 rather than a constant, my loops usually count down rather than up. Finally, when both loops are done, I use the bit instruction to touch the 2 soft switches. These are memory-mapped I/O locations that switch graphics to high-res mode, then switches on graphics. I could have used something like LDA or STA, but I wanted to illustrate one use of the bit instruction, reading a memory location without saving the result. Here's my horizontal line code, which illustrates a typical kind of function linkage in 6502, namely, using whatever registers happen to be convenient to pass arguments. Here I chose to use the accumulator to hold the byte to be written to the screen, and Y to hold the row number. It's very helpful to also list the global variables your routine uses, since the code that calls it might be relying on them not changing. I begin by saving the color byte by pushing the accumulator on the stack, since I need to use the accumulator for something else. I read the address of the row from the lookup tables and store it in G.Bas.Al and G.Bas.H. Then, I load Y with the number of bytes to write -1 so I can count backwards, and restore the color byte in the accumulator by popping it off the stack. The loop writes the color byte, then goes to the previous byte. Here I want to stop after writing byte 0, so I use BPL to branch until Y turns negative. For the vertical line routine, I save the color in a 0 page location because I need to recall it quickly within the inner loop, and I'm already using both indexed registers and the accumulator. Here, since I want to draw up to row 1 but not row 0, I use B and E to test the end condition, which branches unless X is 0. Now let's talk about the code for drawing a ball on the screen. First, I decided to use an old graphics trick for placing sprites on the screen. I exclusive OR them onto the screen instead of simply copying them, which lets you use the same fast code for both drawing and erasing sprites. Here's the logic for the exclusive OR of 2 bits A and B. If you start with A equal to 0, the result is the value of B. If you start with A equal to 1, the result is the opposite of the value of B. Here's a way to graphically show the same thing. XORing with a black pixel gives the new pixel. XORing with a white pixel flips the color of the new pixel. The result is that if we start with a black screen and XOR with a white ball, we get a white ball. If you XOR the same white ball again, it goes away. Now if we XOR it a third time, it reappears. The exclusive OR technique doesn't distinguish erasing a sprite from drawing another nearby, so when two sprites overlap, their common white pixels cancel out and appear transparent, a visual artifact. Fortunately, because XOR commutes, you can redraw and erase the balls in any order. While unfortunate, my hope was that the balls would move fast enough for you not to notice this. Did it work? I knew the speed of the ball drawing function would be critical, so I wrote it starting from these inner few lines, which load a byte from the screen, exclusive ORs it with a byte from the pre-shifted shape table, stores that on the screen, then does it again for the next byte. This code assumes I've put the address of the beginning of the row into gbasl and gbsh, so the Y index register needs to hold the bytes offset in the row. That leaves the X register to hold the index into the shape tables. I decided to try to preserve the X register value between iterations, but needed the Y register for looking up row addresses, so I stored the current row number in the HGRX 0-page address. This code only displays 2 bytes in a single row. To display a ball, we needed to execute 8 times on different rows. So I wrapped it in a loop that first reads the next row address from the address lookup tables using the row number in the Y index register, which I increment before storing back in its HGRY 0-page location. After XORing the 2 bytes, I increment X, which holds the index into the shape tables. To exit the loop, I look at the lowest 3 bits of this index. If they just became 0, we just finish drawing the 8th row of some ball, so we can return. Now let's talk about how I handle horizontal movement. Since there are 7 black and white pixels per high-res byte, smooth horizontal motion demands the byte number to update once every 7 pixels. While I could have stored the horizontal position as a number of pixels and divided it by 7 to determine byte and shift numbers, division is comparatively expensive on the 6502, and we aren't moving the balls around randomly, so I wanted a different approach. Another issue was that I wanted the balls to move at fractional speeds horizontally, and not just 1 or 2 pixels each time. This meant that I needed some bits that would represent fractions of a pixel horizontally. Then I remembered since each ball is 8 rows high, and I am storing the bytes in order, the second shifted ball is at offset 8, the third is at offset 16, and so forth. I decided to represent the horizontal position of each ball with 2 bytes in tables called ball XL and ball XH. Ball XH contains the byte offset of the ball, which ranges between 0 and 39. Ball XL contains the shift number of the ball times 8. Storing it this way provides 2 advantages. First, the shift number is already multiplied by 8, ready for indexing into the shape tables. Second, the least significant 3 bits allow me to model moving as little as 1/8 of a pixel at a time, which makes the motion smoother. Here's the first half of the horizontal movement code, which assumes the ball number is in the X register. First, I add ball dx, the horizontal velocity, to ball XL. Now, if the result was negative, this means the ball moved to the previous column, and we need to correct for this. So we add 56 to correct for the underflow, which we can do without clearing the carry since we know it was set, and decrement the byte number. If the byte number reached 0, we know we hit the wall and branch to bounce X. Otherwise, we're done. When there wasn't any underflow, we next checked for overflow. We first saved the updated ball XL value, which may be wrong, since we check for overflow by subtracting 7 times 8, or 56, and checking whether a borrow occurred. If the carry was clear, there was a borrow, meaning the shift number was in range, the byte number does not need to be adjusted, and we can branch to X done. Otherwise, we store the now corrected shift number, increment the column, check to see whether we've hit the right wall, and if so, bounce by negating the horizontal velocity. Note that this all assumes the ball isn't moving too fast horizontally, which I ensure when I generate the initial velocities. I also use a pair of bytes to represent the vertical position, but encode them more simply. The high byte in ball DYH is the row number. The low byte in ball DYL represents fractions of a pixel vertically. The vertical code starts by applying gravity, which increases the vertical velocity by 1 pixel per update, then adds this to the current vertical position. This sequence of instructions is standard for adding 2 16-bit numbers. Finally, I check to see if the vertical position has exceeded the bottom. If it has, I fall through to the bounce code. Since we may be moving quickly near the bottom of the screen, the simple reverse velocity procedure we use for horizontal movement doesn't work here. Instead, we reflect the vertical position around the bottom line by subtracting the y value from twice the value of bottom. Why twice? If y is just a little more than the bottom position, twice times bottom minus y is just a little bit less than the bottom position, as desired. Finally, we negate the vertical velocity by subtracting it from 0. Both these instruction sequences illustrate the standard way to subtract two 16-bit numbers. This is hardly the final word on 6502 or Apple II assembly language programming. My graphics code is still comparatively simple since it does not perform page flipping to avoid flicker, and it's only black and white. And there are many more tricks to 6502 assembly, including many variants on using pre-computed tables, self-modifying code, and even dynamic code generation, all of which have found use in various programs that push the 6502 far beyond what its designers intended. Regardless, I hope this has given you some insight into the 6502 instruction set and how to use it to write interesting code for the Apple II series. The source for my bouncing balls example can be found on my website, which is an easy Google away.
Excellent. Well, there we go. Let me give you the full screen, Stephen. What do we got? Questions-wise.
Questions. How does coding on the 6502 compare to, for example, the Z80 in another contemporary 8-bit processor? How does coding on the 6502 compare to, for example,
You're on mute, Stephen, and I don't know if you can hear us. We're experiencing technical difficulties.
I can read an observation while we're waiting for him.
Yeah.
Someone says, from observing the silicon on the 6502 embedded in the NES SoC, the silicon is identical to a regular 6502, and the BCD is present but simply disabled by removing 5 transistors via changes in the polysilicon layer. And we've heard that it has more to do with the patent issue than you mentioned, rather than saving on die space.
That might be a good one to save for later. When we get Bil.H and others on, there's going to be some interesting, totally geeky wafer level discussions that come up.
Ed, were you ready?
Yeah.
All right, there we go.
All right. You want me to repeat the question or you remember?
Yeah, you better repeat the question.
Okay. How does coding on the 6502 compare to other contemporary processors like the Z80 and other contemporary 8-bit processors?
So the register pressure on this 6502 is very high. So you only have this really tiny collection of registers to play with, and so you have to constantly worry about essentially spilling into 0 page or some other location. So a lot of it is about figuring out, okay, I want to put this in the accumulator now. Oh, I might be able to save this in the X register or something like that. So you spend a lot of time sort of fussing with, oh, what is in this register when? And for processors that had more registers, that would be less of an issue. Let's see. The other thing is that the addressing modes are reasonably restricted. And so what you need to do is think in terms of, okay, I need to do this indirect index with Y. How do I get things into the position where I can actually do that?
Okay, yeah, that makes sense.
1 second, Jeff. I just wanted, Stephen, I don't know if it's a bandwidth issue on your side or not, but your video is kind of frozen or choppy. But we're hearing you fine, which is good. That'll help with the questions.
Okay.
And then for folks that are out in the ether. Again, microphone at vcfed.org for questions. Sorry, Jeff, go ahead.
That's okay. Are there people still writing code for the 6502 and Apple II series? What are they doing?
Absolutely. So certainly not as many as there were in the 1980s, say. But remarkably, we're still getting new games. Go take a look at Michael Packard. He seems to crank out one about one per year. And these are high-res shooter games or something like that, basically as good as anything you could find commercially from that time. There's a German fellow who I've been in contact with, Mark Gullenbeck, I believe is how you pronounce his name, who just pumped out a double low resolution library that lets you use double low res, which is, let's see, it's 80 by 48 resolution, which is actually pretty nice, 16 colors, and it's low enough resolution where you could draw stuff quickly, but high enough where you can actually display interesting images. So it's kind of cool. So yes, people are still actively writing this stuff today.
Next question. The Apple II and its variants have been produced for, they said, about 16, 17 years. How did the graphics modes evolve over time? And were the later machines, for example, the Apple II GS, were they backward compatible?
Yeah, so the GS is rather a marvel of backwards compatibility. And it's kind of interesting. The biggest challenges actually were worrying about the ROM locations, which people had relied on from the beginning. But of course, as they put more ROM in for the Apple II GS for various other features, they had to kind of figure out how to move stuff without actually moving it and breaking it. So it's quite a challenge. Let's see. So the big jumps were when the Apple IIe came along. They added an 80-column mode, text mode, which was very important. External additional plug-in cards had been used for that, but this standardized it and made it part of it. And this introduced something known as double high-resolution graphics, where you would use an entire 16 kilobytes to represent an entire image, and this substantially increased the number of on-screen colors to 16. And you can get some pretty impressive stuff with double high resolution graphics. That also introduced this double low res that I mentioned, which doubled the horizontal resolution of low resolution color up to 80 by 48, but very few things used that. The next big jump was when the Apple II GS came along and they added sort of a proper high resolution, and this is annoying, I can't remember the resolution of that, but they got rid of this multiple of sevens stuff. They cranked out actual analog RGB to monitors and all the rest of it. So the Apple II GS, the graphics modes were substantially improved, although they were still frame buffers. I imagine there were a bunch of Commodore 64 folks on the line who were saying, oh, but what about hardware sprites and all the rest of it? The Apple II line never had hardware sprite support.
Yeah, I was wondering about that. That was one of my, because I'm a Commodore 64 guy, so I was wondering about, oh, no sprites. You have to keep redrawing things there.
Yeah.
All right. One more question. It's very simple. I guess someone wanted to know is there a website for your bouncing balls demonstration?
There will be. So what I need to do is actually create and put that up. And yes, I'm a little bit tardy, but one of my primary successes professionally is if you type in Stephen Edwards into Google, I am #1 in most cases. So I should be relatively easy to find. You can find some Apple II related goodness there at the moment. And yes, I'll be posting the source code and a disk image and so forth of the bouncing ball example.
Well, that's it. That's the last question.
Well, I actually had one with regards to all of the technical machinations that are in the Apple II and the Apple II manual, and that is, I think, fairly typical of the way Woz did things, looking for the best efficiencies. Have you ever have you ever gotten in touch with him with regards to some of those compromises and some of those assumptions with the numbers and why he set things up?
So I met him once and didn't ask him specifically about that. One of the most interesting things he said was that it was he who lobbied for all of that technical information to be put in the reference manual and made available. And Jobs did not much like that idea because it meant people could get in and copy and build stuff. And of course, Jobs realized that you don't make quite as much money that way. So the big thing I learned from was that he wanted to make all of that technical information transparent. From reading Woz's books, however, it's abundantly clear that everything for him was, can I use one less chip? And stories of him doing this for Atari and coming up with a design for Breakout that had half as many chips as they used in the final version or something like that are really pretty remarkable. But it's abundantly clear, and just looking at the schematic with the 40 some years of experience I have now, everything was about, can I use fewer TTL logic chips at the time? And this is very different than, say, the design of the Commodore 64 or other machines that had access to a lot of custom chips. The Apple II, with the exception of the processor, was all stock chips. And the design Woz came up with was good under that constraint, but maybe a little absurd in retrospect.
Yeah, I've heard other people, including people like Al Alcorn, describe some of the stuff that Woz did as brilliant but absurd. All right. At this point, any further questions that we've got for Stephen, we'll either post online or we'll find a way to get them to him. It is time to, in effect, change manufacturers. We've done a little bit of 6502. We'll come back to it, but we're going to Intel now, and we're actually going to earliest Intel. Dwight Elvey has been working on a 4004 project that we're going to take a look at now.
In 1972, Intel introduced the first commercial microprocessor. Not the first microprocessor, but certainly the first commercial. That was, today it seems like there are very few applications that remain. That a person can find where these microprocessors were actually used. And I've only been able to come across 4 different source files for the 4004. That includes talking to Intel's museum, etc., etc. So one of the more interesting things about the 4004 is that at that time 4004 was coming out, Gary Kildall had been doing contract work for him in order to write what they call their PLM programming language. So he was also working at the Monterey Peninsula Naval Postgraduate School in Monterey, and he was able to acquire what he called broken hardware from Intel in order for his students to have hardware to work on projects. And some of it included the 4004 and later on 8008 and 8080. So Gary Kildall was very involved with some of this stuff at the very beginning. There were 2 projects that were done on the 4004 at the postgraduate school. One was a a load calculator for calculating how much weight you can put on your helicopter and still safely take off. It, of course, used parameters such as there were, of course, the static parameters like the actual helicopter you were using, how much fuel you had, what the temperature was, what the humidity was, all the factors, and the altitude, of course. So you needed to have all of these factors to know when it was safe to take off. The thing that most interested me was the other project that was done, that was a maneuvering board, electronic maneuvering board. Anybody that stood a watch on a bridge of a ship knows what a maneuvering board is, because they have to use that to calculate when they are possibly on a collision course, or even in like wartime, for instance, in a submarine, for instance, knowing where they need to go to be on a course for intercepting an enemy ship, something of that sort. So the maneuvering board was quite interesting. So I downloaded the paper that they had, which included a listing that of the program, and also a brief description of what the hardware looked like. They had what they called a schematic of it. The schematic included the layout of the lights and the switches. So that was their schematic diagram, which I thought was interesting. So years ago, I found this software and always wanted to create a working 4004 program for it. And I'm close right now. Some of the features in my hardware, I've got some of the levels inverted. Remember that the 4004 was PMOS, and ones were minus 10 volts, and zeros were plus 5 volts. So that made it kind of, you had to constantly think which level you were talking about, whether it was a TTL level or whether it was a PMOS level. So I got some of it wrong, but needless to say, I'm very close to having it functional now. Probably in the next month or so, I'll finish off the software. I'll make software changes right now rather than make hardware changes. So anyhow, I got the listing, which had the raw instructions, but the listing only had line numbers, and it did not have anything about the actual code that goes in there. I wish they had the code, but they didn't, because a lot of the listing was apparently done probably on a RS 33 teletype, and had a really bad platen on it, because what happened is certain columns, you could see where the characters zeros and C's looked the same, and letters like P and F looked the same. So a lot of it had to do with not only translating the listing into a computer readable form, which of course you couldn't do in OCR because of the poor quality, and actually getting it up to a working program. So part of my project, which I didn't show here, but I made a simulator for the 4004 in software, and actually debugged the code to get it all so it was ready for operational to try to blow on an EEPROM. The project took, like I said, I've been working on it off and on for several years. Some of it required pieces that were hard to get. I had an extra 4004 processor. I had some of the RAM I needed and some of the other parts. And just recently I've been able to acquire the final pieces. So I use KiCad to generate a circuit board, and it still has a few features that I had to hand cut wire and stitch the correct wiring in. But so we can kind of get a look at what I built, and then we'll take a look at the actual PDF that I downloaded from the library there at the postgraduate school. This is the board I built. You can see there's a 4004 in the corner over here. There's a series of 4002 RAMs. There's -1s and -2s scattered across here. The lighter colored ceramic ones are -2s, and the plastic ones are all -1s. There's I'm using the original probably used a 4008, 4009 set, and I'm using the 4289 chip. And rather than trying to make my own clock circuitry, I'm using a 4201A clock generator here for the clocking of the device. This really should have been all done on a 4-layer board, but I tried to do it as small in the space as I possibly could, because it's you know, it's a proto board and it's by the square inch, and it was already a couple $100 for the prototype. So, but it should have really been done on a 4-layer board. Just to show you what I mean by I had more screw-ups. If you look on the back here, you can see the extra wires that I had to cut and jumper to make things right. This is all the wiring off to the switchboard, and I'll use little switches. I'm going to run it a little bit. The display doesn't work, but I believe it's all a software problem, because which I will probably modify. I have another ROM that I use to test out the actual displays, so I know the displays are functional. It's just that they're not quite right. This light that's lit is actually a status light. It's supposed to mean there's an error, but like I said, getting my levels, you know, what's 1 and what's a 0 confused, it's backwards. It's a relatively easy fix. I can just use another pin on the 7474. So that's pretty straightforward. So anyhow, you can start off, for instance, like you can put in the speed of your ship, and so you can tell it what the speed of your ship is. Like I can tell it's 12, and then I could tell it that I'm on a course of maybe 90 degrees or 95 or something like that, 95. And then I can hit the own ship switch here, which you saw a momentary flash there, but that was supposed to have done something more meaningful. But anyhow, if you did something out of order, the light will go off. So like if I at this point just type a number, you can see that what it's really supposed to be doing is turning all of the displays off and turning that light on. So it's kind of going backwards. So I know all that stuff is working. It's just a matter of actually getting my levels right. And I'm not too opposed to actually changing the software to fix that. One thing that was hard to get was a power supply. You notice my UL approved blue tape over the power leads. Most of the dual power supplies are 12 and 5 used for disk drives, and the grounds are actually hardwired together. You can't separate them. So I had to find a power supply that I could use the plus and minus supply rails on it as truly plus and minus rather than plus and plus. So that's it for that. And like I said, it looks like it's coming along. I'll be able to fix the display pretty quickly. It's just a software change. I had some problems with my programmer and some other problems along the way, so it's always a constant battle. This is a diode matrix, of course, for the switches. There's 27 switches out here, so it makes it a lot of fun to try to mux those all into the processor. Yeah, this is the title page. This is the name of the library where it's kept. And I see Naval Postgraduate School here, archives. This Kenneth Harper and Kearns were the primary authors of this paper. If you look at some of the code here, you'll notice over here, first off, you get line number in hex, line number in decimal, and then number of the page you're on, the 256 page, and the address of the page that you're on. But notice there's no actual code here. It's all over here. There was multiple instructions per line, which actually kind of made sense because you had different things you wanted to do. You can see these little RCs here. I believe these are actually R0s. So you can see that they got dropped off. You can see the M over here is missing the edge of the M. And you can see a few other misses. This is really an F because when it has quotes around it, it's meant to be hex. And the values that are just numeric values are always in decimal. So anything with quotes is a hex number. Anything with decimal is just a number. But you can see, like here, this is obviously XCH. It's missing the part of the H, things like that. So it was quite a bit of effort to get the listing first typed in, and then try to run it to actually see where the problems were in the simulator, and then actually repair the actual listing, both for my typos and for 0 versus C, which was the worst one.
All right. I'm going to, first of all, remind folks again, microphone at vcfed.org for questions. And I'm going to also ask the NeoHabitat folks to indulge me for just a few minutes, because we're either 2 minutes before they're supposed to start with Dwight not having time for questions, or we're going to gift him 5 minutes. I'm hoping we can do the latter.
Definitely.
Yeah, so we'll start the NeoHabitat as soon as we're done with questions. And Jeff is... Oh, no, it's Dag. Dag right now, right?
Hi there. Excuse me. Can you all hear me?
Yep, loud and clear.
Okay, question for Dwight. Can you explain a bit more what a maneuvering board does? And were you in the Navy?
Yes, I was in the Navy, but the largest floating object I was on was a landing craft that belonged to the Army. I was mainly on shore sites the whole time. So I did spend time on Midway, which was kind of interesting. But anyway, a maneuvering board, it's actually a physical board that you put a piece of paper on that you plot out where your ship is, and you use it to calculate where your ship will be at a certain later time and where other ships that are around you would be. It's quite important for a large ship because they don't stop or turn quickly. So it's important to know where you are, where you're going, and stuff like that. So people that stand watch on a bridge are required to learn how to actually work a physical mechanical maneuvering board. Today, it's all done on the radar screen for them, so they don't have to, if they're paying attention, they don't have to do very much. Of course, the McCain and the USS Fitzgerald, they were not using their radar at the time, and therefore they weren't keeping track of where the ships were, and they both got smacked into just a few years back and killed a few people. So you can see how serious it is that you have to keep up on that. But this particular board can track 10 target ships, as you know, keeping track of where they are and when you will be, what time and how far away you will be at closest point of approach. Of course, when closest point of approach is 0, then you're in trouble. Okay?
Great, thank you. Great answer. That was the only question so far.
Okay, nobody has anything about 4004 code or any of that stuff.
Didn't see anything yet so far. Yeah, sorry.
My board is currently functional. I have a functional board. I've recoded up the display portion, and that all seems to work well, and the code works well. It does what it's supposed to do according to the text. I'm running a slightly slower crystal and reduced voltage in order to keep the parts from getting quite as hot. 4004 runs pretty hot.
One question just came in, actually. Did you work on any submarine software? I worked on SSN 688 Mark 81 software. I think that's a sea-launched pistol.
Like I said, I was always on shore base. The only closest I got to a submarine was the computer that we used. We had a computer for radio control and things like that. Was designed to go on a submarine, and the shape of it was designed to fit down the port of a submarine. But that's the closest I ever got to a submarine while I was in the service. I did fly a couple R&R flights on P3s, which of course are sub chasers, but that's it. That's about all I got.
Yeah.
And
great. Well, thank you, Dwight.
And in chat, you can come off mute if you want to, Arturk, but he was asking a question. Referrals to good 4004 programming books. if there are any?
There's, you know, on bit savers, of course, there's manuals on there, which are very, very useful. There's a few key things you got to keep track of. If you're using a register pair, which is a byte, oftentimes that uses an address for addressing ROMs or RAMs, and the MSB bits will be in the lowest order register. So 0, say it was 0 and 1, the high bits will be in 0 and the low bits will be in 1. Other than that, most of it, it's pretty straightforward. It's tedious from a normal standpoint to access external registers or the RAM registers, because you always have to first off load a pointer register, and then you have to send the pointer register out, and then you do the actual access, whatever you want to do. So there's a sequence of 3 instructions just to get anything going. It makes it a little tedious. I just wrote macros in my own assembler that I use to do a lot of these functions. So it simplified my work quite a bit. Other than that, it's, you know, you're working in nibbles instead of bytes. It's you just have to think about what you're doing the whole time.
Got it. Thank you.
Excellent. All right. Well, I think if there are no more questions, we're going to cut over to NeoHabitat. I don't know who to give the pin to, so it's up to you guys if you just want to have the view that we're seeing now, which is the tile view of everyone talking, or I can zoom in on anyone.
So I should be able to give the introduction. I'm Steve Salavan here. Really nice to meet y'all. It's an honor to be on the call. My name is Steve Salavan. I'm one of the project leads on the NeoHabitat project, where we have resurrected the world's first graphical MMO, Lucasfilm's Habitat. I'm also on the call with one of the co-founders of the project, Randy Farmer, and also one of our users, Pedro. And so we've got a pretty interesting situation here for y'all. We have, in fact, 3 different ways that you can connect. Indeed, you can even, we'll show you real quick, you can even connect via an actual Commodore 64 if you so feel inclined. So, without further ado, I'm going to show you the 3 links that will take you to places where we can get started. So, I'll share the next window. And without further ado, this is also the first presentation with the theme song. So, there are 3 different ways that you can connect to NeoHabitat. The first and easiest would, of course, be the web browser, v.ht/habitat. If you'd like to download one of our prepackaged emulators, you can check that out at v.ht/habitat-emu. And then finally, if you are so intrepid as to want to connect via Commodore 64, you go to v.ht/habitat-c64. And that should more or less get you cooking on all of this. We're very much looking forward to seeing y'all in the world. And if you have any questions, or once y'all get in there, we can demonstrate some of the features and show you around some of the cooler parts of the world. So while we're at it, I'm going to present one of the in-world screens. This is the first room that you are going to connect to when you join NeoHabitat as a new user. This is something we call the hatchery, and Randy's currently sitting in there alongside our welcoming bot, and I'm currently ghosting in there just to sort of keep an eye on things. Additionally, we have, probably a couple thousand different rooms or regions, as we call them, in world. So there's plenty of interesting places to explore. And we've always found that the more people who tend to join the world, the more interesting the situation kind of becomes. It can feel very lively indeed. So yeah, that pretty much covers the intro.
And of course, for those who don't know, I was the lead client programmer and first in World Oracle. I ran the virtual events and did a bunch of the world creation. The rest of the team was at Lucasfilm Games, now known as LucasArts. We built this from 1985 to 1988. As far as I know, it's the longest running Commodore 64 project for the most complex code ever produced in its time. So anyone who wants to ask any technical questions, any operational questions, I'm here for that. So the historical part. I also led the NeoHabitat rebirth for the Museum of Art and Digital Entertainment. They're the ones responsible for doing the legwork to get the licenses cleared so that we could run this. And as a side effect, I wanted to share that the MAID was able then to use Habitat to get the copyright extensions for museums to also apply to servers, which is a major breakthrough. This happened about a year and a half ago. You can read all about it at themaid.org. So they did the legwork so that they don't have to do it more in the future. So if people write replacement servers to bring back legacy multiplayer games for museums, for exhibit, like this is the Habitat exhibit, you can now do that legally in the United States.
Oh, we're getting a couple folks joining. This is awesome.
I was just going to ask.
I'm going to be.
If any folks have
Go ahead.
joined in, are you going to be able to show the screen and let us monitor them online?
You bet. In fact, I will go ahead and show the. I'll go and show one of the windows that is in the middle of the world. It's part of our fountain region, which is sort of like the meeting place of the Habitat Populopolis world. And here we go.
So we also have another person sharing a screen, Pedro. If you want to pop up and say hi, you can. People can look at your things when you talk, and they will see what you've got. So, yeah, we're in there. I'm in the entry region. A whole bunch of people just came in. For those who just came in, yes, someone just arrived and pressed F1, and you can't see what's going on. But I will talk to those people a little bit so that if they're watching the broadcast. Good news is someone figured out how to use the controls right away. For those coming in with an emulator, if you don't have a joystick, which you probably won't, you'll need to use the arrow keys to act like a joystick and the backtick key to act like the trigger. So you'll hold the trigger down. Habitat has the first ever that I've ever found Commodore implementation of what we now know as pie menu. So you hold the trigger down and then you select a direction and you release the trigger to choose the commands.
So while folks are coming in, I might show you all around a couple of the interesting locales inside the world. Wow, we probably have about 10 people who've joined thus far. That's awesome.
What were the specs back in the day when this was running live on Commodore? What would a normal session look like? How many people would be in there?
They would simultaneously have hundreds of people in during the beta test. It was dozens, but during the release it was hundreds. It released under the name Quantum Link's Club Carib. There's a whole story online about how it's kind of interesting to be the first MMO and the first virtual world. People didn't know what those words meant. We have summaries for those now. This is the first of its kind. So they had a problem grasping the idea of people walking around in a space and interacting with each other. And so this was very fascinating. They couldn't describe it in 25 words or less. So when they released it under the name Club Carib, they hit a lot of the fantastic things you'll see today. And to go for the club metaphor, I call it club metaphor, to try to simplify the interactions. And eventually they added back all the things. So there's so many, because this was the first of its kind, we experimented with weapons and hit points. So it's an MMO in the sense that there's combat,
magic items, virtual currency, scarce objects. The heads that you see on these characters are potentially scarce objects. A full working virtual economy, user housing. Someone earlier gave a presentation about sprites in the Commodore. Someone mentioned something about sprites in the Commodore 64. If you look at this application, the only sprites on the screen are the cursor itself, and if people type in the word balloons, the little part that goes between the interrupt pair between text and graphics, that's also a sprite. Everything else is rendered every frame. And so it uses strip painter, not unlike the one described a couple of presentations ago. And we are literally a 3D renderer rendering 2D objects, where things are occluding. If you walk around, you'll see people occlude behind objects because they're being rendered in front of them. There's nothing clever going on here. It's all brute force because there's only 64K of memory, of which 30K is dedicated to double buffering rendering frames. Looks like everyone's getting through all right. That's pretty good.
So some of the some of the other earliest MMOs included, and I don't remember the name of the one that ran on AOL, and then I was familiar with Meridian 59, which was PC based.
Yes. It's about 10 years after this.
About a decade after you guys did this. What did they steal from you?
What's really interesting is not enough. In 1990, Chip Morningstar and I gave a presentation at the first CyberConf, and it's been recorded in a book you can look up. It was published in a book called Cyberspace First Steps, where we talked about the lessons we learned from running this service. And we published it widely, as widely as we could at the time. But most of the people who built their own MMOs, when I ran into them at various things like the Game Developers Conference, had not even heard of the paper. If you logged in on the emulator, you'll need to turn off warping. So Alt-W to slow down to the normal speed. And you'll know you're warped if you try pressing the space bar and it shoots around like fast. So someone's logged in like that, and I've seen a lot of spaces. So turn off warp, which is Alt-W to turn off warp. So anyway, as I was saying, I would talk to developers, and they would not have read the papers, and therefore made a lot of the same mistakes. So one of the things that happened is people made the same mistakes for well over a decade. It was like 15 years. I don't know that anything was copied. In those days, everybody was inventing based on the same kind of reference material in their lives, from fiction and art, and everyone had a different view about what was important. And so there were a lot of things where people went for 3D rendering was the most important, and they ran into another class of problems. So it was just a Wild West field. Another thing, though, Habitat was really good for is in the 1990s, when the second batch of this stuff started coming out, the stuff most people know, they started patenting it. And so for a long time, Habitat was the thing that lawyers went to. So I had a lot of work destroying patents filed in the 1990s for things that were first shown in Lucasfilm's Habitat in the 1980s.
So it looks like we got
about
20 people in the world.
Very cool. So one of the things that a lot of the later MMOs did was they sort of emulated the D&D world, and
yes,
you ended up having character classes and advancement and so on and so forth. What part of that was in Habitat?
So to be clear, there was some of that going on already at the time. Neverwinter Nights came out and overlapped with Habitat on AOL. And it was very, very structured. The way it worked, it wasn't an MMO, but it was an MMO in the sense that they were actually implementing spells and all those other things. So, but we tried combat out in here, and what we learned was when you had a social world, that you need a PvP flag. So we implemented the PvP flag pretty quickly, and it wasn't per person; it was per location. So downtown is weapons-free zone. No one will get shot today if they don't leave town. If you leave town and someone comes up with a gun, they can shoot you and take what's in your hand if they kill you. And so these were all really early experiments, and they're well documented. If you're interested in some of the stories about that, look up a paper called "The Lessons of Lucasfilm's Habitat." That was the thing we published in 1990, and it has stories about what we learned early on from things like guns and things like that. But everyone ran their own experiments. And D&D, I'm a huge D&D fan. I still run games, and I love paper train. I still build worlds. But you know, I don't think anyone's really delivered it. In fact, when Chip Morningstar put the project proposal together, he was the lead for this product, both for the server and doing the project. He said that he'd had a conversation with Noah Falstein that we could never do good AI for opponents, and this is mid-1980s. And said, so why bother? So he came up with this idea where everyone was a player, and that's what Habitat is that vision personified in the 6502.
Dag, are there any outside questions? I feel like I'm monopolizing things.
I'm reading one that's actually in Habitat. It says, is this what Halt and Catch Fire was based on? In season 2, they featured a virtual world. And the short answer is yes, and other things, but specifically that the writers had seen Habitat, and it was coincident with the time cycle. And so they borrowed it. And theirs has got a lot more color. You can't make a Commodore 64 do what they were doing at the time. You can do this, though. So if you haven't seen it in Halt and Catch Fire Season 2, there's kind of a tribute to Habitat without naming anyone. And of course, if that's the case, then the main character, Cameron, is playing me. Of course, she looks a lot better than I do.
So one question here is, what is the link, if any, to Q-Link?
You want to talk about that a little bit, Stephen?
Yeah, so Q-Link was, of course, the predecessor to America Online, and it was the platform upon which Lucasfilm's Habitat was originally hosted. The platform ran on top of some servers known as Stratus servers. The original service was written in PL1, and basically, as far as I can tell, I believe that the original deal was actually put together between Lucasfilm and Quantum Link. The original funding came together because of a partnership that y'all put together out there back in the 80s. And as it turns out, there was a beta period where people would experience a world that was very similar to the one that you're currently experiencing right now. And when it went to general availability, which I think was probably somewhere around, what you reckon, probably about 87 or 88, it was, as Randy mentioned, something known as Club Carib, Club Carib even. And that ended up, as far as I can tell, becoming a, fairly popular feature. I remember, when my dad used Quantum Link, he was on that service plenty of times. So it was very fascinating to be part of the project that helped to bring it back, for sure. And in fact, on the topic of Club Carib, I've managed to get us back in world here. I'm going to show you a few of the regions that were very popular back then. We have a whole sort of beach zone, and it ended up becoming a pretty popular hangout spot back in the day. So that's basically the connection to Q-Link.
Okay, thank you.
Yeah, so when we took on the Reboot project, we originally had you go through Quantum Link to get to Habitat, but it added like 5 minutes to the boot experience. And fortunately, we were able to get Gary Lake Shaw to write, to take the original binaries, which is what we're running, the original client binaries, and wrap them with the launcher that you were experiencing, with the blue Habitat screen, followed by type in a name and you log, and you're taken into the game. That replaces a long series of authentication issues with the Quantum Link software. You could use the original Quantum Link software, and then you had to patch it, and you had to go through this long set of steps. And we just decided, although that would be accurate for what the whole experience was like, we wanted to focus on the Habitat experience and wanted to get people into the game immediately. So the goal was to run, if we could, an emulator in the browser. If you're using the browser experience, you're also seeing a docent on the side. As you walk your way through the world, you'll get descriptions of regions and stuff. We wanted to have a museum experience, not a recreate all the pain of the history experience. So they were an important part of it. That without them, they wouldn't have been financed. And they financed it for 3 years, which is amazingly insane. It's because it was George Lucas, Star Wars, and they were making a game in a partnership. And if you look at the history, you'll see announcements for this game 2 years before it comes out. And videos
Amazing.
2 years before it came out. Yeah.
Thank you.
This is the project that should never have happened.
Maybe a little too geeky, but how is persistence handled with regards to the multi-user stuff? You said that there were a lot of unique items and people could collect stuff.
Yeah, persistence is all on the back end. The object model is still an object model we use to this day. The original Habitat object model, which is a client-server model, where basically all the heavy lifting is done on the server because you had to do it back then, is still the basis of a platform called Elko. If you're interested in, you go to GitHub for NeoHabitat. It links through to the GitHub for Elko, which is the core server we're running on, which is basically the 9th generation of the Habitat server architecture. And you can read all about it there. So persistence is all handled on the server. The client is actually very lightweight in terms of utility. You choose commands. The protocol is basically noun, verb, arguments. That's what's going over the wire. And everything is handled on the server.
So very much the original text adventure, the Colossal Cave Adventure, like at least as far as the back end front end interface.
Well, no, because those
lamp.
were originally pure text, right?
No, I agree. I'm just saying,
Yeah, there's a kind of a logistic. There's a kind of a logistical truth to reducing everything to a clean, tiny semantic set of commands.
Yep.
But the client's much harder.
Oh no, I agree. I just wanted to make the get lamp connection.
Got it. Yeah, no, get lamp works. So basically, literally, there are lamps. You go over here, you click, and you choose get. You will pick up the lamp, and now you're carrying it around. And so very much that legacy is part of it. Although what's interesting is I'm friends with Richard Bartle, the creator of Mud 1, Mud 2, and he was working on his thing the same time we were working on this. So they are coincident. They didn't actually influence each other. But as I was saying, developers are all inventing the same things around the same time. And back then, unlike now, we weren't actually connected to each other very well. Lucasfilm Games was connected to NetNews, to use NetNews, but no one talked at that level about stuff. We mostly just argued about, commenting capability, semantics and stuff. And downloaded ASCII pics, so more people are coming in. It looks like some people are having control, which is pretty cool.
Yeah, I feel like it's been seemingly working pretty well, which is
Steve,
pretty
you
great.
might want to invite Must Be Art to wherever you are.
Must be art. You got it. So what you're seeing here is one of our new features that we added to the game. So it used to be you couldn't actually invite people to teleport to where you were. You just had to sort of walk to where they were. There was also another feature that we can use here. In fact, I can send a message over to Randy. This is something called an ESP. It's sort of like the instant message before the instant message. Another thing that's cool is that there's actually a built-in mail system. So let's say that somebody wasn't online, but you would like to send basically a mail to that particular avatar. So what I'm going to do, I'm just going to go walk towards a space where I can more easily click on my avatar, and then I'm going to pull out a piece of paper from my pocket. I'm also holding what is apparently an Olympic torch, so I'm going to put that down. There we go. Because you can only have one thing in your hands. This was one of the major memory constraint issues working with the Commodore 64. So I've just entered my pocket, and this right here is a new piece of paper. And if I go and do a do on that piece of paper, let's say that I would like to write a message to Randy. So very similar to that, you basically start the piece of paper like that. Hello, Randy. This is being sent to you live from the VCF Meetup. Sincerely, Bill Collins. All right, then we're going to go ahead and mail it. And Randy will go on his screen, see that there is a new piece of mail in his pocket. And if he was not logged in, he would see that upon his first login. And then when you started to look in your pocket, instead of a blank paper, there would be an envelope that you could then open, and it would contain information about the sender and a postmark as to the date on which the mail was sent. And we actually, it looks like we've got a bit of a party going on here. This is pretty wild. How's it going, y'all?
That is impressive. I was hoping you would get a pretty good crowd from this this setup. As it is now exactly 12:30, you guys can stay playing in NeoHabitat. We're going to sort of leave this thing running on the chat session, but it's time to talk about a little bit of small big iron. We've got David Guesswine here with a straight 8, a running PDP straight 8. I can't explain how jealous I am. But let's have a look at that. And thank you, guys.
Thank you. I'm going silent.
Thank you.
Hi, I'm David Guesswine. I'm going to discuss and demonstrate the DEC PDP-8. This Digital Equipment Corporation Programmable Data Processor 8 was the first in that product line. They did not give it a specific model designation that the later machines had, so it's frequently referred to as the straight 8. This machine was introduced in 1965. This particular one was probably made in 1966 and used at the University of British Columbia in Canada. So you can understand my slant on computer history. Did use the PDP-11 some in college, but did not use the PDP-8 in its prime time. The PDP-8 was based on the PDP-5 computer, which was introduced in 1963. The PDP-8 was DEC's low-cost entry line, so the purpose of each new model was to reduce the cost, and there was no significant performance increase over the life of the PDP-8. The PDP-8 line itself was mostly compatible. There were some variants in the instruction set between the models, but if you were careful writing code, you could write code that would work on any of the PDP-8s. The peripherals tended not to be compatible even if they were performing a similar function. Next, we're going to go over the front panel on the PDP-8. You may wonder why the machine has a front panel. It was common on many computers of this era to have one. It's useful for both debugging programs and for detecting and fixing faults in the processor itself. Without entering a program from the little bootstrap routine from the front panel, you can't get the machine to do anything. The PDP-8 is 12-bit instructions, 12-bit memory. The program counter is the instruction address register. It can directly address up to 4096 locations. There's an option to address up to 32K words using the instruction field and data field. That option is not installed in this machine. The memory address and memory buffer are internal registers in the memory subsystem that are not directly visible in the instruction set. The accumulator is the main register in the machine. link bit is the carry. The multiplier quotient is another register in the extended arithmetic option, which allows you to do up to 24-bit multiply, divide, and shift operations. That is installed in this machine. The memory on the machine is core memory, which is a non-volatile magnetic memory. So whatever was in here when you turn the machine off should still be there when you turn it back on. I had recovered memory from a machine that probably hadn't been powered on in over 40 years. So I can load an address into the program counter. The examine key will show you what's at that memory address in the memory buffer and accumulator. The deposit key will write to the current program counter address, the value set in the switch register. I can set the address of a little program I left in memory, load it, and the start at switch starts the machine executing and performs a master clear. The stop switch halts the machine. You can restart it with the continue key. There are also switches for executing a single instruction, which you then can continue after. And you can also execute each individual state in the internal instruction execution. These 8 lights indicate which of the 8 primary instructions are executing. The AND, 2's complement add, increment and skip if 0, deposit and clear accumulator, jump to subroutine, jump, input-output transfer, and operate. Input-output transfer is how you talk to peripherals, such as this 32K word disk drive. The operate instruction is a bit-encoded instruction where the various bits control operation inside the machine. So you can set a bit that clears the accumulator, a bit that increments the accumulator, and a bit that shifts the accumulator left, and that will have the effect of loading a 2 into the accumulator. These lights are the internal states in the instruction execution, and these are some internal state flip-flops, such as the run flip-flop. This is the memory side of the PDP-8. The color of the handle indicates the type of board. The red boards are the main diode transistor logic, all discrete components, no ICs. The blue boards are a faster version. The white boards are I/O functions. And the green boards are special purpose functions. Here, the interface for the core memory. This box contains the core memory. It's 4K or 4096, 12-bit words of memory. All this logic is just to support the core memory. This down here is the teletype interface. It's basically a UART. This cable is the interface to the teletype. These 4 cables and 6 more on the other side are the interface to the disk drive. This side is a reproduction. Both of them were missing when I got the machine. This is probably a little redder than the other machine I've seen. So this is the back of the machine. Here we have a 20 amp circuit breaker that's protected by a 7 amp switch on the front panel used to turn on the machine, and this accessory outlet. Here's an hour meter that you use to tell when it's time to do preventative maintenance and to see how long you can run between failures. The machine has been running 6,837 hours. These controls are used for the margin check. This, along with switches on the backplane, you could use to apply the margin check voltage to a row of cards. You would do that while running diagnostics, and then you would use this to adjust the voltage while monitoring it on the meter there. And if you saw a significant change in the operating range of the cards, you would then know that one of the cards in that row is starting to fail, and you need to determine which and replace it before the machine fails during normal operation. You can do it for both the -15 and the +10. This is the processor side of the PDP-8. These 12 cards are the accumulator. These 12 cards are the other major registers. The rest of this section up here is the additional logic needed to implement the processor. These cards down here are for the extended arithmetic element option. Down here is the power supply for the machine. Back here, and there's more inside, is exposed AC. You need to be careful reaching into this machine when power is applied. There's 3 fans in here and 3 on the other side, which provide cooling. They pull air up through the power supply, blow it up over the cards. The plastic covers help keep the air going through the cards. These are the other 6 cables for the disk drive. This is a teletype automatic send receive ASR33. This low-cost model was 8 bits and frequently used with the computers. For $1,200, you got a printer, keyboard, program load device, and program storage with the paper tape. Its disadvantages was it only communicated at 10 characters per second or 110 baud, and if it was not properly maintained, it become unreliable. This is an electromechanical device, so you needed more of mechanic skills for working on this machine than the electronic skills of working on the computer. There are over 100 spots in here that you're supposed to periodically lubricate, and a bunch of adjustments that may need to be done. The teletype used rolled paper tape. DEC distributed their tapes on this fanfold tape, and their high-speed punch and reader used this. This was a convenient form since it's stored well, and the reader would restack the tape after it read it. Versus the teletype where you needed to re-roll it after using a tape. Punch tape had the disadvantage of not being as easy to edit as the punch card decks. The most common way would be to read the tape in, fix the error, and punch a new tape. To make that less time consuming, the program could be broken into multiple sections, so you only had to fix the one section. You could also load a small patch tape after the main tape to replace the instructions in error. There were tools to either repair damaged tapes or to allow you to edit them. Would be you could cut out a section of tape you wanted to correct, and then splice in the corrected tape, and then you would use one of these patches that's punched with all holes to splice the tape back together, and then being all holes, it wouldn't interfere with reading the data on the tape, and you could also use that to fix a torn tape. Since the teletype was much cheaper than the computer, you may have a second teletype that you could use offline. So then you could type in your program. And if you made a mistake, you could then backspace the tape, and then you could hit rub out to overwrite the character with all holes punched, and then type the correct characters and finish your program. When the computer read the tape in, it would ignore any characters with all the holes punched. I'm going to demonstrate using DEC's symbolic editor to edit a program tape that has an error in it. then punch out a corrected tape, then assemble it with the PAL assembler, and then load that tape into memory and run it. I'm going to start with putting the bootstrap in, assuming that the previous program had overridden the bootstrap. I'm now going to enter the brim loader using the front panel. It has 16 instructions. The later help loader had 10. I'm going to use a cheat sheet. People who had done this enough times back in the day would likely remember it and be much faster. Start address is 7756. Load address, first instruction 6032. (6031). 5357. And I write any value to the last two locations. This allows me to verify that the binary loader loaded correctly, since it should have a jump in the last memory location. The rim loader does not perform any error checking. 7756 is the start address. Now check the last instruction to verify the binary loader loaded. It's the jump to the start of the binary loader, so we're good to load binary tapes now. I'm now going to load the symbolic editor tape. I have a program here that when I assembled it previously, I got a UA error. And if you don't know what a UA error is, you would have to go look it up in the manuals. That's the one for the assembler. Back at this time, they had good manuals for the computers where you could really learn how to use it and the various programs. And this generic one on the computer. I'm using a room microphone for this section, so you can actually hear better the sounds of the computer. One of the disadvantages I hadn't listed earlier of the teletype is it's really loud. The computer's somewhat loud, but I've heard worse modern servers. There are arrows on the tape which tell you which way to load it. Put it in the leader area. Oh, come on. Set the starting address of 7777. Load address. And start. So the relative level of my voice gives you some idea of how loud this is. Now switching back to the normal mic. So this tape will take about 2.8 minutes to load. The high-speed reader option they had could load this 30 times faster, and they had a high-speed punch, which would punch 5 times faster than the teletype. This is the original 1967 version of the symbolic editor. This one has a couple of errors in it. The 1970 version of the editor fixes these errors. And what I'm loading is a line editor. These were common back in the time of printing terminals and even survived into the DOS era with Edlin. The 12 accumulator bits being 0 indicates the tape loaded without error. The link bit doesn't matter what state it's in. And next we'll start the editor. The start address is 200. The switches control operation of the editor, so I'm going to go with default all down. You type an illegal command, you get the famous question mark error. Now load the program source tape, stop the reader, read command, and start the reader. The editor can handle programs up to about 5,000 characters. Bigger than that, you have to break them up into sections and edit each section separately. It'll take about 5.1 minutes to load this program. The UA error I mentioned earlier is undefined address, and it's saying the address TNT, which is a symbol, was undefined at program address 251, and you can see from the symbol table it printed that count COUNT was the correct label I should have been using. So this is now trash. Next I'll guess, based on the listing, that somewhere past line 45 is a label that's near the error. So I'll enter 45G. That finds the first line following 45 with a non-blank first character, which is normally a label. Now I'll guess about 4 more lines down. So dot plus 4L. Still not the right line. Escape for the next line. That's it. So I'll use the dot S to search for a character. I'll search for a T. That puts me past the erroneous label or symbol. So I'll use the rub out to remove those 3 characters. Type in the correct word. And then Control L. So that fixes that line. Okay, next we'll punch the tape back out. First I'll punch some blank tape with the T command. And now have it punch the rest of the tape with the P command. We'll need to turn the punch off so the P command itself doesn't get punched on the tape. Now turn it back on and restart the computer. So this tape had tabs in it. When I read it in, the default, if all the switches are down, the tabs are converted to space on output. So for the PAL assembler, it does not expand tabs when it brings your listing. So this way it will actually print nicer on the next time, but it will take an extra 2 minutes to punch and read this tape with the tabs converted to spaces. Next, punch the form sheet to end the tape. And I need to turn the punch on shortly after I hit return. And a little more trailer. Should have been off, but oh well. Now we have this mess of paper tape down here. The teletype, when you rip the tape, does put the little arrows to indicate the beginning and end. But I have a paper tape winder. I haven't actually seen the instructions on how you're supposed to use this, but this seems to work reasonably well. You see some other automatic winders that could be used to spool it as it came off. And then the rubber band to keep it from unwrapping. Next we need to load the assembler. That will take about 5.1 minutes. I'm not going to show much of it because you've already seen loading a binary tape before. We'll next assemble our corrected tape. Start address 200. And we need to select pass 1 on the switch registers. This tape will take about 5.8 minutes to load. It'll then, the first pass generates the symbol table and then I'll print it out at the end. The second pass generates the binary tape, and the third pass, if you wish, will generate a listing. It can't generate both the binary tape and the listing at the same time because anything punched is also printed. Now to generate the pass 2 binary tape. $200 again. Pass 2. I may have misspoke earlier. The actual time to read this tape is 8.8 minutes. And I don't need to empty the bit bucket yet. And next we'll do the pass-3 listing. This will take about 19 minutes. Next we'll load the tape we just generated. Now, time for you to see what the program does. Start 200. Punch on. Yes, we replaced a Dymo labeler. This actually was done in the day. This manual for a straight 8 was labeled this way when I got it. I've also seen that type of labeling at the beginning of tapes for identification. Thank you for watching my video. I hope you found it enjoyable or at least informative. Visit my website, www.pdp8online.com, for more PDP-8 information.
I think I'm glad we sped some of that up along the way. So hopefully we've got folks online for questions. Once again, microphone at vcfed.org if you have questions for us or for any of our presenters. We've got David here. And I didn't check, but do we have Dag here with questions? Is it Dag or Jeff this afternoon? All right, sounds like no right now, but how long have you had that machine?
Probably about 5-6 years.
Was it?
There's more than that. Time always gets fuzzy on me after a little while.
Did you have to restore it, or was it working when you got it?
No, I had to restore it. It was in reasonable shape when I got it. You know, there some cosmetic damage, you know, some missing side panels. I think I had to replace parts on 15 or so cards, and to make this video, I had to repair 2 more cards and the teletype, which was the paper tape reader was acting up. A piece of plastic had broken in it and needed some adjustments.
All right, we have Jeff online, right? or not?
1 second. I'm in the museum right now. So DAG is not there. I guess I'll check to see the questions list. Hold
Yeah,
on.
if you would do that for us. The main question I had after watching your possibly deliberately painful exercise is you've got that 32-word disk drive attached. Would that speed up your whole process of edit, compile, load at all?
Immensely. It takes about 2 seconds to load a program off the disk. It took about 8 seconds to assemble the program until it started printing the symbol table. I was going to show that at the end, but my first cut came in at 42 minutes for the 30-minute video, so that didn't make it in.
Yeah, that makes sense.
But yeah, 32K, you only really could keep the stuff you were currently working on it, since that was a tiny little disk drive.
Yeah, it's still better than 110 baud.
Yep. But no, this was intentionally showing how painful computers could be back in the day.
Yep.
And why people wanted the better peripheral. Because with decent peripheral, disk drive, it's actually not too bad a machine compared to the later early microprocessor machines.
We have some questions here. Are you ready for questions?
Yep.
Yep.
Okay, great. Someone is asking where they can buy your stylish T-shirt.
That was VCF. I think that was Southwest shirt that was given to me. I didn't actually manage to make that event, but since it had a PDP-8 on it, somebody gave me one of them.
Okay, great. Do you have the high-speed paper tape reader, and are they easy to find now?
I do have it. I have it on my 8i and my 8e. I don't have one that's designed to interface to the straight 8. The actual deck ones are reasonably popular, so they tend to go for a reasonable amount of money if they show up. I have not seen one show up terribly recently.
Okay. Is it getting harder to find blank paper tape, teletype paper, ribbons, all the consumables, that kind of stuff?
The ribbon's not an issue. That's a standard typewriter ribbon. It just needs to have the rivets in it for the auto reversing. But some of the typewriters did that. And like the early Okidata 90-something printer also used teletype, the same type of typewriter ribbons. So those aren't too hard to find. As far as I know, nobody is making the paper tape anymore. So you are now fighting for old stock. I think the teletype reel stuff is still a little easier to find than the fan fold, but that is definitely getting to be an issue. The actual teletype paper was a common paper used for lots of things, so finding roll paper that will fit a teletype doesn't seem to be that big a deal.
Sorry, Dag, just
yeah,
personal experience, the fanfold paper tape, just because the PDP-1 group at the Computer History Museum looks for that stuff, and whenever I find it, I grab it, and that's rare as hen's teeth. The roll stuff, believe it or not, the oiled rolled paper tape was used in CNC machines for the longest time, so those outlived the computer uses for quite a while, and there's a lot of new old stock out there. At least relative to fanfold paper tape. So you can find it, sort of.
That is really cool about the NC machines.
Yep. That's where I got my
so the last
from.
So the last question is, I'm surprised to see the teletype didn't have an automatic roll catcher on the output. Did they ever have such a thing?
At least some of the models have auto winders for the paper. I don't know whether the ASR 33 had that as an option or not. but I have seen it for some of the other ones. And I did find a video online of somebody had an auto winder for the punch paper tape.
Okay, thank you. That concludes our questions for now.
All right. Well, again, our email address for questions is the microphone at vcfed.org. We've got a little bit more than 5 minutes left for questions here. You mentioned that you had to replace and repair cards. Are you doing that at the component level or at the card level? Do you have a collection? I mean, it sounds like you have a collection of PDP anyway, of DEC machines anyway. Do you have a collection of spare cards, or are you going down to the chip level, component level?
There are no chips, so it's not. But it's the component level. So I do have spare cards for many of them, and with a recent acquisition, I now have the option of switching between machines for, I think, pretty much any card. But so I will do that to try to validate my guess at which card the problem is in. But no, I then go down and replace the diodes or transistors that failed. The biggest failure is diodes. There's some glass diodes that tend to go bad. So that's the dominant failure. On this last repairs for this video, it was 3 diodes, 1 transistor.
Didn't sound too bad, except for the need for repairs. And there's a large following, a large DEC following out there. I know of a couple of local folks who have big DEC collections, and there's no such thing as a small DEC collection, I don't think.
It's a temporary state.
If it happens, it's temporary. How are you guys? I mean, do you guys continue to write and swap and organize and meet and that kind of stuff? Can you tell us a little bit about that?
The main get-togethers are through the VCF East has get-togethers at their facility, work days. There's also been Bob Roswell had one up at his place not too long ago, and there are a couple people local in the area with some DEC stuff that I have corresponded with, and there's various people who just contact me through my email, through my website.
Okay. Dag, have there been any other questions that have come in?
Not yet, sorry.
That's okay. I was actually, I'm a little bit surprised that the folks at the museum now, and they must be doing a workshop or something, and they're kind of busy. But usually those folks are good for at least DEC related questions. I know that's set. Okay, so again, a reminder: it's microphone at vcfed.org for questions for any of our exhibitors. Our next exhibitor up is Brian Stewart on the line at this point. I wish I could see a good list. Let me see, because he's up in a couple of minutes.
Yes, I'm here.
There we go. And my question for you is similar to one that I asked earlier. You've got two different presentations. You've got, hold on a second.
I'm here if you can hear me.
Yeah. Oh, we can hear you. Can you hear me? So you've got 2 presentations. Both are ENIAC related. And I have to admit that ENIAC is, if you're talking computers, probably my favorite. And the question is, do you want to take questions after I run both videos, or would you like to do video questions? And you're on mute right now.
Oops. Probably easiest to do both of the videos and then questions.
Okay, that sounds fair. I'm probably, rather than bug Jeff to do a very brief museum tour, I'm going to do a quick, I'm going to borrow time from later. We'll actually borrow time from David at this point, and I'm going to start you like 2 minutes early, if not. And Mike would like to remind folks, and this is probably a good point for a reminder anyway, if you're not actively speaking, mute your microphone, and if you are speaking, make sure that you're muting the live stream behind you. I know that you want to monitor the stream, but it runs at a delay, and you'll start hearing yourself, and we get into these mental loops that I can't handle. So I will run both of your videos back to back, Brian, and we will get into a Q&A for that afterwards. Again, microphone at vcfed.org.
The ENIAC. Almost everyone in our field has heard of it. Hardly anyone is left who saw it in operation. And few have truly understood it. My name is Brian Stewart. I'm a professor at Drexel University, and I've been researching the ENIAC for 4 years. In this exhibit, we see not only a 3D model of the ENIAC, but also a pulse-level simulator of the machine. Here we see that simulator as it's computing a simple number theoretic problem. It's looking for all 3-digit numbers that are equal to the sum of the cubes of the digits. And as we can see here, there are 4 such numbers: 153, 370, 371, and 407. Now, we're going to look a little bit at how the ENIAC works here. The primary computation in the machine takes place in the accumulators. There are 20 such units in the machine, and each accumulator holds 10 decimal digits and a sign. And each digit is implemented by a 10-stage ring counter, as we can see in this figure right here. Now, the 10-stage ring counter is driven by pulses that arrive over a trunk line. So if I am receiving pulses from another unit, then those pulses get added to the value that are stored in this unit. And as you might guess, there's a carry bit that is set that causes a 1 to be added to the next column over. Now what's interesting is, how does it read them out? How does it read the digits out? And it does so, as illustrated in this figure right here, by sending 10 pulses to each of the digits. Now that, of course, will cause the ring counter to cycle through all 10 positions back to its starting point. At some point along the way, it will flip the carry bit as the pulse goes from the 9 position back to the 0 position. When the carry bit is flipped, it changes the routing of a group of 9 pulses. Those 9 pulses will either give you on one output the number stored in the accumulator, or 9 minus the number stored in the accumulator. And this allows us to do subtraction in the machine. So we will illustrate that in the simulator. So here in the simulator, we have the accumulators going from the 2nd unit through the 8th unit in this portion of the machine. This, by the way, is what you would see looking into the machine in the back left. The item you see in the lower left-hand corner, this is a representation of what was called the portable control station. It was a handheld unit that you could carry around with you in the machine and use it for debugging purposes. And we currently have this set up to, every time we push a pulse button, to carry out 1 addition times worth of activity. So let's do that. And after a few pushes, we now have a value stored in one of the accumulators. We push the button again, and we now have another value stored in 2 of the other accumulators. We can see in that first accumulator the value 15. The lights, as you can see, are representative of each digit, and the values are from 0 to 9, going from bottom to top. The other 2 accumulators each have the value 27 in them. Now the next thing I'm going to do is switch the machine so that each time I push the pulse button, I'll get 1 pulse time, 20 of which make up an addition time. And we will watch as the number is read out of the accumulator on the left. Its value goes to one of the other 2 accumulators, and the complement of the value goes to the other 2 accumulators. And so if we issue the pulse button, you can see the computations taking place. And you'll notice, by the way, that we're carrying out the addition and the subtraction in parallel. And what we now have is the 15 that we started with in the first accumulator. The second accumulator has the sum, 42, and the third accumulator has the difference, 12. So this gives you a little idea of what you would see in this exhibit on the ENIAC. If you're interested in seeing more, go to this website right here, and you can download the simulator. You can read a fair amount of documentation, including some papers published in the Proceedings of the IEEE. Thank you. Hello, I'm Brian Stewart, and I'm going to talk a little bit about various aspects of programming the ENIAC. In particular, we're going to talk a little bit about bugs in some of the original programming for it. Now, when we talk about the ENIAC, it's become somewhat cliche to talk about how different programming the ENIAC was from programming modern computers. We always highlight the fact that you had to plug in patch cables and set switches. Well, certainly the process of deploying a program on the ENIAC was quite different than punching cards or paper tape or typing at an interactive keyboard. But the process of creating the program, of determining the flow of control and the operations to be performed on the data, those weren't as different as we might think. And it's in that we're going to see that the bugs are also not as different as we might think. So let's go back to the very beginning of programming the ENIAC. What was the very first programming done on it? Well, as you might guess, the developers of the machine also were developing some programming along with the original designs. That's fairly typical for the way we go about designing something. In fact, in December of 1943, they released a report, the first progress report on the ENIAC, which contained bulk of the designs of the machine. And in that report, there was a discussion of programming. And the figure we see here is a subset of one of the diagrams that was included in that report. The programming in this diagram is for computing the trajectory of an artillery shell. This, of course, was the original justification for building the machine. The form of representation we see here is known as a setup diagram, and it describes the way in which the cables are connected and the switches are set. An alternative way of illustrating things is this setup table. In it, we have the operation of the machine represented in a two-dimensional grid. The rows represent time steps, and time flows going down the page just as modern code does. This two-dimensional representation is not terribly different than the coding forms that arose in the 60s and 70s. The primary difference is that the columns in coding forms are the individual characters that make up the lines of source code. The columns here are a bit different. Imagine, if you will, that you're programming a computer whose instruction set repertoire is only 30 instructions. So what you have is 30 columns in your form. And for any given time step, You go to the column that represents the instruction for that time step, and you put the operands into that box. Now, we would tend to think of this as somewhat wasteful, in as much as each time step would only have one instruction being executed, and the other 29 columns would all be blank. But in the ENIAC, the functional units of the machine could operate in parallel. So a number of these boxes can have something in them, indicating activities happening in parallel on the machine. And instead of instructions, the columns represent the functional units themselves. This form of representation was not at the time called a program, though if we think of it today, it really does fit our modern conception of programming. It determines the control flow. We're ordering steps in time order from top to bottom, unless there are looping operations or some form of conditional operation. The time steps each have some description of what data is being operated on and what kind of operation to perform on that data. It's essentially like the old textbook cover used to say, algorithms plus data structures equals programs. So throughout this, I'm going to refer to these things as programs, even though in the day of the ENIAC itself, the term program was being used really for something more akin to what we think of as an instruction. By the end of 1943, there had been a certain amount of programming work done, but of course the machine had not yet been built. There was by then a 2-accumulator prototype, and some programming on it, of course, was done for testing. But the larger scale development programs that were kind of motivating the choices of things like how many accumulators and so on, none of that, of course, had been tested yet because the machine hadn't been built. Well, this gets us into 1945. The machine is nearing completion, and a group of 6 mathematicians are assigned to assist with the machine. These mathematicians are women who have been hired and who have been working throughout the war doing manual calculations and using the differential analyzer for trajectory calculations. And what better resource than mathematicians who are already familiar with the problems involved to learn how to solve those same problems on this new machine, and then go on to help other mathematicians, engineers, physicists in deploying their equations on the machine. This group of early programmers, Fran Bil.H, Betty Jean Jennings, Kay McNulty, Betty Snyder, Ruth Lichterman, and Marilyn Westkoff, they became, in effect, the first programmers for the ENIAC. Certainly the first people assigned the task of being programmers. They had a particularly challenging situation in front of them because they were assigned to this machine before it was completed. So they couldn't really directly use the machine in learning about it. No manuals had yet been written, though they were told a manual was in process. And we'll get to that manual in a few moments. So they had to figure this out based on the engineering drawings of the machine, the untested prototype programming that had been written for reports, and fortunately, to pick the brains of the developers, the engineers, and the scientists who were creating this machine. And collectively, with that information, they were able to develop programming techniques for this machine, and even to develop debugging techniques that anticipate our debugging today. The term we use today, breakpoints, that was coined by this group of programmers. So they were assisting people in learning how to operate the machine. By the time the machine was complete in December of 1945, it was used for a computational problem for Los Alamos. And these programmers assisted the scientists from Los Alamos in deploying their problem on the ENIAC. By February of 1946, the machine was now ready for its public debut. So as you might guess, the period between the Los Alamos work and the unveiling was spent developing the code and the programming to demonstrate the machine in that public release, in the press release and in the public demonstrations of the machine. So this manual that the programmers were told is being worked on was indeed being developed throughout this time by Adele Goldstein. But as you might guess, because the machine was busily being used, completed, used, demonstrated, and so on, Goldstein was unable to test the programs in her manual on the machine. Now, the manual itself was being written during, as I said, this late 1945, early 1946 time frame. We don't know exactly when each of the examples in the manual was first committed to these drawings. When we study the copies of the manual that exist today, we see dates ranging in most cases from 1944 through 1947. Interestingly, the manual was officially released in June of 1946. So those instances where we see diagrams with like revision dates of 1947, it's not clear whether there were later copies of the manual produced with these later drawings, or whether drawings and manual copies have been separated and then later, when people go to scan the copies, find whatever versions of the drawings they can find. But either way, it seems quite clear that the examples developed for the manual were in place, if not before the machine was even finished, at least before its before the publication in 1946 of the manual. And in that time frame, there was really no opportunity to test it. When Goldstein's manual was completed and released as a part of the report on the ENIAC from the University of Pennsylvania to the Army, this is what the front cover of her part of the report looked like. In recent years, a company called Periscope Film LLC took scans of the manual and republished them in this book right here. And this book, as you might guess, was very heavily referenced as I was developing the simulator. And it is the reference from which I've gotten those examples that I tested on the simulator. Now, anyone who has published code knows that if you haven't tested it before you put it out there, you can pretty well guarantee that Murphy's Law dictates you will have bugs in it. And since it seems quite unlikely that Goldstein was able to test the programs in her book, it probably doesn't come as much of a surprise that there are some bugs in those programs. So we're going to look at one such bug now. This particular bug arises in the example contained in Chapter 6 of the report. Now, Chapters 5 and 6 cover the multiplier and the square rooter. And there is an example that is begun in Chapter 5 and completed in Chapter 6 that uses both the multiplier and the square rooter to calculate this particular equation right here. Now, as you can see in it, there's a square root, there's a division, there are several multiplications, and a number of additions that take place. Now, to understand where the bug arises, we first have to understand that the multiplier does not operate entirely on its own in this machine. The multiplier interacts with a set of accumulators. And in doing so, there are a number of operations that the accumulators carry out that are driven by the multiplier directly. As a result, when we have a setup table, we don't usually draw into the setup table those operations that are happening implicitly as driven directly from the multiplier to the accumulators. So what we see right here is that the multiplier finishes its operation. And when it completes the operation, it causes the result, the product that was computed in accumulator 13, to be transmitted twice into accumulator 12. Now, the reason it's done twice has to do with the way the square rooter works. Not terribly critical, but it is important that it is transmitted twice. Now, if we look closely at this figure, we see in accumulator 12 the operation of it receiving a number twice. We don't see anything drawn in on those same time steps for accumulator 13. But accumulator 14, in the second of those time steps, begins its own transmission of data twice. Now, remember I said that we can have a lot of parallelism in the machine, so there's nothing wrong in principle with transmitting from accumulator 13 to accumulator 12, and also transmitting from accumulator 14, and having those transmissions overlap. Except for one thing. If we look at the way it's wired in this part of the wiring diagram, we see that both accumulator 13 and 14 are wired for their output to go to data trunk 1. So during the second half of accumulator 13's transmissions, accumulator 14 begins transmitting on the very same wires. Needless to say, the result that ends up in accumulator 12 is not twice what was in accumulator 13. It's what was in accumulator 13 plus whatever effect occurs when accumulator 13 and accumulator 14 are transmitting on the same wires at the same time. A sort of wired OR effect. Now, it turns out this is not difficult to fix. Where accumulator 13, it is important for it to transmit twice. Accumulator 14's transmission twice was more a convenience than a requirement. Only the second part of that transmission is actually being used. So it was easy to fix this bug by adding a delay, that is, an extra operation that would hold off a control signal for one addition time, adding that delay before the control to tell accumulator 14 to transmit, and then changing accumulator 14's programming to transmit only once instead of transmit twice. And by making that change, this bug was cleared up. And it turns out in the same problem, a few time steps later, the same bug reoccurs. In this case, it's an overlap again with accumulator 13, but this time with accumulator 15. And of course, the same fix can be applied. And once that fix is applied, then the example computes the value correctly. The interesting thing about this is that the kind of bugs that we find in this early programming are really not all that different from our modern bugs. Now, of course, these aren't the only bugs that we found. there are bugs that are essentially notational in character, that are not unlike bugs we would have today in misspelling a variable or in declaring a variable of one type but using it as a different type. Things that are actually so simple that we let the compiler even point them out for us. This particular bug is more similar to the kinds of bugs that we might have today in concurrency, where I have a shared resource that I'm accidentally using in two different threads of control without having some form of mutual exclusion locking. We don't have to use mutual exclusion locking on the ENIAC in this particular case because the timing is so rigid, and we can control exactly when accumulator 13 is using trunk 1 and exactly when accumulator 14 is using trunk 1, and thereby eliminate the conflict without forcing one to wait on a lock. But the feel of the bug, the nature of it, and the sense that the programmer gets as one looks at the code and goes, oh, I see what's happening here, I need to fix this. It's very similar to the kind of debugging experience that one has when debugging concurrent code. Now, needless to say, there are other bugs that were encountered on the ENIAC. Many were not documented. But there was one other one in particular whose observation and reporting is worth mentioning. It's almost certain that this bug arose in the spring of 1946, when Douglas Hartree from England visited the University of Pennsylvania and did some work with the ENIAC. Later in 1946, in particular in July of 1946, when the University of Pennsylvania hosted what they called a summer school, what has become known now as the Moore School Lectures. On the second day of these lectures, Hartree discussed his experiences and his understanding of mechanized computation. And in it he relates this bug that he had encountered in his programming earlier that spring. And the bug was actually the result of a number being rounded up and then being used as an index into a table. And of course, if you're at the last entry in the table and you have round-off error that causes you to go off the end of the table, well, what happens? Ray-bounds error. And in the case of the ENIAC, the tables were such that when you go off the end, you roll back around to the first element. And so he was grabbing, of course, the wrong value out of the table. So it's a bug not unlike what we would recognize today. And when he talked about it, he said the following: having once appreciated what was happening, I saw that I ought to have foreseen the possibility of this situation arising and told the machine what to do if it did. But I didn't foresee it despite 30 years of experience of computing of various kinds. And this just illustrates how differently a human computer and a machine look at a problem, and how necessary it is for those organizing the application of a machine of this kind to computing problems to get thoroughly accustomed to taking the machine's eye view. One might think that the very earliest bugs in programming an electronic computer would be very different than the bugs we have today. One might think that programming has changed so much since then that none of the lessons then apply. Yet what we find is as we approach the 75th anniversary of these bugs, we find that really they aren't all that different than our modern bugs, and that the lesson is still the same. That it is vital to be able to take a machine's eye view of the problem. Thank you.
That was quite a lot to digest. But I like the basic conclusion that bugs are bugs, although had the term been coined yet, officially?
Well, that's a good question. So there's several origin stories, I guess I should say, to the word bug. The reality is we do have evidence that the word bug had been used as early as Edison. Now, of course, the famous bug that Hopper discovered in working on the Mark II at Harvard, where they found a moth whose wing had gotten caught in one of the relay contacts. And then she tapes it into her lab notebook and puts a note in there. And the way the note is phrased, it's very clear that this wasn't the first time anybody had used the word bug. She phrased it kind of along the lines of, this was the first instance of an actual bug. So I think it was a case where they were very amused that the bug had been caused by a literal bug. But interestingly, in the documentation that I have found, I haven't really come across them talking about the term bug so much. You know, they'll talk about flaws and errors, but it doesn't seem, at least in what I have read so far, that the team involved with the ENIAC was using that term very much.
Okay. A reminder to everyone that's watching this, the email address, microphone@vcfed.org. Please put, in this case, Brian's name in the subject line so that we know who to direct questions to, and please send those questions to microphone@vcfed.org. Dag, did we have...
We do have a question.
Okay, there we go.
Okay. Can you talk about the proportion of time spent setting up the machine versus running the problem, and give some examples, if possible?
Well, you kind of have to divide the life of the machine into two phases to discuss that. In the period of time during which it was being built, the early development of the programming techniques and so on that were happening at the University of Pennsylvania, the setup time was driven by the patching of cables and setting switches. And that was a significant amount of time, but the reality is that very often you would set up one problem and then run it on lots of different data. So it wasn't as bad as we would kind of imagine it to be, but it was quite significant. In late '46, the machine was basically packed up and shipped to the proving grounds in Aberdeen, Maryland, at the Ballistics Research Lab. And so by the spring of '47, it was up and running there in its new home. By about a year later, in April of 1948, they had deployed a new way of programming the machine. In effect, they had said, well, if we can rewire this machine to solve any sort of problem, then one of the things we do is rewire it to be a CPU. And it would read then numerical instructions off of the function tables. And so you had now a sequential instruction set execution, not unlike our modern machines. The machine obviously ran quite a bit slower because you didn't get all that parallelism. There was a mathematician by the name of Lemmer who, in a later conference, made the statement, that the ENIAC was a wonderfully parallel machine until von Neumann spoiled it. But that obviously made the programming somewhat easier. And so it was really at that point then a matter of deploying a program was just dialing in the switch values. So by that point, the amount of time to deploy something was quite a bit smaller than it had been and was not viewed as a really significant fraction of the overall time. Another interesting tidbit I'll mention is that for debugging purposes, I mentioned in the video that they had this little control box. And the switch up here allows you to basically determine whether you're single-stepping or running at full speed. And so one of the things that's actually discussed in the manual is you run it at full speed up to a point where you want to do some debugging. And then you can switch the switch over to single step and then single step after that. And they said, well, how do you make it stop at the point you want? Well, you go and you find the wire that sends the control signal and you just pull it out. And the next sentence in the manual is, we call that the breakpoint.
Oh, that's interesting.
So that's where our modern term breakpoint comes from.
Yeah. That's really interesting. One other question here was, can you comment on how the upgrade to core memory affected how people program the machine?
So the main thing the core memory did for you is it gave you more places to put data. It was not reading the instructions out of core still, but prior to the introduction of that core, the data memory amounted to simply the 20 accumulators. Now, it wasn't uncommon to split them up and use 5 digits for this number and 5 digits for that number. But when you kind of think about it, you're really limited to less than 1,000 bits of data storage. So the addition of the core memory unit increased that considerably by adding basically another 100 10-digit values, so roughly another 3,000 bits worth of storage. By that time, they had already switched the programming mode into this sequential instruction mode driven by the switches on the function tables. So the main thing that happened when the core memory got added was the addition of a few instructions to the instruction set for talking to the core. And that's in the papers of the time, that's referred to as the registers, or the register instruction set. And it's one of the things that ultimately is on my to-do list to add to the simulator. The simulator does not currently have that in there, but it's one of the things that I have planned to try to add to it.
Great, thank you.
Did you have any other questions there, Dag? Or I've got one here.
Let me just take one last. Oh, yeah, here's one. Is it fair to compare the ENIAC programming to modern microcode?
It's similar in a lot of ways. In fact, the best way to really characterize programming the ENIAC in its original form is to think of it as a data flow machine. When an operation completes, a signal is generated that drives the initiation of the next operation. And of course, if I have several things going on in parallel, then I need to time it so that the last of the parallel ones is what triggers the next operation. And if you look at modern CPU design, you kind of look under the covers at what's going on at the microarchitecture level, at what the folks at Intel do. The machines are basically data flow machines. So it is very much like that. It's a little different than what we would think of as microcode in the sense of bit slice microcode from the 70s or 80s. But it is very much like the microarchitectures that are going on even in modern machines.
Great, thank you.
So, with regards to your simulator, you've written that and you're evolving that. Is that available? Is that do you have that running on a website? I want you to plug that thing because it's cool.
It is so the website that I mentioned in the end of the short video. That is the page where you can basically get everything. Now, very recently, I've also put a copy of it up on GitHub. So if you search GitHub for ENIAC simulator, ENIAC-simulator, you'll find it there. It's written in Go for a couple of reasons. One is the portability is really nice. Basically, I write it and then I can just run a script that builds executables for a whole pile of different kinds of platforms. The other thing about Go that really is well suited to simulating the ENIAC is the parallelism, the concurrency model that Go has. And so what happens is each unit of the machine, say an accumulator, is implemented by a couple of Go routines. And then they communicate with each other using channels. And what's transmitted over these channels is essentially the pulses that get transmitted on the wires in the machine. So the level of emulation is very close to what the hardware is doing. And that was part of my reason for creating it in the first place. I really wanted to know how the machine worked and to understand, you know, down at the level of the pulses, what was going on. So the emulator's written that way. So yeah, you can just pull a copy of the source. If you don't have a Go installation, the web page does have executables for a variety of platforms. The graphics are all handled through TCLTK, and so as long as you've got that installed in your environment, then the emulator just fires up a child process running the Wish application in TCLTK, and then just shoots graphics commands down the pipe to it. So it's very easy to basically run anywhere.
And you simulated the original machine,
That's right.
Not the core memory stored program, von Neumann.
So there's still a number of steps to go. The situation in 48 where they deployed an instruction set. They deployed an instruction set that contained 95 instructions. In order to have an instruction set that large, they added another piece of hardware to the machine they called the converter unit. Prior to that, however, there was a proposal in place to have an instruction set that was small enough to deploy on the stock machine, if you will. And so some of the projects that I've got in the pipeline are taking the information about the different phases of instruction set design, deploying them on the simulator, and also implementing the converter unit for handling the larger instruction sets. Another thing that came along with that was a separate shifting unit. Ironically, in its original use, if you wanted to shift something by some number of digits, you simply plugged in a cable that just moved all the wires over. And so shifts were effectively free. But once it was sort of used in this sequential instruction set mode, shifts were very expensive. And so they ended up adding another hardware unit for shifting. And then again, a unit for the core memory. So the plan for the development of the simulator is kind of progressively to add these other units that were added later on in the machine, and along the way to try to reproduce as much as I can with the programming that we have records of. And that includes attempting to recreate the demonstration that was done in the unveiling. I have found a little write-up by Arthur Burks describing the sequence of things that were demonstrated in that unveiling. And so hopefully I'll be able to put together a little recreation of the unveiling demonstration.
Okay, and Dag, I think we've got time for one more question if we can make it quick.
If Dag doesn't have a question, I've got one.
Please go ahead. Yeah, I don't
Okay.
have one.
Okay, yeah. As we know, these things ran on tubes. Tubes were not terribly reliable. Have you considered in your emulator actually having faults and then having the debug techniques used to find the bad tube?
I've thought about it, not very seriously, but I have thought about it. One of the interesting things that they did was that they had designed the whole machine in terms of these modular plug-in units, and virtually all of those they had spares of. So if they could narrow down to one plug-in unit where a fault was, they could just swap in a spare and then take that unit over to the bench to diagnose it at the component level. And as a result, they kind of got into a rhythm that they were able to keep it running pretty reliably. Another facet of that had to do with the heaters on the tubes. The original design and the original instructions for how to run it called for keeping the heaters on all the time, because of course the thermal cycling is a lot of what degrades the function of a tube. As it turns out, not long before it was shut down at Penn and moved to Aberdeen, there was a fire. And one of the byproducts of the fire was that when it was turned over to the Army, the people who were responsible for it dictated that it had to be completely powered down at night. And so every morning when they powered it up, of course, they had a lot of failures. To the point where the engineers at Penn were confused as to why they were getting so many failures until they went to visit and realized it was because they were powering it off all the time. But over time, it got fairly reliable. And a lot of it was circuit designs that were oriented around maintaining as much margin as possible in the tube functionality, so that the tubes could drift off of their nominal gain by quite a bit and still function correctly. And then again, the procedures for identifying where there was a fault and swapping out a module that could then be component level debugged later.
All right. Well, we're running just about a minute late at this point, so I apologize. I'm going to cut you off, and I know that there's at least one question in the queue that we'll get to at a later date. But we were talking about Whirlwind before, which is the origin machine for core memory, and of course we switched ENIAC over to core. Our next presentation is a modern use of core memory, which I thought was pretty cool. So Andy Geppert's Core 64 project.
Hi, my name is Andy Geppert, and this is my virtual exhibit for Vintage Computer Festival West 2020. I call this project Core 64.
My project combines a layer of core memory, like this, directly over the top of an LED array. This allows the LEDs to show the state of each core when it's affected by a magnet, like this. I designed it in the form factor of an electronic badge so that it's portable and encourages interaction. All of the logic and power and control is down in this lower layer of the board. And the next level up is this LED array. And then over the top of that, the core array is placed. The core array is scanned constantly. And if there's a change in state that isn't expected, or a bit fails to flip when it's supposed to, the logic knows that there's a magnetic interaction nearby. So if I go I'll explain why this is slow in a moment. If I go here, you can see the interaction, the magnet sweeping across. The way this works is when a magnet is held close to the core, the magnet prevents the core from changing state, and the firmware recognizes that and then lights up the LED. The board here on the left in green is the first prototype that I did, and it was a single board. You can see everything's taped on the back, and it uses a teensy LC. You can also see where some things needed to be fixed. The one on the right here is a dual board concept, which sandwiches the battery pack in between there, along with the LEDs. Again, using a teensy LC, but this one has some I/O expanders built into it as well. That did not work out quite as I had hoped. Before I go into more detail on these prototypes, I'm going to jump back to the beginning of the project to share how I got to this point. I've long been intrigued by exhibits of core memory, especially the ones at the Computer History Museum in Mountain View, California. I wanted to work with the core memory myself, so I started looking around for a kit to build so I could experiment with it. Initially, all I found was Ben North and Oliver Nash's Arduino Shield project, but it was not available for sale. About a year later, I found UC's Core Memory Shield kit on Tindy, and I ordered it immediately. I put that kit together and had some fun experimenting with it. Beyond that, core memory is just nice to look at because the arrangement of the wires and cores has an artistic appeal on its own. Not to mention that this is an essential part of the Apollo technology that took humans to the moon in the 60s. But I wanted to go further with the shield and make it actually do something. Since each core represents a single bit, I thought it would be interesting to visualize the state of each core with an LED, and that led to my first proof of concept. I put together this proof of concept using a serial link between UC's 4x8 core array and a Rainbow Arduino LED array. It worked and was surprisingly fun to use. I effectively stumbled on a low-res touchscreen overlay. The next step was to integrate the cores over the LEDs. The closest match I could find was a 4x8 NeoPixel matrix. It didn't line up perfectly with the cores, so I made an adapter to direct the light to line up directly behind each core. I shared this proof of concept through a contest on Element 14 and in person with other like-minded folks at Maker Faire Bay Area 2019 and on Hackaday. I even had a basic game of snake running. The response was always enthusiastic, and I could see people having a lot of fun with it when they used it. It ends up being something that is magical to actually use. It was clear from the feedback that I should pursue this project further. As far as I know, adding an interactive element to core memory is an original concept. If you've seen anything like this before, I'd like to know about it. Please share a link in the comments below. In the process of looking around the internet for similar projects, I found an 8x8 matrix that Rolf Bolger designed. When I saw his project, it was clear I needed to expand my project for a larger interactive surface, and 64 bits seemed like a great number to use for a Commodore fan. By studying the schematic, I could see it wasn't a major leap to double the number of cores from Juicy's project. Another influencing factor in my decision to move this project forward is the fact that it pulls together many interests I have in a single project. I've always been captivated by magnetism, electronics, designing and building, and in recent years, vintage computers. So uncovering a way to stir these interests together in a single project was a powerful motivator for me. The first formal prototype is this single board design in the classic green solder mask. This was also my first complete circuit board design project from concept to prototype. I used KiCad in a great tutorial series by Sean Heimel and DigiKey. This prototype runs smoothly with all 20 of the matrix drive transistors directly connected to the teensy LC I/O pins. I maxed out the available I/O and even had to overlap some of the functions by sharing pins. The second prototype is this dual board design. To provide more I/O, I added 2 I/O expanders. I just got this one working and it is running much slower than the first prototype because I'm using the I/O expanders. Although I see some room for optimization, I think I'll steer away from the I/O expanders and go back to the direct I/O because it's about 100 times faster. You can follow the prototype progress on hackaday.io. I intend to make this project available in the form of a badge kit on Tindy. The lower logic board will be fully assembled with the surface mount components. The upper core board is the kit part of the project. Purchaser of this kit will be able to weave their own core matrix. You also have the option to create your own core driver logic and experiment as much as you'd like. There are a lot of directions you can go with just the base hardware, and I'm also including provisions for easy expansion and add-ons in the future. Thanks for hanging with me in this virtual exhibit. I'd really like to get your feedback and gauge the level of interest in this project. Please head over to core64.machineideas.com and fill out the simple survey form there. I hope to see you at a future VCF, and thanks for watching.
Weave your own core.
Hi, Eric. Can you hear me?
Yeah, I just muted myself for some reason. I just clicked the wrong button. All right. And again, as a reminder to those that are viewing, it is microphone@vcfed.org. Please send in your questions. We've got Dag moderating those at the moment. And anyone that's on this chat as well is welcome to ask questions, or if there are any folks at our museum still, it's after 5 there, they've probably gone home. Questions are incoming. So, have you made any progress since you did the video? Is the kit available yet?
Sorry, say it again?
I was asking if you'd made any progress. Is the kit available yet?
Kit's not available yet, but it looks like this. It's getting very close. I need to do one more spin. I got to get rid of that I/O expansion that I thought was going to be so great. It ends up being so slow to do the I2C stuff, to trigger all the wires and then get it to come back. There's 64 cores, as you know, and each core takes a read, a write, and a read and a write, and there's 4 wires, multiple transistors, so it's just really time consuming to read them and write all of them quickly. This one works way faster with the direct I/O.
Okay.
I have a couple questions. Nobody else has got that.
No,
go
go
for
ahead. Go ahead, Dwight.
Yeah, when I look at your array, I didn't see a sense wire. Is it because you routed it differently or something? Or?
You probably, maybe I just didn't hold it the right way. I'll hold it up here.
Okay.
There is a sense wire diagonally, so there's the standard XY grid and then just one sense wire.
And you don't? And do you have an inhibit or no inhibit?
No inhibit. I actually, I don't think I can get a 4th wire through there, because I was thinking about how fun it would be to basically start stacking these, and go to 8 layers and do 64 bytes. So I will probably do that at some point, but I'm going to have to do it differently than using an inhibit wire. I'll just block the signals to each layer.
What kind of current do you need to write and read each bit?
Good question. It's each wire, and of course there's 2. Each wire is about 1/4 of an amp, so it's about 1/2 an amp for. Boy, all you need is like a couple of microseconds. Microseconds. Yes, not milliseconds. It's in the microsecond range. It happens fast.
Hey, that's it. That's all I had.
And that's relative to the core size, right?
That's my understanding. This is me learning about core memory, so I don't know all the history on it. I've just thought it was fun, and I wanted to do something to learn more about it, and this just took on a life of its own, because it's just I've had a whole lot of fun doing this.
Where do you find cores?
eBay. Where else?
Yeah, that was a dumb question, I guess.
Oh, we do have a question here. Have you any plans for a larger version that you could use, for example, as main memory in, say, a homebrew computer?
I don't know. I have gone down the rabbit hole on this, and I've got other projects I want to do. I got to get this kit done and get it out there. I might go to the 8 layers, so 64 bytes. But beyond that, the door is open. It's a very open, accessible design. So the idea is to get it out there and just see what kind of crazy things people do with it.
Oh, great. Thank you.
I got another one, of course.
Go ahead.
Are you familiar with what they call a wire memory, which is also a magnetic memory?
I'm not. I don't know what that is.
It's kind of a unique one in that it's supposed to be non-destructive reads, and it has the effect that you look at the effect of the magnetic field, and not disturb it so much when you read it. It's interesting.
That's really interesting. I'm gonna have to look into that more.
Okay, it's just called wire memory. There's a couple articles on the web on it.
Okay.
Got one more question here. What era of core are you using? So if you went back in time, what decade, what era of when this was really used as main memory would your cores be?
Yeah, I don't know. They're 1 millimeter diameter. They're not small as they get. They do go smaller than that from what I understand. I don't know. My guess is it's just somewhere in the 60s, probably in the later part of the 60s, because it looks like things just got smaller over time, and then I think core memory faded out in the 70s for the most part.
Right. Thank you.
All right.
One of the
Okay.
let me show you guys one thing here. This is what I call the flux detection mode. So the cores are being scanned constantly. And what's really interesting about this is when you start to put different magnets on there with different focal points for the flux. So it's a really cool 2D flux sensor. And of course, you got to ask the question, why not go 3D? I haven't done it yet, but I've been toying with the idea of if I do an 8x8x8 LED cube and then do the same thing, the stacks of 8 cores, if I could get 3D flux sensing visualized, so you come in with a magnet and you could just see, the lines of force in space. I think that would be a lot of fun.
It's getting to be a big kit.
Yes, add-on.
Yeah. All right. Well, thank you, Andy. It is
Thank you.
A quarter after the hour, and we're gonna flip to something a lot more modern but still old with the Amiga Video Toaster. Amiga Bill Winters is going to walk us through that.
What's up, VCF West? My name is Bill Winters. I'm also known as Amiga Bill in the retro community. Today I'm going to demo for you one of the most legendary pieces of equipment for the Commodore Amiga computer, NewTek's Video Toaster. When the first version of the toaster was released in December of 1990, having this amount of video power in a home computer was absolutely unbelievable. A toaster system built for less than $10,000 could do things that systems costing over $100,000 in major TV studios couldn't do. It truly was a video revolution. This is an actual video toaster. It's a card that plugs into the video expansion slot on your Amiga 2000, 3000, or 4000. We can see there's B and C connectors on the back. It's got 4 composite video inputs and 2 composite video outputs. The inputs can be anything like cameras, laserdisc players, VCRs, and the outputs are for preview out and program out. Many people think the video toaster is a video editing system. Technically, it is not a video editing system. The toaster is a live video switcher. Think of your favorite sporting event. There's multiple cameras set up covering the event, and they're live cutting between camera 1, camera 4, back to camera 2. That's live video switching. That's what the toaster does. Now, you can do video editing with the toaster, but this feature wasn't available until about 4 years after it was released. And you do that with something called the Video Toaster Flyer. And this will allow you to do nonlinear editing like you are familiar with today, but this was not available when the toaster first came out. The toaster also comes with a character generator, a paint program, a video effects processor, and it also comes with the legendary 3D modeling and rendering program, Lightwave 3D. Here we are in the video switcher. This is what you first see when you fire up the toaster. At the top of the screen, we have banks of effects. The effects are basically the transition between your video sources. You come down to video controls, you've got main and preview. Main is what the main output of the toaster, and preview is what you're going to switch to next. Getting into more detail on this in a second. Then we got freeze, which will freeze frame a video. Take will do a straight cut. If you don't want an effect between sources, you can just straight cut between them, cut camera 1, cut camera 2, etc. And then this auto SMF. You can choose the transition speed, S for slow, medium for medium, F for fast, and auto will automatically do that speed for you. If you want to do it manually, you can. That's what this is right here. This is called a T-bar, and it's a reflection of an actual physical lever that is on physical video switchers. This is a virtual representation of it. Graphics will let you switch to the other programs I mentioned before. So if you want to switch to Toaster Paint, you click on Paint, the character generator, and Lightwave 3D. We also have still images that we can load up here. And we got our superimpose bank, which allows us to superimpose things over our video source. For example, you're doing titles, you want to superimpose a title over the video, this is where you do it. So this is a typical video toaster setup. You got 3 monitors. On the lower left, we have a 1084S monitor, which is our Amiga RGB out. Above that, we've got a composite monitor hooked up to the preview output of the video toaster. This is what's coming up next in the toaster switching. Then a program monitor is also a composite video out coming from the video toaster. And this is our main output. This is what you would connect a VCR to, or it's what you would send out to a live broadcast. Now right now, my gorgeous VHS webcam is being broadcast live, and I've got an image of the video toaster logo queued up and ready to go. So you know what, let's do a broken glass effect. I'm gonna click on the broken glass effect. I'm gonna hit auto, and voila. Boom, it just transitioned from my webcam to the video toaster logo, and now you can see that my webcam is queued up in the preview, and going out live is the toaster logo. Now let's say I want to change the speed of that transition. I'll hit slow. I'm gonna hit auto, it's gonna do it slower, and it's gonna come back from the video toaster logo to my VHS webcam. You don't have to go between live video to a graphic. You can go from live video to live video. So let's see what else I got. Let's click on number 2 preview, and you can see here's another camera I got set up in the back of the room, and we can switch from camera 1 to camera 2. So let me put camera 1 in the main output, and I've got camera 2 queued up in the preview, and now we're going to transition from camera 1 to camera 2. Boom, there it is. And you can see camera 1 moves over to my preview monitor, and camera 2 is now going out live. You know, and that's the basics of the video switcher. All right, let's head over to Chroma Effects. Now, Chroma Effects is kind of like Snapchat before there was Snapchat, or Instagram before it was Instagram. It comes with a bunch of filters that are preloaded, and then you can edit these filters. So let's see, here we've got a solar filter. Let's start with a solar filter. We will hit the slate to render it, and we'll see what happens. Oh, there's our solar filter. It's a solarization effect, which is pretty cool. Let's see what Crazy Nuke is all about. It's like a negative effect. It's pretty wild. So in addition to silly effects, you can also use Chroma Effects to do things like adjust the brightness of the signal. So like here, we're going from dark to light, back to dark again. And it's pretty useful if you want to change the quality of your input source. Let's check out Toaster Paint. It's basically the next step from NewTek's original paint program, DigiPaint. Toaster Paint is a 24-bit paint program that comes with the toaster. When you launch Toaster Paint, you can see that we basically switch over into Amiga RGB mode. I'm going to load in a 24-bit Amiga IFF image and bring it into our toaster project. And here it comes. This is a 720 by 480 image, but if you notice, we're not seeing it in 24-bit. And the reason for that is we're working in Amiga RGB mode right now. So this is a standard 4096 color ham image. Look at that gorgeous ham fringing right there. I absolutely love it. If we want to see the whole image, I can use this tool here, click on that, and it'll show us the whole picture. Now the reason why we're seeing this in 4096 color ham mode, we're using an Amiga 2000, so it's using the traditional ham mode. If we had an Amiga 4000 with a Toaster 4000, we could see this in AGA. Now, what do we want to do with this picture? Let's just say we want to turn this power light back on. I'm going to use the colorize mode. I'm going to do that with the keyboard shortcut. I'm going to choose this light green color to turn it on. we'll do a filled rectangle. We're going to turn this sucker on. There we go. It's a little bit dark. It doesn't look like it's actually on, so let's lighten it. I'm going to switch over to lighten mode. You can see I just switched from color to lighten mode. And now I'm going to draw over our green, and I'm going to lighten it up. Make sure it looks like it's on. There we go. And now we've got an Amiga 500 that is turned on. Pretty cool. The killer app for the toaster was certainly its 3D modeling and rendering program, Lightwave 3D. Lightwave was used on Babylon 5, seaQuest, and various film and TV productions around the world. Originally, you had to have a toaster in order to run Lightwave, but it was so popular they came out with a standalone version of it. And Lightwave is still used and supported today over on the PC. Here's our Lightwave scene, and within the scene you can load in objects, you can add lights, you can edit your camera settings, and the first thing we're going to do is load in an object. My concept for this little demo is to have an Amiga logo and take the camera and fly it past the logo, as if like we're in a drone and we're flying past the Hollywood sign. This is a pretty good perspective here. I can clearly see like where my camera is in relationship to the object. For a scene like this, whenever I'm doing a camera move, I tend to like to go with a wider lens and move the camera closer to the object, because when you're wide and close, it exaggerates the movement more and you can really feel it. Let's go to a zoom factor of 2.2. That gives us a 17mm lens. That's perfect, nice and wide. We get up and close with the 17mm. I'm going to put the camera over on the camera left side of the logo and then move the camera to the right as if we're on a dolly or on a slider. And now I'm going to rotate the camera and aim it towards the logo. Now from this perspective, it's a little bit hard to see what the camera is seeing, so it's really cool. You can change the view, click on camera view, and now you can see exactly what the camera is seeing. I'm going to push in a little bit closer, and something right about there looks good. So I'm going to mark this as keyframe number 1. Now I'm going to go to frame 30, and I'm going to set our end mark. And I'm going to move the camera to its final position. So I'm going to slide it to the right, pan the camera left, and look back at the logo. Frame number 30 keyframe, hit OK. So now we have our 2 keyframes. So what I want to do now is create a wireframe preview. I'm going to click the play button, and not too bad. Here's our final render of the animation. Let's check out the toaster's character generator. A character generator allows you to incorporate text into your project. It could be titles, credits, etc. There's 4 different types of text you can have with the toaster. So here's an example of text over a background color. Here we've got text over video. But wait a minute, that doesn't look like Kiki Stockhammer. We can go change it. Erase in the text, put in some Amiga Bil. Boom, there we go. All right, let's do a little end credit roll. Execute. Thanks for watching. I hope you enjoyed this brief overview of NewTek's Video Toaster. Stay tuned for more in-depth videos. Amiga forever. So there you have it. I hope you enjoyed this brief overview of NewTek's Video Toaster. Thanks so much for watching, and enjoy the rest of VCF West.
I'm going to need sound again. Sorry about
Mic
that.
check 1, 2.
Yeah, exactly. Well, you know, if you don't click the right buttons. So we've got a few minutes for questions. Dag, what do we got going?
Okay. First question: did TV studios use the toaster, and if so, what for?
Oh yeah, TV studios definitely use the toaster. They use it mostly for like live video switching, like I mentioned, and it was really popular in public access channels because, like I said, it's a really powerful video switcher that costs much less than your typical video switcher. So like my friend at the time, he worked at ABC in New York City, and they had this video switching system that cost like over $100,000, like $120,000. And when the toaster came out, the whole package cost like under $10,000, and it just kind of like blew them away. So it was something that a lot of public access channels really gravitated towards because of the price point. But then professional studios use it as well. Like I mentioned, they use the 3D modeling and rendering program Lightwave for TV shows like Babylon 5 and seaQuest. So yeah, it found a good home both in public domain, public access, and more professional studios as well.
Great, thank you. Next question is, which maybe you kind of answered a little bit. What became of Lightwave?
Oh, Lightwave is still available today, believe it or not. Yeah, so it's interesting. When Lightwave first came out, you had to have the video toaster in order to use Lightwave. And then they came along with the standalone version of Lightwave, so you no longer needed the toaster hardware. You could run Lightwave natively on an Amiga. And but NewTek is still around, and NewTek is an awesome company, and they make something called the TriCaster, which is a video switching live streaming service. Anyway, they still have Lightwave. Lightwave's available for the PC, and you can buy it. It's competition for like Blender and Cinema 4D.
Final question, or one more question is, Bill, is the video toaster the coolest video device ever invented?
Yes, the video toaster is the coolest video device ever invented, for sure.
That sounds like a plant.
I mean, Will Wheaton, Penn Jillette, Tony Hawk, they all use video toasters. So yeah, it's definitely what all the cool kids use. And it's so funny because since it's the last question, I can elaborate. I always dreamed of having a video toaster. I saw it for the first time. I still run the Westchester Amiga user group. We meet in just outside of New York City, and we had NewTek come in and demo the toaster for us in 1990, December 9th, 1990. I'll never forget the day. And so NewTek came and demoed it when it was in alpha, and I just dreamed of having it because I love filmmaking and I love video, and I'm actually a cinematographer now professionally. So when I saw the toaster first come out, man, I wanted it so bad. And even though like it was a really great price point, it was still, to have a full-blown toaster system was still quite expensive. So obviously I couldn't have it when I was 15 years old. So I finally got one. I finally got one in March of this year, and that's when. I'm just starting to play with it. I'm actually not a toaster expert yet, but I'm learning. I got it right back here. That's my toaster, and that's actually not the toaster I was playing right now. I'm playing a video. The toaster is actually quite loud because the fans in the Amiga 2000 are quite loud, so I turned it off so you guys could hear me better. But that's my toaster back there, and I'm learning it, and it's just an absolute blast to finally have the holy grail of video devices that I always wanted to have when I was a kid.
Oh, that's great for you. We did get one more in between as you were answering that one from Bill Hurd. Tell Bill, I remember the day Carrie Sagatti got the first Amiga Genlock to work.
Wow, that's amazing. So I didn't, like I said, I couldn't afford a toaster back then, but I did have a Genlock, and it was called a Rock Gen, and I had that on my Amiga 500 and my Amiga 2000, and that was like, I had that, and I had something called a Chroma Key, and and like between those two, I kind of had like a poor man's video toaster, so I was still doing like titles for my high school videos and stuff, so it was amazing. Like the video capabilities of the Amiga were just awesome, and it was like the first home computer, in my opinion, that was really geared towards home video and artists. So it was amazing. It's so powerful and ahead of its time. It really allowed me to do stuff that no one else was doing at the time, just at home with this little Amiga 500 computer. It was amazing. What's up, Bill Hurd?
Yeah, we're going to hear a little bit more from Bill later, but for the awkward segue, I did want to get Bob Roswell's video up and running. So thank you very much, Bill.
Thanks, guys. Awesome job. The show's awesome.
Thank you. Yeah, we're having a lot of fun. And Bob's got a collection where individual units outweigh my entire collection, and I've got a lot of crap. So let's let Bob talk about his Univac 490, and then we'll go to his questions. Again, microphone at vcfed.org.
Hello, and welcome to the Univac exhibit at the System Source Computer Museum. System Source Computer Museum is in Hunt Valley, Maryland. We're 4 miles outside the Baltimore Beltway, and we're looking forward to hosting all of you to see the whole museum and not just a single exhibit as soon as the COVID-19 crisis is over. The Univac 490 is the largest single CPU that we have in the collection. Here we're looking at a 12-foot long chassis. It is 6 foot 6 inches high and approximately 3 feet deep. So it's a big boy, and that of course is just the CPU. The entire system took up full rooms, and we're extremely lucky that Scelbi hired photographers to take pictures of all the Univac 490 setups, and they are on deposit at the Hagley Library in Delaware. So the Univac that we have is at the very left-hand side of this picture. There's a console and a number of tape drives in this picture. Here's another picture with what looks like a line printer and possibly a card reader in it. Yet another room-size setup. In this picture, we see the Univac set up with its original mass storage, which would have been memory drums. So memory drums are large spinning cylinders coated with a magnetic material, very much like a disk drive, except that on a hard drive now you have moving read-write heads. The drums had fixed read-write heads, one for each track, and they're over there in the left-hand portion of the picture. In 1963, when this unit was developed, there were no hard drives, but later that year, Scelbi did introduce some hard drives, and that's what it looked like. The Univac 490 is also the slowest completely electronic CPU that we have in the collection. So when we got the Univac, the iPhone 4 was new a few years ago, and I did a little bit of benchmarking just based on the statistics, based on floating point multiplications and divisions. The iPhone 4 is on the order of 110 times faster than our Univac 490. In a strange coincidence, if we lined up iPhone 4s and stacked them, 110,000 iPhones would fit inside the chassis of the CPU of our Univac 490. So it's not the fastest thing in the world. It's also the most expensive CPU in inflation-adjusted dollars that we have. So the CPU alone, each one was sold for $2 million. A large number of organizations bought them. One went to the Bowery Savings Bank. We'll see a picture of that. Several went to the airlines, and 6 of them. You may have noticed that the signs on the Univac 490 say real-time system. So what we mean by that is most of the computer systems in the 1960s and even through the 70s when many of us got our start, the computers were batch-oriented. What that means is that we sat down at a key punch machine, we key punched our program, we walked over to an operator with a deck of cards, the operator read the cards in, we waited. In my experience, it was typically about a half an hour, and then we would get a printout on green and white barred paper. It was done that way because computers were just way too expensive to sit there waiting for Bob to type a character into an online editor. But batch-oriented systems don't work too well for real-time data. So examples of real-time data that we'll talk about are things like telemetry, getting data from flying spacecraft in real time. Another application would be for airline reservation system. Again, real-time applications. We have to keep that database right up to date. So our Univac 490 was installed at Goddard Space Flight Center. You can see it a little bit here in the very back. Over on the right-hand side of the picture here, what you're going to see is a map of the world and strings that represent where NASA had tracking stations. So the computer's obviously way too large to fit inside the Gemini or Apollo spacecraft. Instead, the spacecraft had radios in them and telemetry data, what the astronaut's heart rate was, what their blood pressure was, the performance of the aircraft itself was all beamed down to Earth in a narrow beam. In order to capture that data, NASA had ground tracking stations. So here's a picture of the antenna that tracked the spacecraft that was at Goddard Space Flight Center in 1968. But because it's moving all the way around the Earth, one of these isn't going to do the job. We need a dozen of them all around the world. So here's a picture of another NASA setup in Madrid, Spain. And in some cases, there's no land where you needed a tracking station. So the tracking station was on a Navy ship. Each Navy ship had a Univac 1218, also known as the Univac CP855 UYK. It's an 18-bit computer that gathered the data from the satellite, sent it over a radio modem, and the radio modem's connected to Goddard Space Flight Center. Back here on our Univac, up in the mirror, you can see the connectors up at the top. That's where the data feeds came into the computer. Closer look at that. This is again on the very top of the computer. And I'm embarrassed to notice right now that we have one of our infamous stink bugs stuck in connector J063. So just here's an article explaining how it worked. Just in the first sentence here, I find it interesting. Highly reliable Univac 1218 computers operated for a total of 910 hours during the historic Gemini 4 space mission without a single failure. So it's only 910 hours. It doesn't feel very long. But the mean time between failure quoted for both our Univac 1218 and the Univac 490 was only 1,000 hours. So there were 2 Univac 490s at Goddard Space Flight Center, and there were more at Mission Control for redundancy. Another use of the Univac 490 was in the first, what they called PNR, Passenger Name Record System. So what's going on here is before the Univac 490, when you made an airline reservation, you spoke to someone, that person got out a notebook, found that day's flight, wrote your name in, and you had a reservation. If you changed your reservation, somebody got that book and got some white out and crossed it out. With Eastern Airlines and British Air cooperated to build an operating system for the Univac 490, and they were able to have 1,000 terminals like this going over modems and building really a forerunner of the modern air traffic, not air traffic, but reservation systems. I'm particularly excited about the Univac 490 because it was the first real computer that I ever personally saw. So the American Library Association brought a Univac 490 to the New York World's Fair that was in 1964 and 1965. And visitors like me could look in and actually see a computer. And then we could walk over to a terminal and type in any subject. And as long as there was an entry on that subject in the Encyclopedia Britannica, we would get a printout that we could take home. I do have an example or two in the museum. So it's really sort of like the internet today, although in this case, the only source was Encyclopedia Britannica. So that was probably not the most popular exhibit at the New York World's Fair, but it caught my eye. So now let's take a look at how the Univac is built. So our Univac is built with only about 18,000 transistors. They're discrete transistors. Integrated circuits would be a number of years in the future. So there are approximately 1,000 of these boards. Here's a closer look at one. Each board has a handful of test points. Reliability was not yet there, so you can test each board through these test points. And corresponding to each board type, we're lucky enough to have a complete set of schematics. We can see how that is put together. So I'm not much of an electrical engineer, but these are simple enough circuits that even I have some chance of understanding how a line driver works or how a flip-flop works or all the various types of cards that are in the system. So there's some close-ups of it. The cards are in the front of the computer. In the back, we have this crazy rat's nest of wires that connect each of the cards together. And I would love somebody's explanation as to why they used so many white wires. Clearly they had colored wires because we have some orange wires and some red wires and some red-white wires and some yellow wires. But there are thousands of white point-to-point connections on the back plane of the Univac 490. So our Univac 490 has core memory. Here's a close-up of some cores. We have 90K words of memory. 30K words of memory. The word length on this is 30 bits, so today we would call this 96K of memory. That means there's about 900, for 96K, that would be 96,000 bytes. Each byte would have 8 bits plus 2 parity and error correcting bits made out of these little magnetic cores. So these are ferrite cores, and by putting a voltage on the X and Y, we can flip the magnetic field. And then we have a diagonal sense card so that we can read any individual core. These cores are pretty tiny. So a core plane looks like this, and there's a whole stack of these core planes. And on top of each core plane are the diode matrix for deciding which bit or byte we're trying to get to at a time. So there's stacks of these cores here and here and here and here. There's about 10 deep here in the middle on the bottom. And then there's another set of them on the other side of this door. This door weighs about 280 pounds for our 96 kilobytes of memory. The door is open. These gentlemen from the Bowery Savings Bank are admiring their new Univac. So here at System Source, we're trying to emulate the former and hopefully future Living Computer Museum. We do have many, many, many working exhibits. We would love to turn on the Univac, but our Univac has not been turned on since 1969. So today's the 12th of July. James Mahoney was up from helping build a tester. So Dwayne Craps, who's been a member of the Vintage Computer group up in New Jersey, had built and had worked with an audio tester. He was nice enough to send us the schematics for one. James bought one. So with this, we can take each card out and test that each card behaves the way we expect it to, one at a time. The next step that we're beginning to think about is how do we turn this on? We have a 280 volt power supply. It has 15 positive, 15 negative, minus 3 volts. It also has some higher voltages in it. I'm frankly afraid to plug it in with the giant capacitors. I'm leaning towards just buying a modern power supply and cleaning up the old one. But I would love anybody's advice in where we go to turn this back on for the first time in 1970. So it's the first time in about 51 years. So the images came from a bunch of different sources, giving credit where credit is due. And we'd love to see you all when you can come to Hunt Valley. We have changed the policy in the past week. I took the snapshot of the website a few days ago. We are accepting 2 visitors at a time as long as they wear masks, or 1 family group at a time. And it's my turn to talk. Unbelievable.
Sounds like you're there. Are you with us, Bob?
Yes, I'm with you. Hi.
Okay, good. Yeah, it sounded like bad timing there for the moment. And we've got about 13, 14 minutes for questions for Bob about obviously the 490 or about the museum or any of the other stuff. And again, microphone at vcfed.org. And in answer to your question in the video, or one of your questions in the video, I would recommend, and maybe coordinating through DAG, getting in touch with the restoration teams at the Computer History Museum. they've done some pretty impressive restorations and can probably help walk you through some of the finer points of making big old power supplies do the things they're supposed to do.
Thank you.
I hope I didn't just volunteer you for something you didn't want to do, Dag.
Oh, no, that's fine. So, Bob, we have a couple of questions for you already. Is your Univac 490 the one that was at Goddard?
So I was told that it was, and along with it, with the documentation that came with it was definitely from Goddard. I don't have a serial number or any actual proof other than the person who I got it from said it was there. Did he know it firsthand? I'm not sure.
Right. Thank you. Do you know what the military versions of the 490 were used for primarily?
I do not.
Okay. That's it so far.
All right. Again, if there are any other questions that folks have either on the chat or at the museum in Jersey or wherever else, we can still field those. I don't want to stray too far away from the Univac and the restoration of that, but I did want to give you an opportunity to advertise some of the other stuff that you've got in your museum. You've got a huge collection out there.
So yeah, we have a lot of things. Some of the highlights, we do have one of the, in the Apple registry, we have Apple I number 10. We have most of the Apple computer products from the Apple I through 10 or 15 years ago. We have a working model of anti-cathera mechanism that was built by Dave Goodchild over in England. It's a fun thing to play with. One of my favorite artifacts, which I think we're going to show virtually at VCF East, is our working linotype. So that's a Baltimore invention. It's a word processor, sort of invented between 1880 and 1900 that goes ahead and does typesetting. But there's lots of other toys to play with.
Okay. Any other input? Any other questions, Dag, coming in?
Nothing.
Oh. I have a question, Eric.
Okay.
So, Rob, what is the anticipated reopening of that museum with everything that's going on?
From your lips to whatever. I mean, unfortunately, Maryland is seeing an uptick in cases. We're accepting, as I said in the video, 2 masked visitors at a time or 1 family group. But for larger tours, we're still closed. And we'll wait and see, what happens locally and statewide and probably nationally as far as reopening for larger groups.
All right, thank you. Yeah, you have a lot of good stuff there, and I look forward to you doing some more videos for VCF East.
Great, thank you, everyone.
All right. Let's see. I don't know. We have about 8 or 9 minutes left in the time slot before we're going to do Dave Babcock's 1620. And I don't want to start that early. If
Did we get another question there, Dag?
Do you see one?
What software operating system applications did you get?
Okay, thank you.
So there is manuals describing and some source code for the telemetry data that came from NASA. And on top of that, there are just in the manuals there are various test routines, but I don't have any media. There's just examples of what the codes look like in the manual. No operating systems. Would love to find it.
So none of the other like documentation, none of the repair stuff, none of the maintenance stuff.
I'm sorry. Say it again. I had trouble hearing you.
It's okay. Is it? I was just wondering if the other than the telemetry and the other information, if you'd gotten any of the repair manuals or whatever else, because that would feed into that whole power supply issue you might have.
Right. So we have a pretty good full set of schematics. I will, I guess, see if I can put it out on Bit Savers. Ryan Schiff, who works with me in the museum, recently scanned in thousands of pages. Right now it's just on our Google Drive, but I'd be happy to share all of that. I guess Bit Savers is probably the best place to do that, or does anyone else have better suggestions?
No, I think Al has turned himself into the world's repository for that kind of stuff. Are you out of space yet? Are you hearing me, Bob?
I'm sorry. Say it again. I heard what you just said, but there was something short you said before that I missed.
Are you out of space yet? Do you still have room?
Am I out of space? Yes and no. Yes, we're out of space. Yes, I've rented some more space. And in the next very short handful of years, the goal is to sell the computer business and go full-time into a real museum, not just 10,000 square feet of our existing office.
Wow. All right. Anything else coming in?
I've got a question.
Yeah.
Yep. Those boards look like they're germanium transistors. Where are you accessing replacement components to get your boards up and going?
Again, you're way ahead of me.
I'm just wondering about where the components were coming from.
Bob, can I ask a different question? Have you looked into the history of real-time computing? Do you know who was doing it before Univac?
I don't. Everything that I've read shows this as really one of the earlier real-time computing systems. So I'm sure there was something before it, but I don't know who would have made many of them. Does anyone else know?
Not personally. Okay, it doesn't sound like. I mean, again, I would defer the.
When you read through, when you read through the sales literature, they make it sound like this was their baby, but that's sales speak.
Of course, yes.
Yeah, I mean, I would end up deferring to the folks at the Computer History Museum. I know that they've got a real-time computing exhibit and some curators over there that are pretty conversant in that whole concept. But I'm not sure what contemporaneous stuff there is. All right. Were there any other questions out there, Dag, or any of the folks online? Jeff, are there any folks left at the museum, or is that whole effort done with because it is 3 hours later there and it's almost 6 o'clock? Jeff missed that. No other questions?
No.
The museum is closed itself for tours, but we still have a few guys here working on the repairs, different things, and watching the show.
Okay. Just wanted to encourage if they have any questions, they can ask them as well.
Well, maybe let me off the top of my head, Bob. So that's the Univac 490. What is the time difference? Because we have a 1219 B. What is what is the difference between the two? I mean,
I believe it's only a year. The construction, we have a 1218, which I've looked at in detail. It's right next to our 490. I believe the 1218 and 1219 are both 18-bit machines rather than a 30-bit machine. When you look at the construction of it, it is a much denser, much smaller machine. It just looks like they got way better at constructing the boards and shrank everything, in addition to, of course, it being a smaller word length.
Yeah, because I know there's here that we're having is so let me ask another one. Do you actually have that one working, that 490, or is it just for? Like...
No, again, all we've done so far is James is building the testing unit so that we can test individual boards, and that's really the only step we've taken so far towards restoring it.
Because I know one of the problems we're having is that you have to have it on for a certain period of time before we stop having errors, and so it's like a warm-up period. And I was just curious to see if you had the similar problems.
So he's coming up, I believe, this next weekend to actually try and test a bunch of the boards. I think he's perfected his testing unit.
All right.
So he took a couple boards with him back to the Atlanta area. Thanks so much, everyone.
Thank you so much. And thanks for being able to connect with us via phone. I know that things are a little bit crazy.
Yeah, sorry. Our hurricane is coming up, and we had a mandatory evacuation from our vacation rental in Cape Hatteras. So my daughter's nice enough to be driving through a pretty nasty storm right now. My wife's in the back seat. We're evacuating vacation. Thanks, everyone.
Okay. Be safe. So
bye-bye.
Bye-bye. So Dave Babcock and friends and his team have been working on their IBM 1620 Junior project for years. They've been improving it over time. It's been so much fun to watch. He's brought it to a couple of the VCF Wests, and unfortunately couldn't bring it this year because we're not having it. But I'm going to let him via video show their progress on this machine.
Hi, my name is Steve Kastner, and along with my teammates Dave Babcock and Joe Frederick, I'd like to welcome you to the IBM 1620 Junior booth at Vintage Computing Festival West 2020. This is our fourth VCF, and we're excited to share with you the progress that we've made this year towards building a simulated card reader punch device for the 1620. The IBM 1620 was IBM's low-end scientific computer in the early 1960s. It was relatively inexpensive and was often used by engineering firms for design calculations and by schools to teach computing. The IBM 1620 Junior project has a goal of producing a technically accurate replica of the 1620 using modern technology. This all-volunteer project is sponsored by the Computer History Museum. When completed, the IBM 1620 Junior will be used by the museum's education department to let visitors experience hands-on what computing was like in the 1960s. There are four major parts to the IBM 1620 Junior: the control console, a software simulator, a console typewriter, and a simulated card reader punch. Starting with a real IBM 1620 control panel, our team replaced the incandescent lights with LEDs and plastic toggle switches with metal ones for durability. A Raspberry Pi 3B Plus processor provides the compute power. Custom-designed interface circuitry drives all the lights and switches, matching the real machine's varying light patterns and intensities. A new simulator is being developed. It's written in C and precisely mimics the IBM 1620 down to the machine cycle level, turning on all the individual lights on the control console. To recreate a reasonable facsimile of the 1620's console typewriter, our team modified an IBM Lexmark Wheelwriter 1000 electronic typewriter by designing a firmware-driven serial interface board to interpose between the keyboard and logic board. We developed custom keycaps replicating the unusual layout of the 1620's typewriter. At last year's VCF, our presentation focused on a side project to extend the console typewriter into a general-purpose ASCII computer teleprinter called Cadet Writer. Using our design and assembly instructions, several computer hobbyists have already built their own Cadet Writer for use with their favorite vintage machine. The final component of the IBM 1620 Junior project to be developed is a simulated card reader punch. Punch cards were the primary computer input and output medium in the 1960s and 70s. Real punch cards are not practical for our use today, so we're building a miniature simulated card reader using a text file on a USB memory stick to represent a deck of punch cards. These images show a prototype of that device. The final version will have a proper case, enhanced graphics and animation, and will play the actual sounds of reading and punching cards as recorded from a real IBM 1622 card reader. Now we're going to demonstrate what it was like to develop software for the IBM 1620. You would write your program in assembly language and punch it into cards, use an assembler to translate your program into machine code, load your program into the 1620 and run it, then debug any problems, revise your code, and repeat the process. Programs were typically written out on coding forms, particularly if they would be punched into cards by a professional key punch operator. Flowcharting was also often done first to work out the logic of a program before coding. Our replacement for key punching is to type the program in a text editor and save it as a file on a USB memory stick. The 1620 required a 20-minute wait after power on for the core memory to warm up. We won't simulate that. Next, we load the IBM SBS assembler into the IBM 1620 Junior. This is done by inserting the SBS's card deck into the read side of the card reader punch and pressing the load button. The computer now reads the assembler into its memory and starts running it. This takes a while because the 1620 was pretty slow. A modern laptop may be 1 billion times faster. Cards are read at a rate of 500 per minute, equivalent to a few hundred kilobits per second. We'll speed up through the boring part. Then we remove the SPS card deck from the output tray and insert our source program deck into the card reader.
The program switches and start pass 1 of the assembler.
Then pressing start begins the execution of pass 1 of the assembler. The source cards are read and an internal symbol table is created. To run the second pass of the assembler, our source deck is removed and reinserted into the reader. A memory stick representing a stack of blank cards is put in the punch side of the device.
We change the switches and we start the assembler pass 2.
The source cards are read for a second time, assembled, and the binary translation of the program is punched into output cards. The symbol table is printed on the console typewriter.
So pass 2 is done. We remove our source code. We take the punch binary deck and insert it.
We then take the binary card deck that we just punched and placed it in the reader.
We can run the program.
The IBM 1620 Junior is reset, so it's ready to start again.
Reset the machine. Load the demo program.
The load button is pressed on the card reader to read and transfer our program into the computer's memory.
And start the demo program running.
This simple program runs pretty quickly. The IBM 1620 can multiply two 1,000-digit numbers in one instruction.
And that's the complete demo.
That completes our demonstration of assembling and running a sample program that calculated 2 to the 234th power, which is a 71-digit number. The elapsed time was 5 minutes and 27 seconds. But as every programmer knows, the largest share of development time is spent debugging the program when it doesn't work correctly. On the IBM 1620, that was often done on the console. IBM 1620 programmers could use the console to step through the execution of their program one instruction at a time, or even one machine cycle at a time, and examine the processor registers to find where their code went wrong. And that's how programs were developed on the IBM 1620 in the 1960s. The IBM 1620 Junior team would like to thank the Vintage Computing Festival staff and volunteers for their contributions to the project. If you have any questions or comments, please contact us. Thank you for watching our demonstration.
And of course, questions and comments now are also welcome, at least for the next 5 minutes. Who's going to be running this, or do do I just leave it on thumbnail mode here?
Okay, we do have some questions.
Okay.
Why is it called Junior?
Because the original machine was the IBM 1620. It was about the size of a roll-top desk and had a lot of cabinetry and so on. And as you can see, Junior is just a smaller version of it, but it has the same full functionality of the original 1620. So we called it IBM 1620 Junior.
Okay. How is this model different from the IBM 1130?
So this machine came out in 1960, and it was a BCD machine. It was still a scientific machine that was used for a lot of engineering calculations and so on, similar to what the 1130 was used for. But the 1130 came out a few years later, and it was a pure binary machine. So different technologies completely. The interesting thing about the 1620, as a BCD machine, you could define your data fields that you operated on to be anywhere from 2 digits to the size of memory. So as the video mentioned, with just one instruction, you could add a 3,000-digit number to another 2,000-digit number, whereas the 1130 was, just a fixed word length binary machine.
Thank you. One more here. What made you decide to animate the punch card processing?
So the whole goal of the 1620 Junior project is to produce a machine for the Computer History Museum's education department that kind of recreates the whole experience of writing and debugging and running programs on a 1960s machine. And we chose to do it with a card-based machine, and clearly, mechanically, physical cards aren't practical for this machine. But we decided to make it look as much like the real thing, or to give you the same sense of feel of cards going through the machine and so on, rather than just have a static display. We think it adds to that visceral feeling of actually running card decks through a real computer, but with something that doesn't have the expendables and is something that doesn't have the mechanical problems that needs a lot of maintenance.
Right. I got one more here. How did you decide on the Wheelwriter as an I/O device?
Okay, very good question. So the original IBM 1620 Model 1 used an IBM Model B electric typewriter for its console. The Model 2 1620 used a Selectric typewriter, but both of those are basically electronic typewriters that they connected solenoids up to pull down the keys on the keyboard. And they're very mechanical. They're really hard to come by with that adaptation, and takes a lot of maintenance. The Wheelwriter was sort of IBM's next generation typewriter. It's a pure electronic typewriter, and because it's electronic, we were able to design the circuit board that fit electrically between the keyboard and the motherboard of the typewriter, and we can read the keyboard with that interface board, and we can inject fake key presses to the motherboard to do the printing. The other reason is that the Wheelwriter is a very reliable machine. They don't manufacture them anymore, but you can still buy them reconditioned with warranties. You can still buy print ribbons and paper off the shelf at Staples. So for an ongoing machine that's going to be reliable and useful to the museum for quite a number of years without a lot of maintenance requirements, we decided that the Wheelwriter was the best choice.
Okay. Oh, I got another one here that came in. Will the card reader punch get a real panel with actual buttons, or with the final version still require people to interact with the touchscreen?
The jury's still out on that. This is a prototype that we've done at this point. We need to do a real case. We're going to replace the screen with one with more resolution, add some sound effects, and we're still kind of discussing and deciding whether we're going to do real buttons and lights or the touch panel. We're not sure yet.
Right. Finally, this is just an easy one, technical question. What is the word size of the 1620?
So there is no word size.
Right.
Again, it's a memory-to-memory decimal machine, and you control for every operation, for every data field, how big that data field is. So you can have data fields that are as small as 2 digits in length, or you can have them that extend through the entire length of the memory. So there is no native word size, because the only registers in the machine are the addressing registers to get at the memory, but they're not user accessible. There's no accumulator in this machine.
All right. Well, thank you guys. I'm looking forward to hearing you guys' progress next year in a physical location if we get our virus under control.
That would be great.
It would be.
And by the way, thanks to Steve Kasner for producing that great video for us.
Yep, nicely done. And we've actually got in our next exhibit another sort of junior-ish project. Another homebrew retro, this time of a Nova 445. Steve Toner has got that sucker for us. So I'm going to transition to that real quick. Thank you.
Oh, hey, thanks for stopping by my virtual exhibit here for Virtual VCF West. Hope you're enjoying the show so far. And I really hope that next year we'll be back in Mountain View so that you can actually touch and feel these things. But for now, we do what we do. I call this the Nova 445. And so what's that? Well, it's a homebrew retro microcomputer, I guess you'd call it, that emulates a Data General Nova computer. Now, the Nova was a line of mini computers that Data General Corporation created, first introduced in 1969. 16-bit microprocessor, not a microprocessor, 16-bit mini computer. And then in the late 70s, Fairchild, which had a microprocessor division in Mountain View, came out with basically a Nova processor on a chip. This is the second generation, the 9445. The original was the 9440, which was also known as the Microflame. I think they dropped that designation when they came out with the 9445. But there it is. The interesting thing about the 9445 is it uses integrated injection logic, which is a high-speed bipolar technology, whereas everybody else pretty much was using NMOS at that time. So speed-wise, by comparison, there's the Fairchild chip, and here's a Zilog Z8000 from approximately the same era. This has a 1984 date code on it, and it runs at 6 megahertz. The Fairchild processor runs at 20 megahertz. So that's pretty cool. Oh, and of course, the Nova was the first computer I used and learned to program on and such. So it has a special significance to me. So one of the reasons that I chose to do this project. I'm showing it to you today as a work in progress. The full design has additional functionality, which I haven't implemented yet. This is specifically a real-time clock, a serial terminal interface, and a disk emulator. We don't have any of that right now. What we have is a processor and memory and some I/O decoding and a graphics board. So we can run code out of ROM, and we can display on this screen here. And that's about all it does. There's really no input device right now. It generates a standard NTSC video signal, which is displayed on a high-resolution monochrome monitor. We're getting 480 pixels by 240 lines of resolution, 240 vertical lines, 480 horizontal lines. And then there's also a minimal front panel here, if you want to call that a front panel. There's a connector that you can see, and which would allow for a full switches and blinking lights front panel. But for now, it's a minimal thing which just lets me reset the processor and start the code running. Code is in ROM, which is on this lower board, which you can't see right now. I'll put pictures of the individual boards on the screen so you can see them. Now, if you've been to the last two VCF Wests and you've dropped by my exhibits, you're thinking, oh, well, the demo is going to be TacoBot. But no, it's not. For two reasons. One, I already told you, I don't have an input device on this, although it would be easy enough to implement one. And two is that TacoBot is best experienced up close and personal, so where you can touch it and feel it and see it. We lost John Conway this year to the COVID virus. And so I thought it would be appropriate to implement Conway's Game of Life as the demo to honor him. So I've done a rather naive implementation of an unoptimized implementation of the Life game here, and it takes I'm going to start this up here. It takes about 210. It didn't start. I said I'm going to start. I said, there it is. Okay. Work in progress, folks. Anyway, it takes about 210 microseconds to compute each cell, which doesn't sound so bad until you realize that there's 113,764 cells, 480 minus 2 because of the outline, by 238. That's over 113,000. So it takes about 24 seconds to compute each generation of the game. And so it's going to tick along very slowly here. But what we'll do is I'll speed it up I'll speed up the video so that you can see several generations going by. And as the game runs here at higher than actual speed, and the cells begin to learn about social distancing, I'll say once again that I hope that we can do this live and in person again next year in Mountain View. And I'll hope to have the completed computer done at that time. And I'm hoping to have it running Data General's RDOS operating system, which will be fun. In the meantime, if you're interested, you can follow my build progress on my YouTube channel, which is called Martian Tech. I'll put that up on the screen there so you can see. And I'll have updates as I go along to let you know how things are going.
Very cool. And I can't remember how many implementations of the Game of Life I've done over the years. It's good to see. So, what questions do we have coming in for Steve at this point?
Okay, we've got one here. What was your greatest challenge with this project?
Greatest challenge was probably tracking down some of these old chips, the processor chips, and I went looking for them. I mean, I had this in mind, but these Fairchild chips are rather hard to come by, and so I did find a place that had some, and I bought 2 of them, and so that's.
Are these the 9300 series chips?
It's 9445.
Oh, okay.
9400.
Right.
I don't know. I'm not familiar with the 9300.
Right. Okay. Any software aspects that you'd like to mention? Or?
Well, I mean, I'm programming it in assembly language, which meant I either had to have a Nova with an assembler to write the code for it, or a Nova emulator. There is an emulator out there, the SimH thing. But what I chose to do is just hack up an assembler in Perl, which will generate the code, and then I burn it to ROM, and that's how I'm programming it right now. Once I get the serial port in, then I'll provide a means in the ROM code to load it over the serial port, and that's until I get the disk emulator going, at which point I can actually load things off of virtual disk. So,
well, since you mentioned disks, what disks are these emulating? The old flat Diablo stuff?
Yeah, it's a data journal called I think 4047, but it's the Diablo cartridge drives. What are they? 2.5 megabytes or something per disk. And yeah, my current thought is to emulate it with MRAM, so it'll be wicked fast, rather than using Flash or something, which is probably what most people would think of. But I haven't gotten to that point yet.
Thank you.
And for input in your full front panel, are you gonna go for the old school look and feel?
If I do a full front panel, then yeah. Now I've seen occasionally show up on eBay actual Data General Nova front panels, and it might be possible to come up with one of those. But yeah, it would be well, if you remember 2 years ago when I brought the stupid computer, which was a 12-bit homebrew computer, TTL based, that it would be kind of like that, switches and blinking lights and stuff like that. And oh, by the way, Dwight, you can see, I think here, I've had to make some mods myself. Everybody goes through that. It's even worse on this other board. Yeah.
All right. Are there other questions in the pipeline, Doug?
One less. Oh, yeah. Yeah. Well, they come in fast, don't they? Okay. Okay. He says he's got a few questions. Where did you get your Fairchild 9445s? Or more to the point, where can I get a 9445?
You can't. I got them, let's see, electronicsurplus.com, I think it was the name of the place. And they're all sold out of them. But they had a number. I bought some used ones. They had some used ones and some brand new ones. And the cost of 2 used ones was less than the cost of a single new one. So I bought 2 poles. And they both seemed to work. So I think I did okay there. They cost me like $25 a piece. Now, as I recall, when these chips first came out, the price for the chip alone, for the processor chip, was like $150. I wanted one back then, but it was much harder to buy things like that because we didn't have the web, and so it was a matter of finding a distributor, and finding a Fairchild distributor it was not something I could do at that time.
Right. Okay. David Guesswine asks, how many instructions per second could it do with a 20 megahertz clock?
Well, let's refer to the documentation. 16 by 16 multiply, 3.5 microseconds. Let's see. They give the cycle time, instruction time is about, I think, 300 nanoseconds for like register to register operations. I'm running with fast RAM, so I have no wait states on my RAM, so that doesn't slow me down. But it's faster than a Nova 800 series, which had an 800 nanosecond cycle time, maybe about the same as the Supernova, which was a faster version that Data General made that had semiconductor memory rather than core memory. Whether he's considering using, I'm seeing a question online, whether he's considering using an FPGA as part of his homebrew system. Oh, well, that's a good question. I'm trying not to. I'm trying to keep it pretty much vintage. I think I said in the video, I don't have a cutoff date, for the chips I use, but I'm trying to keep it to the, at least the 90s and earlier. So I prefer to do TTL and NMOS, but when I get to the disk controller, that's rather complex. That's got to fit on a board that size, and it has a whole bunch of registers and stuff. And so I'm not sure I can fit it. I've already, basically, I moved I had the plan for the board, which would have the disk controller, the real-time clock, and the serial port on one board. And what I've done is I've made a second version of this video board. And can you see that? Okay. Which doesn't have the cutout, and put the serial controller on that, and then it'll have to go underneath rather than on top. But that cutout is there to make space for, well, there's a resistor here, which is acting as a current source and gets quite warm. And then, of course, the front panel plug-in, which is, makes a three-dimensional thing there.
Sorry, Steve. I'm going to cut you off. We're a couple minutes over, and Any additional questions or any additional comments we can catch up with at a later date. But I may have a solution, or rather, Turk may have a solution, and I'm sorry for butchering the name if I did, for finding those processors.
Hi, welcome to Vintage Computer Festival 2020 and the session for my project Retroshield for Arduino Mega. As you can see, Retroshields are small daughter cards plugged into Arduino Megas. A real processor executes your code while Arduino emulates the rest of the system, such as the ROM, the RAM, UART, and storage. If you like to modify the design or even run a different platform, it's as simple as downloading new Arduino code. You could also use existing Arduino shields to add new capabilities. You don't have to mess with wiring complicated circuits. My goal is to build a daughter card for every vintage processor out there, starting from the earliest to the latest. And in the past 1.5 years, I built cards for 7 of them: 6502, 6809, Z80, 8031, 8085, 1802, and Signetics 2650. You can visit the project website by going to www.8bitforce.com. From there, click on the project's link at the top and select Retroshield. There's also a link to the GitLab repository for software and hardware details. Now let me show you how it works and give you a demo. Arduino continuously toggles the clock and monitors the read-write and address lines to figure out what the processor is trying to do. Depending on the read or write, Arduino will either drive the data bus or latch data from it. We can also assert the interrupt signals as needed. We use Arduino's internal flash and RAM to emulate the memories. Of course, all coding is done in a simple Arduino IDE. Arduino is cheap and simple, but it has 2 limitations. First, RAM is limited to 8 kilobytes only. Second, speed. For simple bus transactions like 6502 and 6809, we can get up to 200 kilohertz. However, for processors that take more than 1 cycle per instruction or have complicated bus transactions, speed is only acceptable to learn the instruction set. To overcome this, I designed Retroshield to Teensy adapter board in the Arduino Mega form factor. Using a Teensy 3.5, we get up to 256 kilobytes of RAM. Speed is also greatly improved because Teensy runs at 120 MHz versus 16 on Arduino. As a result, we can clock the processors at their target speeds. The really nice thing with Teensy is we also use the existing Arduino IDE to write our code. This is the code for Apple I using 6502. Let's look at the CPU tick function, which is where the action is. So we set the clock high, we read the address lines, and then we check the state of the read-write signal and perform a read or write. I will let you download the code and study the details. Let's run this and see what happens. I use TerraTerm for terminal program, so let's get Arduino connected. And you can see Arduino code printed some configuration details, some notes about how to use it. We're going to run the Apple Basic. To do that, we type E000 run, and we get the basic prompt. We do 10 for I equals 0 to 100, 20, print I, 30, next I, 40, end, list, and run. This is all being run by the actual processor, and everything else is emulated by Arduino. How cool is that? This is the code for emulating Commodore 64 BASIC using the same setup. See, I haven't done any like wiring anything. I'm just going to download this new code and play with Commodore 64. Are you ready? So Commodore 64, we only get 4K because, you know, this is Arduino. We can do print. And we say run. There you go. If you remember on Commodore 64, you could go up with the cursor and change the code. And when you enter, it updates to line 10. So if I hit enter again, it's going to run the code that I just changed and watch for hello. There you go. And this was done with Michael Stell together. He is a guru on Commodore 64 ROM. We had to do a lot of hacks. But see, I did nothing. I just changed new code, and I can run Commodore 64, I can run KIM-1, I can run Apple I, and same thing for other microprocessors. There's one more thing I want to show you. It's a surprise guest for the next processor I'm working on. Earlier I mentioned I was going to do a daughter card for all the processors starting from the very first till the end. And here it is. I'm working on the Retroshield for Intel 4004. I'm still working on the code, and I expect the hardware to be finalized at the end of the summer, but I have it working on a very, very simple manner. So let's run it and see what happens. We're running a simple code, adding two 4-bit numbers together, and at the end we halt by jumping back to address 5. I have debug messages turned on, reset the processor, wait for the sync signal from the 4004. Once we latch onto it, we let it go through X number of CPU cycles, and then we release the reset, and you can see 4004 starts executing at address 0, then 1, 2, 3, 4, 5, 6. And since the last instruction is a jump back to 5, you see the address gets stuck between 56, 56, 56, 56. So I'm super excited to have the very first processor running on Arduino. My goal is to build the daughter cards for 8008, 4040, and then do 8080. So we have the whole Intel series. I call this process breadboarding in software. I hope it makes sense why. My website has everything you need to build one, including schematics, layout files, and the Arduino code. If you have any questions, please do not hesitate to contact me. I'm now going to go back to my microprocessor pets. See ya!
Nicely done. I see Dag got back. Did we have any... uh-oh. I think Dag's bouncing back and forth.
I'm back.
Oh,
Okay.
Okay.
No messages so far.
So
I'm not...
Go ahead.
I can give a question.
Please do.
I can give you the code that runs on the 4004 for the maneuver board here, but you'll have to come up with some way of displaying things. I guess you can output stuff through the USB to your host computer, I think, and then so you can actually run the real 4000 code to actually calculate where your ship is going.
So that'll be good. Yeah, Dwight. I would love to. I don't know much about the 4004 code right now. I'm, learning the instruction code. I did study the hardware simulators on the 4004.com, so I have an idea of how the low-level signals work. But the next level, we can build some 7-segment displays for Arduino and run your code.
Stephen Edwards just asked a question into chat. Did you want to ask that out loud, Stephen? Or should I pull up? Whoops. That one.
Yeah, you better. I can do it. Have all the processors you've worked with use 5-volt TTL I/O? Do you have a plan for some of the stranger processors?
Yes. So most of the latest processors are 5-volt only, so a direct connection to Arduino is okay. But the earlier ones and some weird ones, they may, or strange ones, have a different voltage levels. One example is this 4004. It operates at, if I remember, the VDD to VSS delta is 15 volts. So I have to use level shifters between, the micro and the Arduino. So I don't have any limitation right now. As I go, I will understand what needs to be done and do the level shifting and make sure those processes run.
And does your Teensy board have level converters?
Yes, that as well. So Teensy is a 3.3 volt only device. I looked at all the processors, the I/O levels, and I need level shifters. So I have level shifters from 3 volts to 5 volts.
Okay. Will this work with Atari 8-bit computers?
So Atari uses 6502, right?
Yeah, but a lot of other
so it
chips.
should work, yes. And I do use, you can get the VGA shields for Arduino. So you can have the Arduino connect to a monitor and you can connect keyboards. I do have a Commodore 64 version that actually, connects directly to a monitor with a keyboard. So that way we could also emulate the Arduino. Sorry, we can emulate Atari with that.
Right. And next question is, this one is 256K. Do you plan on doing larger implementations?
So for large, currently Teensy has 256 kilobytes of RAM, and that's enough for me. We could do like bank, switching or like implement the OS stuff. If we need more, we can look at, I'm sure we can hook up some other ways to do it. Hook up a standalone RAM chip or use SPI type of RAMs. But we can do more, like we can connect to Arduino.
Right. Thank you.
Yeah.
At some point, we'll be able to emulate like a Win 10 machine.
Eric, can you switch my video on for just a sec here?
Sure. Hold on 1 second. Oops. I got to admit someone first.
Okay.
And pin, not mute. Go ahead.
Okay. You need one of these little cards like this for your 4004, so you can program it.
Hold it up a little bit higher.
I don't know. It's not about there. Yeah. A little
Cool,
pocket.
yeah.
One of these little pocket things. Yep.
Okay. Yeah.
Yep.
Nice. I'll show the $4,000 card quickly.
Yep. Now, the other thing you should know about the 4004 is that that being PMOS, the 0 level is the stronger level, and that's at the high, if you're using a 5 to minus 10 range, which is the way most people do it. The 0, the hard pull to 0 is to 5, and a soft pull is to the negative voltage. So the negative voltage, you don't have to go all the way to minus 10 for the logic. You can go down to, about 10 volts below minus 5. So you don't got to go all the way down to the full 15 volt range for the logic levels. It's kind of like TTL backwards, upside down.
Okay. Thank you very much. Oh, go ahead. Yeah, no, show us the daughter card.
Yeah, let me show you the card just a little bit. I'll talk to you, Dwight, offline. Did it come up?
Yep.
So I have 2 slots in here. One is for the processor, and the second one is for the ROM or the RAM. And the way I program it is, if you have just a processor, then the Arduino will emulate the ROM and the RAM. But if you have a ROM and RAM, you can do together as a set. Or if you have just the ROM or the RAM, you can have Arduino like read it or access it and test it. That's my goal there. And then I have the LEDs for the ports.
That's a great idea. I like it.
All right, and we're kind of out of time, but I wanted to thank you again. I also want to remind folks that we are accepting our questions through microphone at VCFed. We just learned that for some reason some of our questions have been vanishing into the spam folder, so now we're going to check there as well after each one of these talks. That said, we're going to have Bill Mensch and Stephen Edwards talk about the genesis of the 6502 for quite some time, and then we've got another Bill Mensch talk right after that. We'll take questions in between these two.
I'm Stephen Edwards, and I'm here with Bill Mensch, who's going to talk about the genesis of the 6502, something he was very intimately involved with. And I'm going to do this by showing a series of relevant images and start off by saying, what are we looking at here, Bill?
Well, that's the center of attraction, the 6502 microprocessor that changed the world.
Definitely one of my favorites. And so broadly, this is sort of the time is 1974, 1975 when all this was happening?
Right. Yeah. 1974, we started planning our escape from Motorola. And then we ended up at MOS Technology on August 19th, 1974. Chip was introduced in September 1975.
So speaking of Motorola, I have what I believe is one of the Motorola buildings. Can you tell me a little more about this?
Yes, I think that's the Motorola building that was at Broadway and Dobson in Mesa, Arizona.
Mm-hmm.
And that's where we designed the 6800 product line, the family.
Okay. And so that's this chip here, the 6800 series.
Correct. And that one, the 6800 and the 6502, are in the American Technology at the Smithsonian. So they're side by side in the Smithsonian.
Very nice. At least two of your babies next to each other.
Right.
That's nice.
Right. Yeah.
So you were part of Motorola when you were designing the 6800, and some other members of your team were there as well. Is that correct?
Correct. Yeah, there were 8 of us that left Motorola, all in force. We were actually the second group of 8 people to leave Motorola. The first group went to Fairchild. We went to MOS Technology.
Oh, okay. Interesting. And so MOS, that's this, here's an MOS building, I believe.
Correct. On the second floor there, you see those windows starting from left going to right.
Mm-hmm.
The Vice President of Engineering, his office was on the left-hand side. There was a conference room on the next to his, and then our team offices were down the left-hand side of the building that you do not see.
Oh, okay.
Yeah, that one right there where you're pointing out, that would be the Vice President's office and the conference room.
Oh, okay. Oh, neat. Sounds good. So tell me a little bit more about MOS Technologies. I think this was the management team at about that time.
Correct. They're the founders. There are 3 of the founders. I'm not sure if, I think the 3 founders were John Pavinen up in the upper left-hand corner. He was the friend of Chuck Peddle that actually closed the deal because they worked together previously at General Electric. I think Don McLaughlin is the second one down on the left. And then the third founder is Mort Jaffe. He's in the upper right-hand corner. The process engineering manager, Walt Eisenhower, is in the middle on the right. Mm-hmm. And Don Payne, instrumental in building the mass shop, which was very revolutionary in my mind. But Don Payne is in the lower right-hand corner.
So why MOS Technologies? Why not stick around at Motorola and strike lightning twice?
Well, Motorola was planning to move us to Austin, Texas, and some of us didn't want to go to Austin, Texas. Arizona is beautiful. Texas is kind of flat. And so then we're also looking at doing something revolutionary that Motorola didn't want to do. And that was do a low-cost CPU. They already had theirs, a 6800. So to do another one better than that at another place seemed like the only way to get the job done. So MOS Technology, we were fortunate because I don't think Chuck actually knew how awesome of an opportunity it was to go to MOS. He could have. I don't remember that being the case. I was quite surprised to find out this team was doing so well in calculators that could be easily translated to our microprocessor designs. And so it was, that was an amazing company, very small, relatively small, and very quick turnaround time for mass and wafers. So it was I don't know, a breath of fresh air coming from a big company like Motorola.
Well, I'm sure. But moving to MOS also involved a rather lengthy move, though, didn't it?
Well, yes and no. We all decided to give our resignation letters and then all move on August 19th, 1974. The interesting thing is when the salary stopped at Motorola, all of our salaries started the same day at MOS. So that was a gift. Our moving expenses, I didn't move my household that I remember. We just kind of moved and set up house in first an apartment, and then we bought a home later. But it was a small, what would be considered a row home back there. But anyhow, but we didn't move all in the same moving company or anything like that. We kind of moved individually, but we were meant to show up there the next week. And so we showed up at the offices next week, and we got to know our new company we're going to work for.
Oh, that's interesting. Valley Forge, Pennsylvania. That sounds like quite a switch from Arizona, though. Although you had some connection with that area, right?
Correct. I grew up in Bucks County on a farm, dairy farm. So actually, I'm going home. So I'm the only one that's going back to where I started. And so it was kind of fun to, I mean, this was not planned by me. Chuck is the one that selected MOS Technology. I don't even think I knew there was such a company. There was one other semiconductor company in the area, but I wasn't aware of MOS Technology when I was back there. And I guess they started. So that's a company I could have worked for if I knew they were there, but I didn't.
Interesting. And so that was where the 6502 was designed, implemented, fabricated, all of that good stuff, huh?
Correct. Yeah, we designed it from the first silicon up, and so we had to bring up the NMOS depletion load process and do all the design, and it was just 1 year of very active work. And not only did we design the 6502, but we wanted to introduce two chips. One was the 6502, and then the peripheral chip, which made a two-chip controller set, and that was the 6530, which has ROM, RAM, I/O, and timer, and that went with the 6502 to do various kinds of projects, control projects.
Oh, very interesting. Yeah, no, you definitely would want support chips. So let's talk about that group that crossed the country and set it on fire. I think I've got an image here that summarizes most of them.
Correct. So the two people that are in the picture that were there when we arrived, Walt Eisenhower was the process engineering manager. And so he was the brains behind the process itself. Terry Holt in the middle sitting down, he also was process and production. One of the members of the team came from Motorola. So he understood the NMOS process. Now, Motorola didn't have a depletion load process, although I did design the process control monitor that monitored all the wafers for all of the Motorola family of chips. So that process control monitor, I did have both the enhancement mode load process control devices, and also the depletion mode load control devices, so that I could see the comparison, and I did that so that we could at Motorola move to the depletion load process, which we knew would be a next generation process. Well, Motorola, this is another reason why we left Motorola. Motorola really didn't want us to design with the depletion load, and even though I designed the process control monitor for it, they were reluctant, and finally did. After 6 months of my trying to get them to run it, they did run it. So we did gain some understanding of the depletion load process before we left Motorola. And so then Terry brought some of that understanding to MOS technology, which helped with getting the production set. Now, on the right side is the president of the founding member and president of MOS, and he was the contact person for Chuck. They worked together at various companies, GE, and then again after MOS and after Commodore, they got it hooked up again. But anyhow, going back to the team members there, next to Walt on the left is Will Mathis, and he was one of the design engineers. He was logic design and application. Then next is me. I was a semiconductor design engineer. Rod Orgel was semiconductor design engineer as well as logic. Rod and I are the key guys that actually designed the chip from an engineering standpoint. Ray Hurt is a design engineer, and he was the designer, the lead designer on the 6532 chip that was used in the Atari game system. He and I worked on the 6532, but Ray was really the key guy that would carry that. Those circuits on the 6532 were designed that used the 6530, which I was the designer of. So then next is Chuck. He was we called him the ringleader. He was also the instruction set architecture lead. He was the systems lead, marketing lead, and just overall program lead. Next was Harry Bauckham. He was a layout designer. Then Mike Janes was a layout designer. Then we have another team member that was part of the team, and that's Sid Holt. And we found her back in Princeton, and so she joined the team after we got going there. So that's the basic team. We were a fun team to work with. We were very synergistic, and we loved our time creating the 6502 together.
Looks like quite a group. I've heard many differing stories about, oh, it was the creation of one person, it was the creation of a bunch of things, it was a copy of this, it was a complete invention. So this looks like a pretty wide, pretty diverse group of folks working on this. How would you say this, the size of this team would?
Well, relative to today's standards, it's a very small team. I mean, we might have a couple hundred engineers working on an Intel processor, but these were smaller chips, smaller processors. But this is just basic minimal number of engineers and layout designers to do the project. So this is a very small team for its day. Motorola's team, now, as it turns out for the PIA, myself and one layout designer designed that in about 3 months. So actually, I was used to working on a small team, and I enjoyed the small team. I enjoyed the total control over what we were going to do. But we all knew our lanes, and we didn't get out of our lanes for the most part. Chuck, as an example, he was all over the place as far as working with the management team and working with us as design engineers. And he was always involved in various ways, but he stayed in his lane because he really wasn't a semiconductor engineer. And so therefore he just worked with Rod and Will and myself somewhat on the instruction set and what we're going to do with minimizing the circuitry so that we could have a smaller chip than the competition, lower cost than lower power and all that. So we stayed in our lanes as far as engineers and layout designers.
Continuing this theme of trying to make things as simple as possible, I wanted to get a little bit more technical about the internal details of the 6502. So this is its perhaps infamous programming model, which seems very, very minimal, especially by my modern eyes and so forth. Tell me how this came about.
Okay, so as with anything these days, it's an evolution, right? And so it starts with an instruction set that was successful. So you look for successful predecessors of what you're doing. So in the case of the 6502, what came before that, Rod and I completed the Olivetti desktop CPU, which was sold by Mostek. It's Mostek out of Carlton, Texas. They were the second source. Rod and I finished the design, and then it was licensed to Mostek to build for Olivetti. That had some interesting features in the Olivetti chip. So Rod and I knew the Olivetti chip to get it successfully completed. And so there were things like zero page was something that was successful with the Olivetti chip. That was carried forward with the 6800. So the 6800, we're not going to show the 6800 register set today, but it had two accumulators. So it had an A and B accumulator. It had one index, 16-bit index register. So the Motorola 6800 as a predecessor to the 6502 had two 8-bit accumulators, one 16-bit index register, 16-bit program counter, an 8-bit status register. So actually, when you look at the 6800 as a stepping stone to the 6502, you'll see that we learned from the 6800 that two accumulators isn't as valuable as one accumulator and two index registers. So if you look at it that way, we actually have in 8-bit register format, we have one less 8-bit register, one less 8-bit accumulator. We have the same number of registers for index registers. And so you end up having a different structure that would actually work more effectively in programming for controllers. Now, an 8-bit stack register that's put in page 1, and we have page 0 for quick access to registers, which I call addressable register architecture. This system here builds on the experience with the earlier processors that Rod and I worked on. So we knew what was a better register set than what we had experienced earlier. So that's kind of going on.
That makes a lot of sense, definitely. Oh, and you mentioned specifically controllers. So at the time, the plan was not to, say, take on the PDP-11s of the world, but rather the printers and other things. Is that
correct? Yeah, and Chuck's experience with some small control systems, like he worked on a point-of-sale terminal and some of these other kinds of systems that he would see that some of his control systems that he worked on before joining Motorola, he knew what we needed to be an effective controller. Now, the 6502 and the 6530, our target competitor was not the 6800, was not the 8080. It was a 4040. So Intel had a 4040 chipset, two chips, that was selling for $29. So actually that was our target. It wasn't PCs. It wasn't these other things that it was used for. It was simply a good controller. So Chuck's idea of building a CPU for control systems was what he saw as what we were trying to accomplish. Now, when I suggested in December of 1973 that we could build a home computer out of the 6800 plus the PIA, that's another part of the story here. The PIA plus RAM and ROM, you could build a small home controller or home computer. And the reason why I was thinking that way is because the PIA, which I designed, was to drive solenoids and other signals that would be useful in controlling a home environment, turning on lights, turning on sprinklers, turning on things like that. And also, you could program it to do, low-level accounting and other things that you might find that a user might want to do. But anyhow, that was when the Hewlett-Packard 35 calculator or whatever that had some fixed functions. So you can see when I'm thinking, why don't we build something that would go into the home? Well, Chuck wasn't interested in that. And he kind of wanted me to not really talk about a home computer because in some ways, I think he knew that was going to happen. But at the time, he was saying, we're just doing controllers. So this was what the intention was. Now, if you look fast forward from 1974, 76 to today, I'm still in the controls business. I'm still building controllers because there are a lot of controllers out there. There's probably orders of magnitude more controllers than PCs and game systems. So anyhow, I'm still a controller guy. Chuck went on to build systems.
Now let's talk about the layout of the 6502. I have here a photomicrograph of the 6502 die that came from the Visual 6502 group. I can see some big structures here. Can you take us through some of these?
Well, okay, if we start wherever we want to start, if we want to start at the top, there's what looks like a ROM, but it's really like a PLA. And so that was that would be what I call on my CMOS, I call that the min-terms. So if you're looking at logic design, there's a min-terms and then there's a sum of min-terms. So partially decoding an instruction with the timing state. So on the left of that, facing it, the left of that is where the timing generator is. And so for the 6502, we needed three bits, which would create 8 timing states. And we only used 8 timing states, actually 7 timing states for the 6502. So like for in my 816, I have more states, so I have actually 4 bits or 16 timing states possible. Now, what happens there is you have a timing state and you have an opcode. So on the right of that is where you have the instruction register. And so you have the instruction loaded during the opcode fetch, and that is decoded partially in that ROM pattern or that PLA, which I call the min-terms. Now the logic below that, until you see the middle of the chip approximately, that's the transfer gates. Right there, what you're showing, that's the instruction decode, which if you were looking at my CMOS version, that would be the sum of min-terms. But in this case, we didn't use that technique. We used just logic that would then complete the decode for the timing state to control the transfer gates that are in the middle of the chip. So you see a row of gates right in the middle there above the data path. So those are active when you want to transfer, let's say, from the index register to the ALU and transfer some other signals back and forth. During each of the timing states, we know what we want to do, and what how we document that is with a flow chart. So we have a flow chart. On the flow chart, it tells you what's going on in each of the timing states of every one of the 151 opcodes. So now let's talk about the data path. So if you look at, so the top of the chip has the control signals for read write. We have the clock generators, we have the interrupt inputs, we have other unique signals such as sync and what else do we have there? Well, in the upper right hand
interrupt.
Yeah, those signals I call the control bus. Okay, then we have a data bus, which is 8 bits, and we have an address bus, which is 16 bits. So on the right is the data bus. That's where all the data comes and goes from the processor. So if you're loading the opcode, it comes through the data bus. If you're loading an address and for 0 page, it would come the next cycle on the data bus. If you're loading absolute address, then you would have 3 cycles, one for the opcode, one for the low byte of the address, and one for the high byte. An important thing about the 6502 that was not carried forward from the 6800, and I'm not sure how the 8080 worked, but the Motorola design marketing group chose to have the opcode followed by the high byte of the address, which means you can't do anything with the address like load or add a index register to it. So what we did is we put the low byte of the address. Now we can add the low byte, the address, the index register to the low byte of the address for index absolute, and then the next cycle you bring in the high byte, and if you had a carry out of the low byte, you could increment the high byte of the high byte of the address. So now that means that we were looking at things that would save a cycle here and there, and that's why the 6800 was kind of a whatever. They just didn't do the right thing there. But we knew that, and so that's why the 6502 works faster than the 6800 in that case. Now, if you look at the chip, we have of course, the buffers and the latches for latching the data coming in and latching the data we're going to put out on the out on the data bus. That's right next to the pads there. And then next we have the program counter. Now, in the case of the 6800, they had both an incrementer and a decrementer on the program counter because they didn't realize that if for single byte instructions, you have to prevent the program counter from incrementing beyond the next byte. So on the 6800, it incremented and then it incremented again. So then they had to back it up, and that means they had to use a decrementer. And so what we did was we had look-ahead logic so that we knew whether we were going to have a single byte instruction so we could prevent the program counter from incrementing. That's another speed-up technique. Less transistors used because we didn't have the decrementer. So then following across, then I think we had the ALU, and then the ALU with the decimal correct. The decimal correct actually added, I don't know, 6 mils or whatever it was. It was actually more significant than the value of it apparently, because decimal math wasn't really that necessary. However, I wasn't the one that actually chose that, but I know that it ran into problems for other things. So anyhow, then moving across, I think it might be the stack pointer next, in X and the Y register. I'm not sure which sequence it was. And then you have the low byte of the address. So you can see where you're bringing in a 0-page address, you can transfer it right across to the address bus. So that's how we reduce some of the delays in the system. And then the high byte of the address is the ones on the bottom of the chip. That's basically the data flow from right to left. Now, there's another thing. The adder is in the middle because you're going to take some things like from the program counter or from the, I don't know that we put anything from the status register, but you would have coming from the pictures right, you have some variables or some register values like program counter. And if you're going to add the index register to it, then you want to put the index register to the right. Also, when you're doing, a compare or an add or a subtract or a logical function from the data coming in from a memory, then you bring that in from the right, and you want to have the paths built into the ALU so that you can do all these operations with the number of buses that carry that information. So we had a special bus, we called it a special bus, that we had carrying the information from the index registers and the stack pointer into the ALU. It's what was needed to get the job done.
This was part of your design flow somehow?
Correct. And so you saw a portion of the logic or the schematic of the microprocessors. So everything was put in a big sheet. There, you can find them online, but we had the top half of the schematic and the bottom half of the schematic. And so that was the floor plan for everything we wanted on the chip. So that means that Harry, Mike, and Sid took that schematic and placed the circuitry that they laid out converting it from the logic schematic to the actual physical layers needed to build the chip. I forget how many layers we had. We had the diffusion, we had the poly gate, we had the contacts, we had the depletion mask, and we had the metal mask. And so we had, about 8 layers or so that the mask designers laid out simultaneously so that they could build the whole thing on one layout. So that layout, if you make a mistake, then of course you can erase it. But we were designing it on Mylar, which is like plastic. And so it was done on Mylar because of the temperature coefficient of the paper, and also the humidity. So if you use regular paper, it could change in size based upon the humidity and the temperature, etc. So when you want to be accurate, you need to have a stable, and sometimes they called it stabling because it was a stable medium to design your circuits on. So that CALMA system there has that thing on the left that's hanging down with the wire. I think they called that the puck. And that was where you put that on the coordinates. So every shape, it's all rectangles. We didn't do really any circles or anything like that. They're all rectangles. So a contact would be a rectangle. Each of the poly shapes would be a rectangle. Now they can go north, south, east, and west. So actually, it's all rectangular drawing, but each of the corners of the rectangles had to be entered into the system and stored on the disk. So they used a puck there that would actually be on each of the coordinates of each of the rectangle's corners. And so there's a thing up in the right-hand corner of that's where you could look up as the digitizer. So we had a person that just did digitizing. The layout designers just did the layout. The digitizer then was skilled at doing the digitizing, and they'd look up there to make sure that the coordinates were online and that he wasn't partway between boxes, etc. Now the terminal that you're seeing there has a screen on the left of it. There's 2 screens in that under that hood. I think the left screen is the bigger screen for the actual layout, showing you what you digitized. On the right screen was like a command line. And so that's the way we digitized it. But the key part was the layout, converting this logic into the actual layers. Now I should mention one of my other best layout designers I'm married to today. And she also does the extraction. So she's like, we have physician's assistants, we have nursing assistants. Well, I created engineering assistant. That means that not only does she do the layout, but she also does the netlist. And so we can do a netlist extraction, but you need to know that the netlist that's extracted these days matches up with what was intended. So she also loads the logic in and has the netlist manually created. But so this digitizing approach we actually use also for our schematics. So what's interesting, we didn't do that at the time. So all those schematics were hand-drawn and remained hand-drawn. But today we use GDS to not only capture our schematics, but also the layout.
So let's talk now about how the 6502 started to take over the world. So I have here an ad that was advertising MOS Technologies presenting at this conference called WestCon 75. And it's interesting. It seems to be talking about the 6501 more than the 6502. Can you tell me a little bit more about that and what happened at this conference, at this trade show?
Right. Okay. So one of the things that happened with what Chuck's marketing plan is we're going to steal sockets that were created for the 6800. So the 6501 was pin compatible with the 6800. That means that they're both same pin out, 40 pin package, And what happens is the Chuck's marketing plan was, because we only had a couple salespeople, Motorola had a lot more distributors. So we're going to go around and find the customers. We're going to market and just say we can plug in the 6501 into the 6800 socket, and that's how we're going to grow the business opportunity. Well, one day when we were, probably about May timeframe, I saw that, why don't we just put the clock generator on the chip? That was not what Chuck had planned. In fact, it was counterproductive because his marketing plan was to steal sockets from the 6800. All you have to do then is recode in 6502 and you're good to go. It's a better system. Everything would work out better that way. Well, Motorola didn't like that idea. And so, but luckily when Chuck came back from one of his marketing trips, I said, hey, Chuck, why don't I put the clock generator right on the chip? I actually, while he was gone, I actually had the layout designers lay it out that way. And he says, well, as long as it doesn't affect the yield. I go, no, it's going to have the same basic, it's going to be the same die size, same everything. It's going to have a few more transistors on it, maybe a dozen transistors or so. But I'll hide them under the metal. Well, as long as it doesn't affect the yield. No, it's going to be the same thing. All you have to do is have a different metal layer for the 6502. You have the 6501 metal layer, and you have the 6502 metal layer. So it'll be basically you won't see a difference in the yield. Okay, so Chuck said, okay. I said, well, actually, Chuck, it's already on the chip. So that's how the 6501 is being advertised here, because the plan was to steal sockets from the Motorola 6800. So now the 6502 is also there, and so we can charge a little premium, even though the yield would be the same. We can charge a premium. So the 6501 was sold for $20, and the 6502 was sold for $25, but the cost was the same. Everything was the same, so you're actually making more money with the 6502.
And I understand this show was quite a hit with the among the people who attended, who swarmed your booth or something. I've heard all kinds of stories about this.
So
this trade show.
Yeah. So what happens is it was at the Moscone Trade Center, and so they had a second floor, and you could look out over the exhibit area. And what you could see that day or that weekend when we were exhibiting, you'd see all these people flocking to our little booth. And we just had the smallest booth because we don't have a lot of money. So we had the small booth. Well, there was the neighboring booths, they were being overrun. And I remember there was a pachinko game set up in the booth, which would have been to the right of facing our booth. And every once in a while, somebody trying to get to the data sheets and get their card. What we do is take a card and pass it over to someone scanning the card, which was just like a credit card reader. You just imprint it, and then you'd hand it back, and we'd hand them maybe a data sheet. And so this was going on for hours, all trade show long. We're going back and forth. And what we agreed that we would trade shifts. So Rod and I might be down there doing this for a couple hours, and another crew would come in and do it for a couple hours. Well, every once in a while, somebody that was trying to get their card scanned or the data sheet would knock over the pachinko game. And of course, they were just not happy with us. But anyhow, that was one of the most amazing experiences. And for design engineers to be there on the floor with the customers, with the people interested in what we had designed, it was just like designer heaven, where this is just joyful. And so then what we'd also tell them, hey, why don't you come back to the St. Francis Hotel? We have a suite, I think it was the MacArthur suite at the St. Francis Hotel. Why don't you come over there? We got some beer. You can see us over there. And after this exhibit shuts down, we'll be set up there. Come up there, buy a chip from us, do what you want to do, but you're invited. Anyhow, it was just one of those special times, and of course, Rod and I had a few beers celebrating. Yeah, it was a little family gathering there, but that's the 8 members of the team that left Motorola. I don't think Sid's there. That's interesting, isn't it?
Yeah,
So
I don't
Sid's
see
not there. We didn't have anybody. We didn't have anybody from the management team there. So this is our big party. This is the big celebration of after the show party and all that. You see on the left, there's Harry. Then you see next to Harry is Chuck, and then Will, and then Ray Hurt is in the back there, and then there's Mike Janes, and then there's Terry Holt, and then there's myself, and there's Rod. So I don't know why Rod and I are separated from the others, but you can see some of the relationships there. But Rod and I were really close friends, but we didn't get together socially except a couple of times. But we worked together, and he was my mentor, logic mentor. And he taught me about De Morgan's theorem and bubble matching and other things that just he was just a very special person.
That's great.
And I want to. This might be a good time for me to say it's with sadness that we lost Chuck last December 15th, and also Rod in 2012, I think, 8 years ago. And Terry Holt's not into his medical condition is somewhat tenuous right now, and his daughter built something that I think will show at this at VCF West maybe, and it's a website, team6502.org, that Terry's daughter put together, which is really a wonderful tribute to Terry and the rest of the team.
You know, what can I say? Thank you from all of us for putting together something that changed the world.
Well, you're very welcome, Stephen. And I want to thank you for inviting me to be a participant here with this Vintage Computer Festival, Federation Festival.
Yep.
It's just really special to be around people that, it's always special to be around people that enjoy your work. And I appreciate the opportunity.
That was the first of 2 Bill Mensch videos that we're going to have. But again, questions to microphone@vcfed.org. If you think of a question halfway through the next one, I'm sure he'll be more than willing to answer it after the next one. But do we have anything in queue so far? Tell me I'm not on mute.
I've got a quick question, Eric.
Okay.
Can I go ahead and ask one?
No, please go ahead.
I'll be off. Eric?
Yes. Go right ahead.
Can I ask a quick one?
Yep.
Okay. The 6530 and the 6532 are very similar parts. Why were the pinouts so grossly different? Did he get it?
I
don't think he heard the question.
Bill, you're muted. Are you able to hear us? Okay. Stephen may be able to answer that one.
Not that particular one. There's always this question of the layout of the chip and the die. What is the most convenient for the people laying out the chip versus what is the most convenient for the people using the chip? And unfortunately, there's always tension there. Oh, I think we have Bill here.
Hey, I think I've got my.
There we go.
My mic on. Can you hear me now?
Yep, we can hear you now.
Okay. So the question is, why are the 32 and 30 different pinouts?
Not that particular one.
Yeah. And if you can turn off the audio for the stream, we're going to get the echo if you don't do that.
Okay, I'm having technical difficulties here. I'm trying to...
For people laying out the chip versus what is most convenient for people using the chip. And unfortunately, there's always tension. Oh, I think we have Bill here.
Yeah, so I'm not sure if it's you, Bill, or if it's somebody else that's on the feed, but somebody is actually playing the stream.
So the question is, why are the 32? Yeah, I'm having, I don't know why I can't get the technical stream and the meeting to play on my computer.
Yeah, I mean, you don't want to be playing the stream. And if you turn off the audio for the stream,
Okay, so I have it off now. Can you hear me?
Yes, we can hear you. Okay,
so now, maybe now I can answer your question.
Yeah.
So the question again, please.
The reason for the vastly different pinouts between the 30 and the 32 parts.
I don't really have a good reason right now. I don't know. Right now, if you look at the die photo, the only difference really is we don't have a ROM on it, and we have more RAM. So we weren't trying to actually make the two pinouts the same. So I'm not sure why they aren't the same right now as we talk. I could probably look at a die photograph and give you a better answer, but right now they could have been the same as far as I can tell.
Yeah, I was just kind of wondering because I made a little adapter for my Kim because I had a blown out 6530, right? Okay. And so I wanted to get everything under the part on a 40, under the 40 pin part. So I had to actually make two little boards, one to just translate pins and the other one to actually be the the ROM replacement part. It was an extra tedious task.
Yeah, exactly.
But thank you anyway. The Kim is a fun little board to work with.
Yeah, the Kim was awesome. I got a lot of people involved. I think many of the universities, colleges of engineering use the Kim. And I think there was a book by Camp and Smay and Triska out of the Iowa State. That was a very popular book that focused on or featured the Kim and the 6502.
Got another question here. What was the overall reason for implementing the 0 page? Was it performance or ease of conversion of other source programs?
It was basically a technique that it wasn't named this back in the day, back in the 70s, but I called the addressable register architecture. And I think when you watched that class that Stephen gave earlier today, he was indicating that you could have register files in page 0. So actually, for our C compilers that we sell, we have registers in page 0 for a C compiler, etc. So you can create faster virtual registers, if you will, or addressable registers. And so that's why we carried that forward from the Olivetti experience we had and the 6800 experience we had. So we weren't the only ones that had 0 page addressing.
Okay, thank you. Another question. I'm working on a logic accurate Verilog 6502 FPGA emulation platform. Do you see any gotchas using synchronous latches for the 6502D latches? D as in data.
Yeah. No, we have we have our own models in Verilog for the 6502, and it's cycle accurate. It's completely timing accurate for the 6502, and we also have one for the 816. So we used the model for our RTL was the model of the schematic of the CMOS version. So actually, there is some compatibility there, but I specifically don't know that you would have any trouble doing what you're asking.
Okay, thank you.
Tom?
One thing I wanted to thank you for is putting the power and ground on opposite corners. That has saved me at least 3 times by plugging the part in upside down. And all I had to do is turn the power off, put it in correctly, and it worked.
Yeah. Yeah, there's a lot of chips in the industry that were designed that way. So we were just following a successful technique. And you're welcome.
I would assume that there are people that hadn't followed that technique that have caused fried parts in the past.
Yeah, probably. Yeah.
So
okay, we got to. Oh, sorry. Go ahead.
Oh, I have another question, but if you have another question from the audience, they ought to go first. I've asked Bill enough things today.
Okay. This one is a little involved. If it's not too OT, I guess that means out there. Can you tell us how far the 65C02 followed the original NMOS 6502, and then the 65H16 followed the 65C02 regarding business and technical design decisions? Amazingly, some on various forums still to this day seem to be unaware of the CMOS 65C02's improvements over the NMOS. So I guess it's just a comment, and the question about how the 65C02 came after the NMOS, and maybe I'll just fill in the blanks and maybe ask, why did you do that?
Okay, well, back in the day, that's 1980, there was a RCA 1802. You may have heard of that one. Well, that was what I would call a disaster of a microprocessor. I mean, it used like 16 cycles to do something we do in like 2 cycles. So it wasn't a very good design. The other thing that my experience after I left MOS Technology, I went to Integrated Circuit Engineering Corporation in Scottsdale. For a year I worked there, and I reverse engineered all of the popular microprocessors for the Rome Air Development Center in New York. We had a contract. It was like $5,000 per processor to reverse engineer them. So I got to see up close and personal the 1802 CMOS processor, and I realized I had an awesome opportunity in using the same design techniques that I used in NMOS on CMOS, and I knew at that point I had a winning combination. Now, the one thing that I knew at the time, which no one else was interested in doing, like Intel didn't do this, or they're going from 4040, which would be difficult to emulate on an 8080, going to an 8086, they were all different architectures. Now, what I realized is that if I wanted Apple and others to use my CO2, it had to be totally compatible. So I made it totally compatible, except for one thing, and that is decimal correct. I had to use an extra cycle because I didn't want to violate my own patent. I designed the logic of the digital correct, or the digital logic function, math functions on the original NMOS, so I knew what I needed to do to work around that patent. So that's what I did. Now, unfortunately, when they plugged the CO2 into an Atari game, the Asteroids game broke up. The Asteroids broke up because they were using decimal math on the retrace time of the TV. So going back to this, I knew I had to be totally compatible. And one thing I wanted to make sure that Woz's disk drive that does some interesting things on read modify writes, I had to do it the same way because he was timing his disk drive off of that particular instruction. So then when I designed the 816, I knew I had to be fully compatible, and I have a patent on emulating a previous generation. So I knew I had to be completely compatible with NMOS, completely compatible with the CMOS, and then I realized I wanted to get Atari's business back. So then I did decimal correct in yet a third way. So my 816 actually has the same timing as the original NMOS part for the NMOS instruction and operation.
Wow, what a great answer. Thanks. Thanks, Bill.
You're welcome. So there's more to the story. The NMOS 6502 that we celebrate today, and we celebrate all days because the NMOS changed the world, but actually the CMOS version is the one that keeps millions of people alive, one heartbeat at a time, as we talk. So actually, the CMOS became more popular, far more popular than the NMOS. But we don't want to take anything away from the NMOS and the team that built it.
Including all variants and its use as a cell and other larger designs and so on. Do you have an idea how many 6502s have shipped?
Well, based upon some Rockwell numbers and some other numbers, I estimate as of about 10 to 15 years ago, I keep the same number. It's 5 to 10 billion of 6502s that came out of my designs. Now, there's a lot of other designs out there by a lot of other folks. On 6502.org, which is a really popular repository for interesting things about the 6502 family of products, you'll find all kinds of versions of the 6502 on there. Now here, since you're asking, this is my latest. This is using the Intel Max 10 technology in that black chip, and this is what we're using as our platform for prototyping IoT devices that use the 65CO2 and 816.
Oh, amazing. Thank you.
So actually, a lot of the people that you have on this show it's all about vintage, but I'm all about now. So going back in history and wanting to talk about the NMOS processor and the wonderful team that created that. And, that's a wonderful historical memory. But I'm today, and I'm into the future.
Excellent. Dag, if there are any other questions, Bill is in the next video as well, but we're adding another Bill and we're adding Eric Scheffler. So I'm going to start that one up, and we'll queue up any of the questions for that trio for after that video. We're coming into the home stretch. I still have a voice, barely, and we'll be back with Q&A in about 40 minutes, 45 minutes. But this is another excellent video.
Welcome VCF Virtual West. Wow, we're doing something for the first time here. It's guaranteed to screw up, I am sure. With me today, I have Bill Mensch and I have Eric Scheffler. Oh, I screwed the name up. Scheffler. Maybe I got it right. Bill, you may know from the 6502, the best microprocessor ever, and before the 02, there may not have even been microprocessors. So we're going to talk with Bill, and we're going to ask him how the heck he did it and what all he had to do, and then Eric's going to show us his monster 6502, which has taken a chip in an all different direction. Instead of going small, he went big, and I actually saw him plug it into the cactus and watched it run. So it's an amazing feat itself many years later. So let me set the stage for Bill Mensch here. Again, without Bill, I wouldn't have had the career I had. My career was based on the 6502. It's fair to say Eric's monster 6502 is based on it. So kudos to you, Bill. You set me up for a career that's still going, and I have a lot of people say that to me, and now I'm saying that to you. So this is a rare opportunity for me. So Bill, back in the days, I know what PMOS was. PMOS was in calculator chips, And you know, the way I tell people is PMOS pulls high easily, doesn't pull low worth of poop. And then there was NMOS, which can pull low easily, but you had to do something to make it pull high pretty good, called depletion mode or whatnot. And the question is, was there any decision making? Did you ever think about doing it in PMOS or in CMOS, or was NMOS the only way to go, and yet NMOS was broken, so you had to fix it? Or tell us how you got started with the process itself that made the 6502 possible.
For inviting me for this discussion, especially with Eric and his monster. I talked to my friends about I'm going to have a conversation with the guy that designed the monster. You have to go back to the beginnings of materials used for digital computers. Now we're talking about digital computers rather than analog, although my first computer that I worked on at Temple University was an analog computer. That's a different story. So if you go back to the days, the first computers were built on field effect devices. So field effect transistors were actually first built. And so field effect transistors actually occurred, I think, before field effect vacuum tubes. So the materials that are used to manufacture digital technology has a long history. I don't know when the first FETs and tubes were built, but probably back in the 30s or 20s or something like that. So now let's fast forward. I'm at Motorola. One of my first design projects was actually to complete the family of logic gates that could be used like they are now, right now, as a standard cell library that you could then call up to build integrated circuits. So that meant that Motorola, being a leader in the business, had PMOS metal gate, PMOS silicon gate, NMOS metal gate, NMOS silicon gate, CMOS metal gate, and CMOS silicon gate. So all 6 of the libraries, it was my job to complete the designs and put them in so that you had the input capacitance, output loading characteristics, sizing, and everything else, so that someone could place these in a floor plan. And it was for the local logic center in Boston for the computer manufacturers that on Route 128, I think is the name of the route, where DEC and these other mini computer companies were. But Motorola is realizing that they have to use these standard cell libraries so that people could build what they wanted to build for these IBM competitors called DEC and Data General, etc., Burroughs and some of these. So when I got to Motorola, they already had the foundry, already had the different processes. So we weren't going to design with integrated injection logic that the crazies that TI did with their 9900. You had to be crazy. I can't
don't
even
get me
imagine.
going on the night. Yeah, don't get me going on that.
So
that's a bit slice.
When you asked me why I designed with what I designed with, I didn't have a choice. I needed to design with a process that Motorola had.
Okay.
But then, so I designed with the PMOS silicon gate for Olivetti. Okay. Of course, I designed the logic families in all the processes that Motorola had in that day, and that is in the field effect transistors. So the PMOS, NMOS, and CMOS. I got to experience all the modeling of all the transistors. And because I was a technician at an advanced semiconductor lab called Philco Ford in Blue Bell, Pennsylvania, my job as a technician was to work with engineers and figure out the basic characteristics of materials, because we were designing the first solid state alternators that had a lot of current flowing through them to charge batteries in an automobile. And also we were working on radios, single chip radios. So I needed to know the characteristics of the, you call the cutoff frequencies of amplifiers. So I was working on all kinds of stuff. And the other thing that's interesting here is I was working with the thermal coefficients for those high current transistors that were in the alternators. So I'd have to look at the thermal coefficient from the surface of the chip, transistors, to the heat sinks, which was basically bolted onto the alternator. So I saw all of this material characteristics for semiconductors. So give me a break. So when I decide I want to be an engineer because I have to pay off my mother for my temple education, then I need to be an engineer because I could pay it off twice as fast. And so that's why I went that direction. So when I get to Motorola, I already know what I want to do. I already
very cool.
was using a computer because I had one piece of advice. Get into computers by an IBM supervisor in 1965. And you go, oh, so I was just fulfilling that one piece of advice, get into computers. Well, I didn't know what that meant. I didn't know what a computer was, really. That's why I did the analog computer at Temple. So now coming back to answer your question, I designed with the PMOS silicon gate. I designed with NMOS silicon gate enhancement load. And when you know the difference between the enhancement load characteristics to get full voltage on a chip, you realize that depletion load will get you the full voltage with one transistor, and you don't have to do all this bootstrapping and other things. So that's what I learned about how to design with integrated circuit or with FETs, field effect transistors, on an integrated circuit. So that means that when we embarked on the 6502 mission, Rod and I were already successful. We already knew how to do it. And when I got my chip to work the first time, Chuck was there. He couldn't believe it. Neither could anybody else, that this crazy guy who's, what at the time that was in 74. So I was 29. So here I'm 29, fresh out of college, more or less. And I'm making a bet with the operations manager at our tape out celebration at a restaurant in Scottsdale. Well, they're thinking, this guy's got pure ego. So guess what I did after that bet? I went back and checked the PIA again because I wasn't going to lose.
I think it was particularly fascinating to hear, Bill, that you had a chance at Motorola to use the different technologies, and so you knew the benefits and drawbacks of each one, and so that built up some very valuable experience for you.
Yep.
So I guess that more or less answers the question that I had about the depletion mode FETs. And so when you were working on the design for the 6502, you and the others on the team were also developing that process, right?
Right. Yeah. So we had to bring the whole thing up because what was there when we got there was, I think, PMOS metal gate. They didn't do any NMOS before we arrived.
So you really were starting from the ground up when you came in. So they had a process, and you knew that it just wasn't going to work for the 6502. There was just no way.
PMOS.
Right. I mean,
yeah.
Yeah.
Yeah, right. Eric, what they were doing was awesome. When we arrived, they were doing awesome. Their chips were 4 times the size of the 6502, and they were getting relatively good yields out of it, better than Motorola was getting. And you got to wonder how this small company could get better yields than Motorola.
Right. How is that even possible?
So
it was because of the spot knock mass set, right?
We talked about that before we started this video.
We did.
Yeah, the mass shop was tightly coupled into the wafer manufacturing. And at MOS, we could turn around layers in a day or two. And at Motorola, we'd have to wait a couple of weeks.
Right.
Impressive.
Right. Oh, I love MOS. You'll never find. I mean, I admit the bad things and I love the good things about them. But yeah, and they did some amazing stuff even with the masks of my day. They were defocusing and doing some of the patching of the masks like you were talking about before we started this. How'd you get drug along with Chuck then? Did he say, "Hey, leave Motorola and come with me," or did he go there and say, "Come to the light. I'm doing cool stuff"? Or how'd you end up in King of Prussia / Norristown?
Well, I had 3 flat tires.
That's you were driving on Route 202 then, obviously.
No. After I got the MOS, I had 3 flat tires. They didn't want us there. They did not want us there.
Oh, wow. Okay. Okay.
And just another piece of information. Now, you could say, well, maybe you drove over them when you were looking for a house to buy. Well, that could be what happened. But I was on the parking lot when I had the 3 flat tires.
I have a video of that parking lot.
What a delightful experience was to show up with everybody saying, we don't like you, and just one thing more, don't mess with the Godfather. You go, what? What's that about? Who's the Godfather anyway? So these are some of the comments. So did we enjoy working there? Yes. But what was this other stuff going on in the background? Because the people that were designing these awesome calculators are saying, why would John Pavinen bring in some cowboys from the West when we know we're totally capable of doing this kind of a project? A microprocessor is just a small part of a calculator. I'm going to give me a break. And especially if you have high volume and high yields.
Right.
Why would you bring some cowboys, 8 of them, from the West? So John Pavinen had some things.
The Gang of 8.
Yeah. So we weren't really accepted by some of the people. Other people, we were. But some of the people, we weren't. And so then, of course, then Chuck, look at Chuck's video. If you were with him, no problem. If you weren't with him,
Get out of his way. Yeah.
Yeah, get out of my way. I know what I'm doing and that. So Chuck was somebody that chose MOS. I never talked to anybody before we showed up. I don't think anybody from the other 8 other than Chuck. So when we showed up, and this is an awesome team with a great math shop and a great process engineering team that's going to make this happen in a short amount of time, I mean, we hit a home run without even.
Can you tell us the 8 names real quick by any chance?
Pardon?
Can you tell us the Gang of 8 what their names real quick by any chance?
Yeah,
Do you remember them all?
In the picture, if I brought the picture up, I'd be able to remember them better.
Okay, I was just curious. You might have said Dan Tonberry.
Will Mathis. You have myself. You have Rod Orgel. You have Ray Hurt. You have, I've got 4 now. You have Terry Holt. You have Chuck. Did I say Chuck already? You have Terry Holt. Then you have Harry Bauckham. Then you have Mike James. So
okay.
I think that's about it. But we had 2 mass designers. Then we got a 3rd one, Sid Holt, that somebody found at Princeton, working in Princeton or something. And she wanted a job, and she was a great contributor. We had an awesome team.
So did you find that you gained the respect of your MOS colleagues after the 6502 project? Or was there some point where attitudes changed and maybe your team won over the respect of MOS?
I think, like the math shop, the guy Don Payne, he was a friend of the family. As it turns out, he lived on the same street as the family that we called Opa and Oma. So they were like neighbors. It's like, how synchronous is that? But anyhow, Don Payne and I might have had a few conversations. But basically, we stayed to ourselves for the most part. And if you say, we feel respect there?
Well, you know, we respected you later. How's that? We had the utmost respect for our roots and our foundation and the 6502-ness of things.
Well, the other thing that you should look at here is 74, August 19. We all resigned 2 weeks before that. Our salaries were picked up by MOS the same day that our salaries stopped at Motorola.
Gotta love it.
Then we get in our cars and whatever, moving vans, if some people had moving vans. I don't recall the moving van. But anyhow, the point is that we leave and go across country. So, of course, it takes about 3 to 4 days to drive across country. So we show up the next week. But that's when we're trying to figure out what do we have going here. No computers. Okay, well, we had unlimited computer time at Motorola. No documentation. Motorola had the best documentation department in the world at the time. All these things we were used to at Motorola, we had none of that at MOS. Wow.
Yeah. That can be a shock. I've done that. I've gone, when I left Commodore and went somewhere, I was in for a shock when I got there. I had taken things for granted. So, Eric, do you have a question about the 6502 itself? We had talked about the ROR bug and other things. Is there a good?
Now wait a second.
Yeah, I think the
Bill, the ROR was never a bug.
I don't know. Okay. It's just one of the things we had listed. When I saw the O2, it worked perfectly in my book. So
But Chuck Peddle was the guy that signed off on the final instruction set. He signed off on
which came
something
from the VAX, right? Or came from the 1123?
PDP 11.
PDP 11, thank you. Which I never knew till I started talking to you that was the same instruction set.
Well, it's not the same, but they have the same name.
I mean, same, but it's the architecture of it. Yeah.
But let's talk about the ROR. I have.
It's not a bug, by the way.
I have the programming card without ROR. Now, you go, well, why wasn't ROR? Well, who's the guy that signed off on all the instructions?
Right.
Okay, end of discussion. He left off an important instruction.
Yeah, it's a good
bug.
instruction.
We had to repair it. We had to figure out how to put some more decode in there for ROR. Now, once you do some of these other things, you can find a way of doing it, and that was fixed. But it wasn't an ROR bug. It was an ROR brain fart.
So it was a lack of the feature in the definition.
And
so it wasn't in the silicon because it wasn't defined that way.
No, and I was counting on Chuck as Rod and anybody else on the program that Chuck was the guy that's going to say this is going to work right this way. So am I going to go, if you know anything about Chuck, am I going to go in there and tell him, Chuck, we need ROR?
Well, you might try, but
that was out of my lane. What was in my lane is putting the clock generator right on the chip called the 6502. That was in my lane.
Yeah, that's very important.
Yes, I'd forgotten about that we always needed a little clock helper in the Motorola stuff. Clock chip.
Clock helper.
Yeah, the Intel stuff had that too. They had some pretty complicated clock driving chips that you had to use with their microprocessors.
A company called ICS made a living supplying things like that too. So, give us another. You had a question about ADC or the history of add with carry or decimal, Eric?
I think it related to the decimal mode, which I thought was particularly clever. If you look at the implementation, it uses a set of XOR gates to selectively invert 3 bits out of each nibble. And I could even pull up the schematic if you're curious to take a look at that. But I think you told me before what the goal of that little circuit is just to add 6 to the number that's coming in order to do the adjustment.
Yeah, so if you're going to increment in decimal from 9 to 10, then the 1 for 10 is in the upper nibble and 0 is in the lower nibble. So if you look at it, you're adding 6 so that you roll over, because hexadecimal has 16 values, right?
Mm-hmm.
Okay, so that particular, that's the only circuit that was ever simulated.
Really?
And I did that in Fortran. I wrote the simulation in Fortran. So
you've heard the story that when they opened up an overseas copy of the 6502, everything was identical to our mask except for the add with carry. They had to drop in something, because I believe you went and got that patented, didn't you? The actual ADC process?
yeah, well, it's actually decimal correct. And so it's not just ADC, it's, I think, an SBC also, a subtract also. Okay.
Right. I'm trying to use shortcuts here. Yeah.
Yeah, and so that was the only patent we got on the
right
6502. So I actually did the design of it, but all 4 of us were on the patent.
You know, we did find something on the 6502 in my era. I'm talking early 80s. They found a 200 ohm short between VCC and ground, or VSS and VDD, as you all say. And that sounds like a poly short to me. And if I'm not mistaken, isn't that like 200 ohms square or something? But they had laid a chip, a heat-sensitive LCD, like think mood ring, on the die, and that's how they found this resistor that was just always on. I don't know if it was just a piece of poly or whatnot, but one of the process engineers told me about that.
Yeah, I don't know about that one.
Yeah, it's just one of those things where he said, oh, we found a, you know, it came in passing, but he had bought this little mood ring thing, so he really wanted to use it, and he actually found something with it. He found a transistor always turned on or something like that.
So that reminds me a little. So you're going to edit this, like what happened with Jeff?
No, so far everybody's hearing us. They're going to hear exactly what we're saying, but I'll edit out something if you tell me to.
No. What I'm saying is, we did a similar thing with Stephen Edwards, and ours went way over. So it was 80 minutes, and he carved it down to 43 minutes. So I'm saying, whatever you want to cut out of this, I'm happy with whatever you choose to cut out. But
I think everybody's going to want to hear everything you have to say in this format. But that's just me, because this is a techie. We're all techies here, you know. So
a question about how the 6502 was tested. So in other words, you get this chip back, and you're going to go into production, and you need a way to check every unit before you ship it out to the customer to make sure that the die is good and that the chip packaging didn't damage it during the assembly process. So how did you do that at the time?
Okay, so in the other video, you'll see the tester. So the tester is in Arizona, and I'm in Colorado. So you might be interested in, how did we figure out that the chip worked the first time? The very first chip.
Right. Good question.
So Chuck and the calculator guys, that was the enemy? No.
No.
The other design
We
groups.
know what you mean, the other people.
The other people. There was a calculator guys and a 6502 family guy. Well, at this point, we have a chip coming out, and from this tape out, when you say, okay, we're good, make the chips, then it took like 2 weeks. Maybe it wasn't 2 weeks. That's what it took at Motorola minimum. But anyhow, the point is that when you do that, then you have some time to build a tester. So when the chips came out and we packaged the first die, by the way, when you go into production, you probe the chips also. So we probe every chip, and then the good ones, the bad ones, we put an ink spot on so you knew which one was bad. So when you scribe the wafer, you basically use a vacuum tweezers to pick out the good ones. That's the one that goes in the package. So I don't think that we had probing set up at all when we got the first wafers out. So we just packaged them at random and put them on the tester. Well, Chuck is there sitting in the lab, and he's across the lab, and Rod and I, there's only 3 of us in the lab checking the first chips. And Chuck's there with his thumb wheels, that putting in the A9, load A, right? And then push a button. And then I don't know what he was looking at, but a display maybe that said that I think you have to do a load A, but you can't see anything, and then you do a store A, then
you see it.
Then you see it, and then he would say, okay, load A and store A works. And then Rod and I are over there, yeah! He knew that if load A and store A
Sitting there
worked,
with a scorecard, right? They call the programming matrix.
If load A store A worked, then 95% of the chip is working.
Right?
Hello.
Right.
So then let's put the next one in, 8D or whatever. And then, and I don't know if he had to, when he pushed the button, I don't know if that was just the opcode or it rippled through, the address would have been 8D or whatever, but there's Chuck. Okay, so the next instruction worked, and then Rod and I are cheering over there, and it's like, that had to take a half an hour or whatever for Chuck to go through 151 opcodes.
Wow.
Yeah.
And
that's amazing.
It was just Rod and I there cheering. We didn't have any mass designers that I recall, or any of the management team.
And you didn't have to probe it under a microscope to get it to work and stuff like that.
Wow, what a wonderful feeling.
It just worked. Now, another little tidbit, when I'm at Motorola, now I'm making a bet that my chip works the first time, right? So the first PIA chips come out. They had a Viatron tester there before we put it on the Sentry tester. Sentry testers, they didn't have at the time.
Is PIA a 6530 or 6532? I'm trying to remember which.
6520, 6820. We're talking
20.
about.
Okay, before the 22, then the VIA. Okay.
Yeah, and that's, if you look at the Apple One picture, the 2 chips in the lower left-hand corner, I was a designer of both of them. That's the PIA, 6820. But anyhow, 6820 at Motorola, we're testing, right? We put the PIA in the tester, push the button, good part. Put the next one in, and I have a test technician there setting it all up for me. Puts the second one in, good part.
I feel you, man. I like to have some failures.
Put the third one in, good part. At that point, I'm going,
there's something wrong.
Something wrong with the tester, maybe.
And then he goes, oh, yeah, there is. We don't have the power supply hooked up to VDD on the chip.
You're powering it from the chip, from the tester.
So I'm going, right. Okay, let's do that, and then let's retest them. First one, good. Second one, good.
We got to power them from
one, and all 5 of them were good.
Yep.
You go,
I've seen chips do that they'll work until there's not VCC on at least one of the pins, and then the chip fails.
So what I'm getting at is the first chip not only worked the first time, but like the first 5 chips we tested worked right the first time.
Twice.
Motorola never had anything like that. In fact, Ed Armstrong had a long beard waiting for getting 10 good 6800s on one wafer. We were getting, and I would go to the parties with the highest yielding PIA wafer in my pocket. They were 2.5-inch wafers. I put them in my pocket, and my wife at the time would say, why do you want to take that? I'm going, dude, wouldn't you want to know who designed the Corvette? No. Oh. Okay, well, I'll leave it behind. Whatever. But that's how passionate I was about designing these chips.
Now, were your wafers this size back then, or were they this size?
Well, what's 2.5 inches?
Probably smaller than this one. This is a ROM that MOS made.
Yeah, but
we used to try
okay.
and
Wait
cleave
a second. Wait a minute. For MOS, they probably did have 4-inch wafers. They could probably 3-inch wafers.
It's probably a 3-inch wafer. Yeah.
Okay. But Motorola at the time when we first started, they were 2.5.
And this wafer here is actually one I got out of the basement of MOS 3 years ago. They actually had them in an old storage cabinet because people said there's going to be stuff down there, and I'm like, there's not going to be anything in the old MOS building. But somebody must have put something from the test group down there, must have put a storage cabinet. There was no nitrogen on it or anything, obviously. But I pulled a good wafer, or not a good wafer, but an intelligible wafer out of it, and it turned out to be one I recognized.
You remember what part it was?
65. It's the 8563, the bane of one of my computers. So now you did the 6522 also, right?
Right, 6530.
And I used 6530s where I was at before Commodore because we liked the mask ROM that was in them. So we had a 6530. Ours were branded -005 for external customer. But we used to use those because EEPROMs I'd have to slow down to like 0.5 megahertz to even use them. So we used 6530s, 6532s, and then the 22 came along. And you changed my life, Bill Mensch, with one simple feature. And that was the auto-loading interrupt clock. Before then, we would get an interrupt, and we'd have to race to get there and reload the timer. And if you saw a square wave made by it, it'd jitter. Well, how do you write a real-time operating system where you don't know what time it is, ultimately, over a day or something? And your 6522 had an auto reload. As soon as the interrupt hit, it'd reload the counter and keep going. And we're like, we know what time it is. It's wonderful. So thank you for the 6522. I like that as almost as much as the O2 itself. So excellent chip.
Well, you're welcome, and my pleasure. And you know the spec on the 22?
Yeah?
Me jotting down information that Chuck and Will wanted.
Right.
On
Well, it
Arby's
looks like somebody, like a wish list of stuff people wanted, shoved in a chip.
But I didn't design it just one time. I designed it twice.
For CMOS?
No. Well, yeah, that too. But no, at MOS Technology.
Oh, okay.
The RB napkin is what I was going off. And then I didn't have to totally redesign the whole thing. But basically, then Chuck and Will said, oh, we want this. And then you go, oh. Okay, so now we have to take it all apart, put it back together again because of, I forget what the difference was from what they said on the first Arby's napkin to the second Arby's napkin.
Yeah, that's a systems guy for you, but we know what we like.
That serial port that's on it?
What's that?
The serial port I put on there?
Yeah.
That was, we want a serial port.
Right, right. It's a wonderful serial port. That changed the world also.
Definitely.
Yeah, I know. It was used in the original Macintosh mouse interface.
Yeah.
And it was also used in the
Jobs
Vectrex.
wanted me to make some
I ran vacuum fluorescent displays from it. You know, it was our 3-wire interface of the 1980s, of the 1970s and 80s.
Yeah,
was your shift register.
Too bad it wasn't I2C or SPI or UART.
That would have been too complex. Who would you have talked to then, back then? You know, so right at the time, that shift register, I could interface it to hard TTL or somebody else's display adapter or something like that. So it was right down the middle of the road. That was great.
There were some very clever things you could do with it for sure. The Vectrex used one to generate the raster character font on the screen. And so they would just simply load in 8 bits for one character
You can do
row.
stuff like that.
And then the 6522 took care of displaying it.
Yeah, that was a busy 6522, but it kept
Very much
up.
so.
You had like, what, 8 microseconds to get back to it.
So just so you know, that my tester, so I took it offline for a weekend, and I set up at home the first video game that used the 6502, and the 22 was a composite video audio for a game I created in 2 weeks called Barnstorming. And so what I had is a biplane flying around and put, 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 because that's the sound that the 22 would make. And so Chuck said, there's no way you can do a video game. I said, here it is. I'm done. But what the game Barnstorming was, there's a cow and there's a barn and an airplane. And I forget how I controlled the direction of the thing, but probably from switches.
Tell me you didn't hit the cow with the airplane.
That was the goal, was to eliminate the barn
Nowadays, that'd be called violent.
without hitting the cow. That was the whole freaking game.
Without hitting the cow.
Oh, that's great.
I gotta remember that. What's putt putt putt? The sound a 6522 makes. You know.
It was just it was just either on or off, basically.
Right. Oh, that's cool. That's cool.
That's very good. So earlier we were talking about really large wafers and really small wafers, and I'll use that as an awkward segue to show off the largest 6502 in the world. Let me see if I can get this centered on my screen. There we go, more or less.
Yeah,
and so it's got all the same functional blocks in the same places. I figured that you guys did a really good job doing the place and route to begin with, and so there was just no sense in changing it.
Well, there you go. Well, it's beautiful.
Well, thank you.
That's cool.
And
okay, so what was your contact with the 6502 before that?
Yeah, that's a good question.
That is a very good question.
On it? Yeah, why not the 8086 or the TI 99?
Well, the 8086 has 29,000 transistors, and that board would be a lot larger and more difficult to design.
Yeah. That was a joke. Yeah.
Well, I picked the 6502 for a couple of reasons. It was technically in the very first computer that I ever used, which was a Commodore PET. So it's not the Commodore PET that's behind me on the table there. It was a different one, but it looked very similar to that. And I did not learn how to program because I was too young. I just didn't understand how to program computers at that point. And unfortunately, by the time I got old enough to learn how to program, we had already moved on to different computers. And so there's kind of a soft spot that I have just because it was my first computer experience. The real reason is that it is a very compact design with a very minimal amount of transistors. In fact, I believe it's the least transistor count 8-bit microprocessor that you can get.
Could
be.
Many
So from my standpoint, it was very practical. 4,304.
Okay. But what haven't we talked about that was cool?
When we introduced the 6502 at WestCon in 1975.
Oh, yeah.
Okay, so you're at that small company in Pennsylvania. The real world was in San Francisco area, Bay Area.
Right.
And then there's the outpost called Phoenix, Arizona.
Right.
So what do you think it's like when you know you just designed the world's best microprocessor? and you know this.
Yeah.
And you're asked to go work the exhibit booth where people are flocking from all over the world to see this $28 chip. That's the 6501 and the $25 6502.
6502.
And you have a board that was the best-selling single-board computer of its day, the Kim Wan. What do you think it's like to work that booth for a couple hours at a shift?
I only know the CES show. Sorry. Speaking of Kim ones.
I got one back there too.
It's joyful. Well, Eric, I think you get attention with your monster there, right?
Yeah.
So you get people showing up saying, so tell me more about...
We always lost our voices. By the third day, none of us could talk. They
must
called
have been
it
so exciting.
Yeah.
I can't imagine, people coming up and they're seeing something that was an order of magnitude cheaper than the Motorola part. And then they could buy one there, just
didn't you
here's
guys
a $20 bill.
have like a barrel or something? He did something dramatic to like make it look like it was full of working chips. Only
a jar of 6502s.
Something like that.
They could have even been untested. But anyhow, no, the idea is you couldn't sell anything on the floor of the Moscow Center.
Right, you had to go to the suite.
So you had to go to the St. Francis Hotel. And we had, I think, the MacArthur suite, one of the suites there. And when we were working the booth, all we were doing, because there's so many people, and this never ended.
Telling them to go to the suite.
You grab their card, which you, like a credit card, where you put it on a thing to get an imprint. Mm-hmm. So we get your address so we can send you information. So we do that, hand the card to somebody that's running the scanning machine, and then you would hand them a data sheet, and then you go back and forth like this the whole time.
They didn't make me do that at CES because I had a tendency to do things with the card that was unexpected, like throw them, gnaw on them, things like that. So they learned not to let me work the booth. They just, but yes, it's long days.
But we weren't doing the actual thing with the credit card thing.
Right.
We were handing it to somebody that was skilled to do that. And then what we would tell these people that, hey, we can't sell you any chips, but we have beer and chips in the MacArthur suite. And if you come over there, we're happy to see you over there. We're selling the chips. And that's where the story, and I don't think it's mythology, it's what Chuck was doing. He had one jar with the 6501s and one jar with the 6502s. And so you would pick one out, and that's how you buy them. And I don't know what kind of a container we put them in or whatever, but the point is that there were the chips, and you could buy them, but you couldn't buy them at the exhibit because they wouldn't allow you to sell them there. So that was just a good reason for you to go over and get a beer and a chip.
So what kind of reactions did you get from engineers that came up? So an engineer walks up to the booth, maybe you remember some of these guys. What were their reactions when they learned about the 6501 and the 6502?
I don't remember specific reactions. Meaning that it was just general enthusiasm. I want to see what this is about, because even if they bought the chip, they may have never used it. It was just one of these things where it's a shiny object, and I got to get me a shiny object. It's like today you would find somebody handing out Arduino boards, little maker boards or whatever. That's the kind of today's world is that maker world that has people wanting to make things out of Arduinos and Raspberry Pis and maybe a Beagle board here or two. So to me, but what I wanted to get the point across is there's Rod and I. We're working as a team. We worked the show as a team. We drank beer as a team. We just enjoyed being there because we were the team, semiconductor engineering team, that made it happen. Mm-hmm. And so when you're out there in the real world, like they let us out of the cage and we're having a ball. And so we're seeing the enthusiasm for our design. How many people have that kind of an experience? Not very many of them.
Wow, that's amazing.
But most of the people would have had a bigger team. At Motorola, they'd say, engineers, you don't make very good people to be a representative of Motorola, so you stay back.
Yeah,
let the sales guy get out front. And so you don't have that at a big company. But when you don't have anybody that knows what you're doing, and there's only 8 of you, and the 2 guys that knew the details of the semiconductor manufacturing process, and Rod and me. Will didn't. Chuck didn't. They knew the logic. They knew how to apply it. But Rod and I were the guys. We made it happen. And I
Yes,
wouldn't
you
say
did.
this without mentioning Rod, because Rod was an integral part of the whole thing. That bet that I had with Rod, I don't even know if we had enough beers. We didn't need another beer because I wanted that. But the idea was that he believed what Chuck was saying, and what Will was saying is that we don't have any salespeople. We had a couple salespeople, but how can we compete with Motorola's sales department and their worldwide distribution system that they were set up a long time? And so you can see where Rod would say, well, the 6501 is going to outsell the 6502. Well, of course, I'm thinking technology wins out. But Chuck and Will and Rod, the other three guys on the design team, they would, of course, say that, yeah, we're going to steal sockets. We're going to plug a 6501 in the 6800 socket. So that would be normally a good bet. Yeah.
Hey, I want to thank you both for being here today. We had some initial problems. We worked through them. We overcame, hopefully. Hopefully this audio is not all echoes, in which case nobody will ever hear it. But Bill, I really want to thank you for your time today. You were, like I said, I wouldn't have a career without you. I'd be a TV repairman doing something else. So, and Eric, again, thank you for your time. I know you did a backflip to help me out here, get everything lined up, and we even beat Skype into submission. So, on behalf of both Eric and Bill, VCF West Virtual, thank you for watching, and it's been a real pleasure. And stay by for questions and answers live, I think, but we'll see if that actually happens.
Well, Bill, I want to thank you and Eric for inviting me to participate in this. It's been fun. Hopefully, Eric, you and I can talk some more. I want to find out more about your passion for the 6502.
Well, now you have each other's Skype numbers.
That's right.
6502 is the highest level of passion I can think of for you to do what you've done with the Monster 6502. I just think that's amazing.
Thank you. I really appreciate it. And Bill, thank you so much for inviting me. I'm very pleased to have been able to participate.
Excellent. So, just to get it out there, I also think Eric's nuts.
Hey now.
But that is an amazing piece of work. So, have we gotten any questions in the queue?
We do.
Excellent. I figured we would.
Yeah. Okay. Acorn used your 65C02 in the BBC Micro. It looked at the 65816, but then developed the ARM, which Sophie Wilson has said in interviews was loosely inspired by the 6502. Why was there no 32-bit successor to the 6502 like the ARM?
Good question. Oh, I'm not. Yeah, I'm on.
No, you're good. You're good.
Yeah, that's a good question. Well, Sophie Wilson and Steve Ferber visited me in 1983, fall of 1983, when I was completing the 816. And actually, they are the only people that ever asked me about my abort pin on the 816. So actually, when they came to visit me, they wanted me to do what I did for other companies like Xerox and NCR and Burroughs and, well, Rockwell and a bunch of others. And that is design their chips for them. And because they didn't know how to convert their ideas into silicon. So they kind of left disappointed that I would refuse to design their ARM 1. And Doug Fairborn there, I think he actually was involved with designing the first ARM chip at VLSI Technology. I think he works there. He was a photographer there when I was there one time at Computer History Museum. But going back to that, what they wanted to do, and they did, is a RISC processor. So they were visiting, I don't know if they visited Berkeley or Stanford, and on the same visit, I think they visited me. I think that's what they say when I saw one of their videos. So what happens there is they wanted me to design something that was not compatible with the O2 and would not be compatible with my 816. And basically, with the BBC, what they thought they would do is leapfrog Apple, going from 8-bit to 32-bit rather than the 16-bit, which was the Apple IIgs. But the Apple IIgs wasn't designed at that point. And in fact, when I did visit Apple, they always told me they have their 16-bit processor, which was actually a 32-bit processor with a 16-bit data bus called the 68000. So there was that confusion there, and I wasn't about to depart from the 816 that I was almost finished with to do what the BBC wanted to do with their Acorn computer. So what happens is, but if you look at what takes place with a 32-bit processor, look at all of the support that you have to have, and look at all of the software tools you need. So I realized that if I did a 32-bit, I would have to be competing with whatever Intel was going to come up with, whatever Motorola was going to come up with, and whatever these guys were going to come up with. And so I decided I'd stop at 16 bits. Although Chuck came back to me in 1992 to design a chunk, that's what he called it, chunk, which is a 32-bit version of the 6502, but we never did that. So today, I still have lots of opportunities with 8 and 16-bit, so I don't think I'll ever do a 32-bit, but I think somebody else did a 32-bit version of the 6502. So actually, I looked at that, and actually, Prudential-Based, who went out of business at the last little recession in 2008, Prudential-Based invited me to Gold Street. They wanted to take me public in 1984, 1985. That would have been 14 years before ARM went public. But when I met them in Gold Street, I still remember the front of the building that they were in at the time. And I go, well, wait a minute, you guys don't know what I'm doing at all. No, we don't. No, we don't know what you're doing. But it's an interesting story. I go, yeah, and I don't know what you guys do, right? But I think what you're trying to do is make money off of taking my company public, right? Yeah. Well, I'm sorry, but I'm not interested in money. I'm just interested in doing my thing. And so if I do this, then what happens? You have all of these people wanting to be part of this, and pretty soon I'm on the sidelines, more or less like Wozniak was on the sidelines, and Jobs knew how to market his Macintosh, and you know the rest of that story. So to me, the 32-bit represented a leaping out of what my comfort zone was into this financial world that I just love what I'm doing, and I still love what I'm doing.
Great, thank you. Great answer. Stephen has a question for you.
Yeah, I was going to ask, so with the 65CO2, you extended the instruction set in a number of very useful directions and so forth. I'm curious, sort of the instructions you added, which were your favorites? Which were you, boy, yeah, I really wish this was the first in the NMOS 6502. I have a few guesses personally.
Well, actually, I never wished I had done something earlier. I never wished I would have influenced the instruction set of the NMOS version. That wasn't what I was. I'm a semiconductor engineer, and having a great applications engineer or systems engineer, that's what Chuck was. Chuck just didn't have the backing of Wall Street, or he would have been side by side with Jobs and Bill Gates and the rest of the crowd there. But Chuck was a systems guy, a very good systems guy. And so systems people is what I was doing, is implementing what they wanted. And so I'm an enabler. And now you can take that any direction you want, but I am an enabler. And so my technology enables people to do what they want to do. So when you asked me the question about the CO2, there was one company called Telenet in, I think, Virginia, that was GTE introduced me to them. And Telnet was the one that did the original, I think, the original data packets for the internet. And so they told me if they ever had a 10 megahertz 6502, that there is no processor in the world that could compete with them, including the 432, which was a 4-chip 32-bit processor from Intel at the time. So now, of course, I've got a 14 megahertz 6502. But Telnet was the one that had me put memory lock on. So GTE is the one that introduced me to some people in the systems business that wanted some new instructions. When Wozniak never had Apple never had anything to do with either the 65C02 or the 816. Although they did look at it and they said, well, that's interesting, but we have a 68,000. We're not going to use your 816. Oh, okay. Well, that was disappointing to hear. And so you see what I'm saying here is these instructions that I added, I had one, well, I probably had more than one, but a graduate of Princeton was named Paul Hiddle, was Larry Hiddle's son. He got his master's degree from the University of Arizona. I said to Paul, what should I do? This is about the time C language came out in 1980, probably 82, 83 timeframe. So what happens is he's saying, well, compilers use a lot of stack operations. That's why you see the new stack addressing modes of the 816. So a lot of this comes out of talking with systems engineer, and that's where I get my ideas. So when Wozniak came back to work on the Apple IIgs, I think he also helped with the Apple IIe that used the 65C02. What he he had determined that my CO2 instruction set would do things that would increase the performance by like 20%, going from the NMOS to CMOS. But that kind of after the fact, so to speak. They didn't really. It's like me and Apple is like a love-hate relationship. So it's not what you might imagine.
What else is out there, Dag? Are there additional questions? We're almost at time.
Yes, there are.
All right, well, let's...
Okay. Yep. What change did Steve ask you to make to the VIA?
Oh, I don't think it was Steve. I think it was somebody that was working with Steve Jobs, so not Steve Wozniak. What happened was they were using the VIA for the mouse interface on the original Macintosh, and the VIA, the 68,000 would have all kinds of interesting addresses that had nothing to do with the next step in the instruction. So they had random addresses, and so what happened was those random addresses would cause random accesses to the VIA, and a random access could reset an interrupt or do some other things that weren't desirable in the 22. So what they wanted me to do is make any non-valid address, because you do know that if you have a chip select, which we have on the 22, if it's not chip selected, they wanted me to go to register 00, which wouldn't cause any damage. So they knew what would happen with a random address generated by the 68,000. The other thing is that they wanted me to fix it so that I could drive from the mouse to the Mac. That conflict, although it was something you wouldn't want, they didn't want it to damage the 6522. So I made those two changes, and then Jobs wanted to give me something for my work, and I said, no, look, I license technology. I'm going to fix it so GTE could sell you more devices. We want your business, but you don't have to pay me anything. You don't have to do anything for me. And then they finally said, well, we'd like to do something. And I don't know if that's for legal reasons or what, but I said, okay, there was 100 Cortlands built. And a Cortland was an Apple IIgs and an Apple IIe case, but it had Cortland on it. I have one of those in my display case in my office. And so I said, I'll take one of those Cortlands if you have one of those laying around. So a Cortland showed up, and that was my compensation for changing to 22 to work with the Macintosh.
Another great story. Thank you. Do we have time, Eric, or not really?
Well, I mean, I'm trying to keep to the schedule, but by the same token, we're
okay
with our last exhibit. I think probably it's best to push the remaining questions online, and we can answer them either as an attachment to the video or whatnot, if
Sure.
that's okay with everyone else. Because at this point, we're going to bump away from the 6502 discussions. We've had a few of those, and jump back to Intel. We've done 4004. We've done a couple of 8080 machines. And I wanted to sort of close the loop with an 8008 machine. So we've got Mike Willigal with his Scelbi 8 and a DG video card. So I'm going to start that video at this point and bring it home.
Hi folks, it's Mike Willigal. I'm going to show you, welcome to Virtual VCF. I'm going to show you my Scelbi reproductions and talk a little bit about the Scelbi computer. Spend a few minutes with you. I hope this works out. I've kind of kludged together a video setup. I'm not really set up for it, but here goes anyway. So basically, this is my setup with the Scelbi 8H. I will now kind of bring it in so you can see a little better what I've actually got here. All right, we're going to start this by booting up the Scelbi 8H, which there's no, in the original Scelbi 8H, it came out with 4K of memory. There was no ROM, no monitor. You basically had to toggle in through the front panel using individual instructions of bootloader. Made it very difficult to boot. So like at least one original owner of the Scelbi 8H, I added on the back a monitor and a PROM I wedged into the, I hacked onto one of the RAM boards. There's 4 1K RAM boards. Each RAM board has 32 1101 chips. So it's a lot of chips, but not much memory. So anyway, to boot this thing, you basically have to toggle in an 8008 jump instruction. Before I put this ROM on here, and I used it a few years without ROMs, I had to toggle in a bootloader. The bootloader was about 40 bytes, more or less. And it took me about 10 minutes to get the machine booted on a good day. On a bad day, it might take me an hour just because I'd made mistakes and whatever. So to boot the machine, I put 1004 into the front panel, which is a jump instruction. So I interrupt the CPU. You can see the interrupt light on. I step. I put in the low address byte. There's a 14-bit address on the 8008, although only 12 bits are used in the 4K Scelbi 8H. So the first byte is the low address, which is 0 for my monitor, and the second byte is 17. This is all octal, and you can see it's starting to execute instructions, and I'm stepping through it, and I say run. And what happens is it's now running. I can put a no-op instruction in here, and I can interrupt and step through more instructions in the front panel, and I can resume running. So that's kind of the fundamental operation of the front panel. You basically got to toggle in instructions to do anything. So what I have connected to the I/O ports in the Scelbi. Now the Scelbi was came out slightly before the more well-known Mark 8, but it had some I/O capability built in. It had 6 8-bit input ports and 8 8-bit output ports. And they came with some Scelbi offered for sale along with the machine, some interfaces. And one of them was the Scelbi keyboard interface. And I have that here. And you can see it runs through these 12-pin, 12 conductor cables, the 8-bit bus. It's actually 8 bits of data, 1 strobe and 1 ground, although you're better off not using the ground and connecting all your grounds directly back to the power supply, which I've done here. So there's a keyboard interface which connects to a keyboard. There's an audio tape interface which connects to read and write the tape. The actual tape read and write is extremely reliable. They had a expert engineer develop this. It wasn't developed by Nat Wadsworth himself or any of his people. He hired a guy to develop the tape interface, and it works very good using frequency shift key modulation. On the bottom there, as these 8008 computers start to get into the marketplace, especially the Mark 8, which got a lot of press, people started building onto them, because when they originally came out, they came out with memory and little else. Well, the Scelbi, they had the keyboard interface, they had the cassette interface, they had a teletype interface, and they also had an interface that would display characters on the oscilloscope. But after a while, people started adding peripherals to the, especially to the Mark 8, and the Mark 8 also used the 8008. And it wasn't that hard to adapt things between the Mark 8 and the Scelbi. So what I have in that bottom of those 3 peripheral boxes is a digital group. Some guys in, a guy out in Denver actually created a video interface for the Mark 8. And there is at least one existing Scelbi that had that adapted to it. So everything I've done here was done back in the day. The monitor I put into the ROM that I use to boot this now was a hacked version of one that was printed up in a Micro 8 newsletter available back in the day. So it was called the Creed monitor. I adapted it. It was originally written for baud.it character code. I adapted it to ASCII and my Scelbi I/O interfaces. But essentially it's a Creed monitor, which was available back in the day. And so as you can see, I have a video display over here. And what I'll do is I'll just take a second. I'll jump over to adjust the chair in the video. So I'm I have a so I've got the monitor up, and the way this monitor works, it's very clever. It's 256 bytes, and what you do is you type in a 3-digit octal code that makes up an 8-bit byte. So, and then you give it a command. So if I want to put in 0 in the high address and 0 in the low address, I type 000, high and low, and it displays the memory at that location. Now to make this demo go a little quicker, I preloaded a program at address 002. And there's the start of the program. And I can increment and decrement through memory. To get that program loaded, the monitor itself does not have a bootloader. But what it does have, because it's very easy to add in, basically edit memory. So I basically typed in, using the monitor, into page 15, a cassette tape read program. And from there, I could read from the cassette tape a program I've already written, and I have a game called Hangman, which I had loaded on tape, and I read in just by typing in this program. It takes me, maybe 5 minutes altogether to type in the cassette tape read routines and then run the tape and read in the program. So at page 2, I have another program. I've got a game in here. So this video output, it's 8 lines at 32 characters. It's the display I'm rather impressed with. It's much better, crisper, maybe because it's less resolution than like an Apple I or Apple II. So it's got a nice crisp display. I'm very impressed with how the digital group guys came up with that board. And one of the shortcomings of this video display is it doesn't really support cursor controls. You can basically write 1 byte, it'll add that byte to memory. It's basically scanning through memory like any video system. And so as you write to memory, it increments what it's writing. So as I put a 0 here, it's putting a 0 in memory and then increments the location. And so the next 0 goes in the next location and so on. And that goes all through memory, all 256 locations of video memory until it gets to the end, and then it wraps. But there's one cursor control. If you write all 1s to the video system, it'll basically set the pointer to the end of memory. It doesn't clear memory, it points it to the end of memory. So you got like a home function. So you can write to memory and you can home, and those are the only 2 cursor controls. To clear memory, to erase the screen, you've got to write a program that's going to write spaces to all of memory. So that's what's happening when I type L and it refreshes and it prints the memory. I'm actually got a program, the monitor there actually clears all of the video memory, homes it, and then displays the high address, the low address, and the data. So anyway, at this location 2, I've preloaded a game just to save us a little time. And you can see that the Scelbi Bil.H, if you put some effort into it, as it comes from the factory, it's not very user-friendly, but if you put some effort into it, add a ROM monitor, add a video system or some kind of I/O system. A lot of people used teletypes back in the day, and Scelbi did offer a teletype interface. It actually becomes useful, but straight from the factory, it's hard to use, hard to get much out of it. So anyway, this monitor allows you to whatever address to execute a program. So if I type X, it's going to start the Hangman program. And this Hangman's a little game. It's kind of the classic game. And it's asking me, do I want to enter and try a new word? And I say yes. And I've got to guess a letter that might be in that word. So I'm going to start with like E. And sure enough, there's an E. So that word is 5 letters with E as the second letter. So I'm going to guess again. I'm going to say maybe a B. And it tells me, nope, I've got one H. And if I make mistakes, let's try J. As I make mistakes, it eventually spells Hangman. When it spells out Hangman, you've lost the game. So I happen to know the first word. And here, so it's spelling out the word. I've got a good guess, another good guess. And you'll notice the screen kind of breaks up when it's refreshing the screen. And that's because when the Scelbi is writing the video memory, it can't update the video. So the video kind of goes on hold. So I happen to know what the first word is. and it's hello. And there I've got the right answer. So I'll try another new word, and this time I'll just get it wrong on purpose, and you'll see how it spells out hangman. I'm putting K's in, and there's no K in this word. And so it's spelled out hangman, and the real word was computer. So I've got that wrong. Should I try a new word? So that's the little game. So the Scelbi 8H, this is the Scelbi 8H. This is a reproduction, pretty authentic reproduction. It runs with the same chips and equipment as the original. And so that's my little tour of the 8008, and this is what personal computing would have been about in 1974 going on into 1975, just before the Altair came out. There's a long history of the Scelbi computer business. They eventually got in, when the Altair come out with the 8080 processor, which was like 10 times faster than 8008, the Scelbi computer business, they couldn't compete using an 8008 based machine. They would have had to redesign it. So they ended up going into publishing. They wrote very good manuals. So they ended up publishing a lot of manuals for home computer users, or computer hobbyists, as it was known at the time. And I'll exit the compute program, and I'll come back to the monitor. So that's my little demo of the Scelbi computer with a digital group video card, audio tape interface, keyboard interface. Pretty nifty system, and once you get everything together, it's fairly usable. Unlike, you know, the Scelbi 8H without all these peripherals, without a monitor. You really need the monitor. Without it, it's really hard to use. It's my VCF demo of the Scelbi 8H with digital group video card. There's a lot of fun building this, a lot of challenges involved. Visit my website, www.willagale.net. Follow my blog where I post some of the adventures I run into. And hopefully have a great day and stay safe.
All right. Let's see if we've got any. Uh-oh, somebody's running the stream and is off mute. Well, hopefully that's not me. Anyway. We got any questions lined up, Dag?
We do have one question. What was the most challenging part of your project?
Can you guys hear me?
Yes.
Yeah, hopefully you're listening on the chat, not the stream.
You can hear me, right?
Yes.
Yeah, I've got the stream off on this end. What was the most challenging part? I think the biggest challenge was actually the number of boards I ended up building, copying, duplicating, cloning. The whole Scelbi computer business, over the 2 or 3 years they were in the computer business, they designed about 16 boards, and I've cloned every one of them, plus the digital group video board. So the challenge was just the scope of the number of boards. I've also done Apple I and Apple II clones, and in a lot of ways that was a lot simpler because there was only one board.
I can imagine.
Yeah.
Is there anything else queued up? I have a question while we're waiting if Dag doesn't have anything, because I'm curious as to why you went through the effort of cloning it out versus looking for an original machine.
Originals are scarce.
Yeah.
There's I know there's a couple at the an 8H and an 8B in the Computer History Museum, but there's like 12 of them that I know of worldwide. They don't come up for sale very often. I probably could have found one if I wanted to, but they're also very expensive. So it ends up I can clone one and get and then I don't have to, if I damage it, my clone, it's not something I worry about that much. I can just build another one. So.
All right. Steven's got a question for you. Are you going to ask it?
Yeah. So for the video board, was it all essentially all TTL chips? Was it using a CRT controller? Was it a simple frame buffer, or was it using a shift register like something like the Apple One was using?
It actually used 1101 1101 256-bit SRAMs and counters to index into the SRAMs. So it kind of shifts through those 1101 memories. And then it had a Motorola character generator to generate the the output of the character generator was sent to an 8-bit shift register that or maybe it was an 8-bit, 6-bit shift register that's used to generate the video. So, but all the rest of the chips were Jelly Bean 74, XX series chips. Although there were some odd ones because they used like a 7401s, which you don't see used that often, and a couple other oddballs. But the chips, the only chip that was hard to find was the character generator, the Motorola character generator, and I still haven't actually found the correct version. The version of the character generator I have on my board. Typically, companies back then that built character generators had like standard character sets. And the one I have in that board has the same character set, but it's shifted around a little bit. So I have some hacks on the board in the counter section, some undoable rework, so that I can, when I find the right chip, I can take the rework off and go with the real chips.
So do you actually sell these clones? Do you sell the boards? Do you sell the plans? Or are you...
I sell the PCBs. I don't sell very many because it kind of takes an unusual person to want to build a Scelbi. There's only, just for the chassis itself and the, on an 8H, there's close to 1,000 parts, between capacitors, ICs, and there's a lot of parts to build a Scelbi. Although it's cheaper than an original system by a long shot, it's still not. And then like the memory, I'm using the 8H has 1101 SRAMs. To get that, it was a 4K system I demonstrated. It took 128 1101 memories. And even if you can get them for a couple of bucks each, that adds up.
Yep.
It's expensive. And then there's a lot of connectors. Each of the boards has 2 edge connectors. So in that chassis, there's 16 edge connectors. And plus there's edge connectors in the peripheral things. Those things add up. So the cost of the system, it adds up.
Yep.
So you won't find too many. There are a few people out there that bought sets of boards. And I think they're having fun.
I think that's why they bought them.
Yeah, I hope so.
Were there any other questions for Mike, Dag?
Not at this time, no.
All right. In that case, I think we're kind of close to done for the day. I did want to let me do this. Oops, I didn't want to do that. That's somewhat better. I did want to basically close out the show, and I'm not going to belabor this, with thank yous for everyone that participated, all the folks that submitted videos, all of our volunteers, all the people I thanked at the beginning, and then some. I'm not going to take a chance of naming people by name and missing out and getting yelled at later, but y'all know who you are. And folks did a ton of work to get this show on the road and get it on the air, and I really appreciate all the help with that. We're not done yet. The live stream will end up being posted to YouTube, as well as all the individual videos, so that the Q&A is in place and so on and so forth. Myself or a volunteer will edit down the live stream a little bit and just cut out some of the junk that we put at the front and the back. Any of the unanswered questions that we've had during the day, some of them that got lost in spam or we didn't have time for, or whatever else, we're going to route those back through to the videographers, through to the presenters, so that we can get those questions answered. And those will either be attached to the videos on YouTube or some other place on our website, so that you can see what's going on. And once again, this virtual event was a lot of fun, and I think it came out pretty well for what it is, but I don't want to do it again. Not because I didn't enjoy doing a virtual event, but I really want to do our live VCF West at the Computer History Museum next year. I think it's scheduled for the 7th and 8th, or 8th and 9th, 7th and 8th, Friday the 6th for setup. And it is my great hope that we can do our traditional event, our series of traditional events next year. And we may sprinkle in a few smaller virtual events throughout, just to keep this kind of thing going. And
thank you, Eric. You did a great job.
Thank you. Did someone else have something to say? I thought I saw a message pop up. Someone wanted to say something.
Oh, I think someone was saying good job or something over here.
Oh, okay.
Echo my thanks. Andy Gippert says, I'd like to echo my thanks to all of you as well. Did a great job of helping us redeem VCF West in a virtual way.
Yeah, I want to give a big thanks to you, Eric, because I know you were pretty invested in having a live VCF West when we began this journey this year, and we're planning on, I think, doubling the size and taking a much larger space at the Computer History Museum. And then obviously, like the rest of us, I should take this off my ear, I guess. Obviously, like the rest of us, you've really, adapted and kind of adapted and really put on a good show, and I think really opened up some new opportunities for us, because there's a lot of people who we'd like to have at our shows, and we've never really thought about a virtual event. And I think this will bring opportunities to have remote or hybrid events in the future, which is wonderful. And this is our first one of this size. I know Mike did one for Seattle, but this is the bigger one. That one was kind of
someone put it together.
Yeah, it was kind of put together
ad
quickly.
hoc,
Yeah.
so it was okay. Crude.
Yeah, and I think this is it's going to help us build a blueprint for the future.
Yep. But like I said,
Yeah,
live is better.
Eric, I was also going to say that you put together a group of people that we probably would have never had in this. So the ability to pull people in from across the nation, all the way out to the East Coast and around, really made it a fantastic show. So I enjoyed it a lot.
Yep.
And I think I do want to add, Eric, that this show has also brought in kind of almost the idea that we can do for some of our shows, almost like a Rockin' New Year's Eve kind of thing, where we can have multiple sites talking back to each other. And while we still are limited here with some social distancing, we couldn't have a large watch party on one coast while the other coast is hosting the main show. I think there's opportunities in the future as things get a little better with what's going on in the world, that we can do that, and we can have really this larger kind of get-together shows, and I think it's exciting.
Yep. No, I agree with that, and I'm definitely looking forward to seeing how we can leverage the new skills and knowledge and tools and toys that we've come together with. But I'm also very much looking forward to marching through the Computer History Museum and looking at everyone's toys in person next year. Keeping my fingers crossed. I was I was struggling. I was optimistic till the almost the last minute before I switched over to a virtual event for West. I really was hoping that this whole thing would be over. Clearly, I was incorrect.
There was one other. I was going to say that we're as much as we kind of see this as done for us right now, it really isn't done, because this is going to be on YouTube. Yep. And it'll get passed around, and there'll be more coverage than we had. I think we were at times we were over 200.
Yes.
200 viewers. I didn't keep track of it all. I wasn't watching it all the time.
But there are people, I'm sure, dropping in and coming out. You have a schedule for the things that they wanted to see. I think we are going to have much larger over time. I think there's a lot of people who are going to. I guess this is probably a vintage expression, TiVo now, right? Because no one has TiVos.
Yeah.
People will TiVo it and watch it later. When it's more convenient to them, and obviously when we start splitting up the exhibits and the talks, people will be able to grab them and watch the ones they need at any time, because it is tough to watch an 8 or 9 hour WebEx kind of, or YouTube, whatever we want to call it.
Yeah, the original, sorry to interrupt, Corey, but the original videos are already up. I think we made a boo-boo. We were supposed to post them for midnight tonight, but we posted them for midnight last night. So those all are all up as individual videos. Of course, the Q&A part is not part of that, so we'll have to decide if we're going to cut and paste or, haul out the Q&A sessions after each video and put those someplace. And then, like I said, of course, we've got some other work to do with regards to unanswered questions and other materials. All of the folks that have posted websites or slideshows or whatever else, we're going to have to find a way to add those to the existing videos and put those up on the either YouTube or elsewhere. And I will be looking for volunteers to help with that. So don't go and hide too fast.
We got some guys to help you.
We got a few guys.
We got some guys.
And here, but Kay Savitz, big thank you to him for help processing all the videos for Eric. It was great. Just between me and Eric getting all the people together, it was fantastic.
Yep. Like I said, there's a ton of people that did great work.
Also see that I've changed to Emmett Elvey someplace along the line.
Yep. I don't know about the rest of you guys, but I need a drink and actually some food. Otherwise, the drink's going to hit harder than I want. Thank you all again.
VCF East will be virtual. All right, so mark your calendars for October.
Well, VCF East will actually, I think, be a hybrid event. So depending on what, we'll have some live as well as some, like we've done here. And we will work within whatever constraints that we are given. VCF East is actually held on an old military base, so there's a lot of different rooms, so we can actually set up one exhibit in each room and have multiple cameras, run around. So it'll be a little bit different. It'll be a hybrid event, but I think it'll be just as exciting as West. And we hope you will join us for that in October.
In costume, because it's, close to Halloween.
I plan on being in period 1980s costume, and everyone else should plan on being as well, because it will be Halloween week. Well, not Halloween month. Yeah. Excuse me.
All right. With that all said, I am cutting the stream, and we will see you in virtual space after this. Thanks, everyone.
Yeah, thanks to all the organizers.
Bye, everybody.
Yeah.
Bye. Bye.
Bye-bye.